Welcome to this course on modern JavaScript. We've seen JavaScript evolve from a toy language into something extremely powerful and now running many of the critical services that we depend upon in our day-to-day life. So there is no doubt that it is an important language, but learning JavaScript today can be pretty overwhelming. This is because of the sea of outdated and misinformation out there because JavaScript has evolved significantly in recent years. This course avoids wasting too much time in legacy features. We do not assume any prior JavaScript knowledge, and we start from modern basics and build up to advanced concepts without slowing you down with patterns that are no longer recommended. This course is designed as a quick reference, so it starts at the basics, but then it goes deep. This means that you can watch it again and again whenever you need to jog your memory, and even if you've been doing JavaScript for a while, you will undoubtedly learn plenty of new tricks, overcome some common misconceptions, and get a deeper understanding of the various JavaScript constructs. By the end of this course, you will be comfortable reading any JavaScript code present in any library or application framework. I am excited that you chose to join me as we journey into JavaScript development. So let's get set up, jump right in, and start learning. A key reason for the success of JavaScript is the fact that it is the language of the web, which means that you don't necessarily even need to set up for it. You can just start playing around with it in your browser. For example, within Chrome, you can click the triple dots hidden way up over here on the side, select More Tools, and then select Developer Tools. It's a good idea at this point to also memorize the shortcut for this. For my particular operating system, it is Option Command I. Now this will open up the developer tools, and one of the features of all of these developer tools is the console. This is where you can enter some arbitrary JavaScript and execute that within the context of the currently open page. So let's use JavaScript's built-in console.log function and pass in a simple string like hello world. The browser will execute the JavaScript, and no surprise, we see hello world on the console. Now, of course, if you are thinking of doing JavaScript professionally, we are going to need a more professional developer setup. The first thing that we will install is Node.js, and you can simply head on over to nodejs.org. You can download straight from the homepage or go into downloads for the current version and then select the download that is appropriate for your operating system. Mac as well as Windows come with very nice installers that will guide you through the whole installation process. Once we have it installed, we can verify it quite easily by opening up the terminal or the command prompt and then executing node, passing in a ---- version. This will log the version of the Node.js that is currently installed. Now Node.js also comes with additional binaries called npm and npx. npm is used to install packages and npx is used to execute various scripts, and it's good to make sure that they are available on the terminal as well. Now the specific versions of Node, npm and npx doesn't really matter because they have been very stable for a number of years at this point, so any version that you have will be fine. Now the next step is to install a nice IDE, and for that I recommend Visual Studio Code. It is a free open source IDE from Microsoft, and it is available for all the popular platforms. Head on over to code.visualstudio.com. From here you can go into the download section and grab an installer specific for your OS. Once you have it installed and boot it up for the first time, you can see some nice walkthroughs on your right hand side that you can use to learn more about this IDE. Now that we have our IDE and Node.js set up, let's just create a very basic hello world application and execute it through Node.js. Now running our code through Node.js allows us to think about JavaScript in isolation without slowing us down with concepts that we do not need when we are simply trying to master JavaScript by itself. So we create a nice folder for all of the code that we will be working with, and then once we have this directory, we cd into it and open it up within Visual Studio Code. Let's create our first JavaScript file. We will call this index.js, and it is conventional to call the entry point of our application as index, and within that we write that same sample statement that we saw before, which is console.log hello world. Now we can execute this code from Node.js by opening up the terminal, executing the node command, and this time passing in the path to the file that we want to execute, which of course is index.js. This executes the code through Node and outputs the result, and of course we see what we would expect, which is that string hello world. Now that we have our IDE and Node.js set up and verified, we can start playing around with more and more JavaScript language features. Something that can greatly enhance your developer experience when you are learning a new programming language is the ability to debug your application, and that's quite easy to do with JavaScript, so let's take a look. Here's a simple program that logs hello world to the console. Now, of course, console.log by itself is actually a great way that you can use to debug your application. In addition to that, the JavaScript runtime provides a debugger statement which can be used to pause our application at a particular point in time so that we can inspect the state of our application logic. Now, if we actually execute our application without attaching a debugger, the debugger statement is ignored by the JavaScript runtime. And you can see this over here, our application executed completely without pausing at that debugger statement. Now, Visual Studio Code actually comes with a number of tools which we can use to debug our JavaScript. You can find them in the Run panel on the left. From here, we can click on Run and Debug, and this will give us the option of how we want to execute our JavaScript and then attach our debugger. The simplest option, of course, is to select Node.js, which provides us a nice isolated environment to learn JavaScript by itself. This starts executing our application using Node.js and pauses our application at that debugger statement. To resume execution, we can press the continue button. Once we resume, the console.log statement occurs and the program terminates. Now, debugger statements are great when you are not debugging within your IDE, but when you are using an IDE, there is actually a better way where you can simply click on the sidebar next to your source code, and that will actually create what is known as a breakpoint, and this will essentially behave like a debugger statement, but you do not need to modify any of the source code. When you have breakpoints within your application, you can see them within the breakpoints panel within VS Code. With this breakpoint created, let's run and debug our application again, and now you can see that we are paused at that console.log statement. Once you are happy with your debug session, you can press the resume button to let the program execute to completion. There are lots of other features provided by the VS Code debugger, like the ability to watch and modify variables, look at the call stack when we are working with functions, so I encourage you to keep playing around with the debugger as we look at more and more JavaScript features. JavaScript only has a few primitive data types, and we've already used one primitive, which is the string in our simple log messages, and we will uncover the others in this lesson. Now, all the strings that we have created up till this point, we have used the single quote character. We can actually create strings within JavaScript using the double quote as well, and at runtime there is no difference between these two. It's simply a matter of preference. I personally prefer to use single quotes wherever possible. Now, if the string that you are going to write contains a single quote on the inside, it is recommended that you use a double quote on the outside, and similarly, if you have a string that contains a double quote on the inside, then we recommend that you use a single quote on the outside. Now, you can actually put a single quote inside a single quote by using an escape character, which is backslash within JavaScript, and then using the single quote that way. And similarly, within a double quoted string, you can place a double quote by using backslash double quote, as we have done in this example. Now, another primitive data type that exists within JavaScript is the number data type, and this is actually always a 64-bit floating point. So of course, we can use it for integers, but the same data type supports fractions as well. And this is actually a signed value, which means that we can have positive as well as negative numbers within JavaScript. Now, because the number data type is a 64-bit value, there is an upper limit on the integers that we can store safely within this. But if we want to store integers which are as large as we want, for example, a Google value, we can do that with the big int data type that is provided by JavaScript. To represent a big int value within JavaScript, we simply write our integer and then add the suffix of the character n. Now, of course, because it doesn't have a fixed precision, it is not going to perform as nicely as the number data type, so only use it if you really need to. A key data type within JavaScript which plays a critical role in conditional logic is the Boolean data type, and this only has two possible literal values, which are either the literal true or the literal false. Undefined within JavaScript is a special value and a data type, which is the value that the JavaScript runtime will return when a variable hasn't been initialized. Another primitive value within JavaScript is the value null, and this is a value that JavaScript developers will use to denote a value that isn't present. For example, if you ask a function for a user profile, but the user isn't currently logged in, we can instead choose to return null to denote that we have no user to return. We will discuss the differences between null and undefined and how we can simplify these concepts in much greater detail later on. And finally, we have a symbol, which is a data type that you are very unlikely to use yourself, but exists as a part of core JavaScript to internally make things like iterables possible. The symbol type allows these internal implementations from leaking out to our normal codebase. And that's it. This is a nice cheat sheet of all of the primitives that exist within JavaScript. Now that we know what we have to look forward to, we will discuss lots of details of all of these primitives in their own dedicated lessons. Modern JavaScript has two ways for declaring variables, and in addition to discussing the technical differences between let versus const, we will also look at the things that are common between these two ways. So let's go. The first way to declare a variable within JavaScript is with the let keyword. We write the let keyword followed by the variable name with an optional assignment that we want for this variable. The main advantage of using variables is that they allow you to use the same value again and again without having to type that out. So when we log out example, we don't have to type out hello world again and again because that is the value that is contained within the example variable. A feature offered by the let variable is that we can assign it a new value if we want to. For example, we can assign it a different string, and now when we log it out, we get the new string. And it doesn't even have to be a string, it can be any other value that we want. For example, it could be a number, and now when we log it out, we get this new number. A key feature of creating a variable with let is that initialization is optional. What this means is that we can create a variable with let and not assign it any value. Now at this point, if we try to use this variable, we get that special type that we talked about, which is undefined, which is the value that the JavaScript runtime returns if a variable has not been initialized. Of course, at any point after we have done an assignment, the variable will contain the value that we assigned. The other way to create variables within JavaScript is with the const keyword, and as we look at the differences between let and const, you will find them to be quite intuitive. Here we are defining a variable called message with the const keyword and assigning it an initial value of the hello world string. Now of course, the advantage of using a variable is that we can use the variable without having to type that value again and again. That value is what the variable will return. Now at this point, this looks very similar to a let keyword, so let's discuss the differences between let and const. Now with the let keyword, we do not have to provide an initialization because of course the let keyword allows us to reassign that variable at any point that we please. With the const, we must provide an initial value. If we do not provide a value, the JavaScript runtime will throw an error, and if uncaught, our program will exit. Now the reason why we must provide a value when we declare a const variable is because of the other restriction that exists on const. That is, once we have declared them, we cannot assign them a different value. The restriction that we must provide an initial value and that we cannot assign a different value once it has been initialized are the differences between let and const. A key feature of these JavaScript variables is that they prevent silly mistakes, for example, trying to use a variable before it is declared or trying to declare another variable with the same name. Let's declare a simple variable called example. Now if we try to use this variable before it has been declared, the JavaScript runtime will throw an error that this variable is being used before it's been declared. Any portion of our code where a particular variable declaration is not valid, for example, the section before the variable declaration, is what fancy JavaScript engineers might call a temporal dead zone, where temporal is basically for time. That is, in a matter of time, this code is going to execute before the code to execute the variable declaration. Now another silly mistake that is prevented by these variables is trying to declare them again. This is primarily a programmer error in larger code bases where we do not realize that this variable has already been declared and we should use a different name in order to not conflict with the existing code. Modern JavaScript variables are lexically scoped to the code block that they are declared in, which means that there are less chances of name collisions and unexpected variable values. Now we will look at various code blocks like if, else, functions, for loops in future lessons, but the fundamental thing that is common between them is the presence of parentheses. So we can actually use parentheses by themselves to create a very simple code block. Of course, since the message variable is declared within this code block, it is available within this code block, so we can safely log out its value. Now this variable will actually not exist outside of this code block, which means that if we create another code block, we can use the same variable name and provide it a different value, and everything will be perfectly fine. However, outside of this code block or in another code block, this variable will not exist, and if we try to use it, the JavaScript runtime will throw an error. As you can see, modern JavaScript variables are quite well controlled to prevent silly mistakes. And to recap let versus const, if you plan on reassigning a variable, use let, otherwise use const. Thank you for joining me, and I will see you in the next one. Providing good quality comments for your code is an art in itself, but from a technical standpoint, JavaScript has excellent support for providing multi-line as well as single-line comments, so let's take a look. Everything after a double slash within JavaScript is considered a single-line comment, and if you want your comment content to span multiple lines, we can do that with a multi-line comment which starts with a / and then ends with a */. Syntactically, these are the only two types of comments within JavaScript. Now, even though the / comment is called a multi-line comment, there is actually nothing stopping you from using a multi-line comment that spans a single line. Now, once you start a comment with double slashes, the rest of that line will be a comment, so it's common to put a single line comment either before the line or at the end of the same line. Now, with the multi-line comment, because it owns its opening as well as its closing, you can have it pretty much wherever you want. You can have it by itself, you can have it before your code, in the middle of your code, or even after your code on the same line. Now, most commonly when you are documenting your code, you will be using a multi-line comment that has been formatted in a special way that works nicely with IDEs. Fundamentally, it is a comment that starts with /** instead of just a /*. And as soon as we add the second star, the IDE automatically closes this comment for us as well. Such a comment is called a JS doc comment, and as far as the JavaScript runtime is concerned, it is still a simple multi-line comment, but for our IDEs, it holds special meaning. Additionally, as we press the enter key within this comment, not only does the IDE add a new line, it also adds a star on that line as well to give it a nice visual look. A key feature of these ** comments is that they will actually show up as documentation for any of the code that follows. For example, here we are declaring a variable called example, and this comment has been associated as the documentation for the example variable, and we can verify that as we hover over example, you can see the contents of the comment as a nice tooltip. Now, one thing that might be obvious with multi-line comments is that of course they cannot contain the */ character sequence, because of course this closes the comment. If you do want */ within your multi-line comment, you can however do so by adding a / before the /, and this will escape that / of the */ sequence, allowing you to use */ within your multi-line comment. Now, an obvious thing that I want to point out, just in case you haven't experienced comments in other programming languages, is that they are completely ignored by the JavaScript runtime and are purely your comments and documentation for the next developer that's going to be working with this code. As always, thank you for joining me, and I will see you in the next one. There is a saying that the two hardest things in programming are cache invalidation, naming things, and off-by-one errors. Even though naming things are hard, what is technically possible as an identifier name within JavaScript is quite easy to discuss, which is exactly what we will do in this tutorial, and also cover some basic naming conventions. So let's go. First up, the set of valid characters for JavaScript identifiers are the underscore, $, or any Unicode letter. This means that all of the variable names that we see over here are valid identifiers. In addition to these, the JavaScript runtime also allows digits to be a part of an identifier. However, there is a restriction that the digit cannot be the first character. So as an example, if you put 0 at the start of the identifier, the JavaScript runtime will throw an error. Another thing to note within JavaScript is that the variable names are case sensitive, so these two are distinct variables. For the valid set, we've used this term called Unicode letter, which is a loose term but basically means characters you see in various global scripts are okay, but it doesn't include all Unicode characters. For example, an emoji in an identifier will result in an error. Now, even though an emoji might be ruled out, it does mean that you can do some pretty crazy stuff. For example, create this thing for the meaning of everything. However, I would recommend sticking to the standard Latin characters for everyone's convenience. Now, you might argue that there are valid cases. For example, you could use the pi character for the pi variable, but again, I would highly recommend not doing this because it is going to be a torture for someone to type without a special keyboard. Now, let's talk a bit about naming conventions. Most commonly in JavaScript, you will be using camel casing, but there are circumstances where developers will use something else. Now, one thing that does look good, however, it is almost never used by JavaScript developers, is the snake case. As mentioned, for most things within JavaScript, people will use camel casing. The other common identifier convention is Pascal casing, and we use this when we are working with classes or when we want to declare something special that a library expects, for example, React components. And a final convention that we find within JavaScript is capital snake case, which people use for immutable constants. Now, in terms of the big forms of naming conventions, the final one that you might be curious about is kebab case, but fortunately you don't have to worry about anybody using it in your codebase because this is not a valid JavaScript identifier, because the dash is considered a minus sign by the JavaScript runtime and does not become a part of the identifier. And in terms of naming things, don't stress too much. As you read and write more and more code, you will naturally start to improve your naming skills. As always, thank you for joining me, and I will see you in the next one. Learning JavaScript can be hard, but one thing that makes it extra hard as a beginner is that while you are writing JavaScript for the first time, it's easy to make silly mistakes, but you get no helpful errors from the JavaScript runtime. Consider the very simple example of the built-in JavaScript parse float function. This function takes an input string, and if that number can be passed into a floating point, that is the number value that it returns. And of course, it works perfectly fine with this particular string. Now, this function is really designed to be used with strings, and you shouldn't be allowed to pass in a number. However, if we do make the mistake of passing in a number, it actually works fine without any errors. Now, you might think that this is perfectly fine, and I don't necessarily disagree with you, except for the fact that this is a completely useless function call because there is no need for parse float in this particular case, and I'd rather get an error and not have just code lying around for funsies within my code base. But there is a thing that is worse than useless code, and that is invalid code. Now, since we haven't looked at arrays yet, here is a very simple example where we have an array that contains two numbers. Arrays are sort of the lists of JavaScript, and you might think that if you want to join two arrays, you could just use the plus operator. So if you have an array containing 24 and an array containing 48, if you combine them, hopefully you should get an array that contains 24 and 48. However, if we were to run this code, instead of getting a valid result or an error, we get this strange stringed concatenation of the values of the different arrays. This is where adding TypeScript to your project, even if purely for the purposes of linting, can greatly improve your developer experience. It's like a professional developer looking through your code and pointing out silly mistakes. TypeScript is available from npm, and to get started, we are going to first have to initialize our project for npm by running npm init and passing in the flag -y to just accept all of the defaults. This creates a package.json file. The next step is to install TypeScript from npm, which we can do quite easily by running npm i TypeScript. This brings down TypeScript from npm and dumps it into the node modules folder for local use. The TypeScript npm package comes with a binary called tsc, which stands for TypeScript compiler. We can use it to initialize a new package.json by invoking npx tsc, passing in the command line flags --init to create a new tsconfig, --checkjs, which is an option to enable type checking for JavaScript files, --no emit, because we don't need TypeScript to transpile our code, we are just using it for type checking, and then --root dir, which is a good option to make sure that all of our source code is well contained within the src folder. Once we execute this command, a new tsconfig file is created for us, where tsconfig of course stands for TypeScript configuration. And it is automatically picked up by VS Code, and it has started to validate our JS files already. We can see the two errors that are showing up, which are obviously silly mistakes, either they are useless or downright dangerous. In addition to Visual Studio Code, TypeScript is a core part of other modern JavaScript IDEs as well, but even without an IDE, we can use TypeScript to validate our code quite easily from the command line. To execute the compiler for checking purposes, we actually just execute npx tsc, and you can see the same errors that we saw in the problems panel. Now, of course, if you are going to be running this command again and again, it's a good idea to jump into our package.json, add a new nicely named script target, for example build, and then use that to invoke tsc. This way we can use a feature of npm called npm run scripts to execute tsc. So for this build script, we would run npm run build. Organizing your scripts within package.json is a good practice to follow to help others discover how you expect them to use your project. TypeScript also allows you to use .ts files, which opens up the JavaScript language to additional syntax which can be used to validate our source code even further. But for this course on pure JavaScript, we will leave TypeScript running in the background as a part of our IDE, seamlessly doing its powerful and intelligent linting. I also have a course on TypeScript which you can watch after you've completed this one. As always, thank you for joining me, and I will see you in the next one. A picture is worth 1,000 words, but a word is worth 32 bits in C++. How conveniently you can work with strings in a programming language greatly impacts your productivity. Fortunately, modern JavaScript strings are pretty damn awesome, and by the end of this lesson, you will know all there is to know about strings, at least at the level of a professional JavaScript developer. So let's go. As we saw in our lesson on JavaScript primitives, we can create strings using single quotes or double quotes, and it's mostly a matter of preference, but for me personally, I prefer single quotes as I don't have to press the shift key. Additionally, we also saw that we can use the escape character / to embed a single quote within a single quoted string or a double quote within a double quoted string. Now, because JavaScript uses the / character as an escape character, if we want to use / by itself, we have to escape it with another / as you can see over here. Now, there are plenty of other escape sequences within JavaScript as well. Among the popular ones is the Unicode escape sequence, where we use \u followed by a Unicode quote point within curly brackets. There are a few relating to whitespace as well, for example \t for the tab character and \n for the new line character. Let's take a deeper look by first discussing some core behaviors of the JavaScript string data type. We create a simple variable called person that contains a very simple string, and of course if you log it out right now you will see this string. The string data type provides a number of useful methods. For example, there is toUpperCase, which can be used to convert the string to uppercase, and similarly there is toLowerCase, which converts the characters to their lowercase values. A fact worth knowing about JavaScript strings is that they are immutable, which means that calling functions on them might return a new string, but it doesn't change the original value of the variable. For example, if you log out person, it is still going to be that original string. We can actually access the individual characters of a string by using an index within square brackets, and this is zero based like all good programming languages. And of course, if you go out of bounds, JavaScript returns that type that we've talked about before, which is undefined, which basically means uninitialized. One additional thing worth pointing out is that JavaScript doesn't have a separate character type. Even individual characters are still a string. And speaking of types, there is a special operator within JavaScript called typeof, which returns the type of its operand. For example, if you apply it to a variable of type string, it returns the literal string string. Strings also have a length property, which returns the number of UTF-16 characters of a string, and our example, Mr. John Doe, has 11 characters including the spaces. Talking of Unicode, you can pretty much put any Unicode characters within the string that you want. As an example, emojis are perfectly fine. Modern JavaScript has a feature called template literals, which makes multi-line strings and string concatenation much easier than it used to be. The way you define a template literal within JavaScript is by using the backtick character, which you can see on screen right now. And when you are using backticks to create simple strings, it's also conventional to call these as template strings. Now, of course, because these are delimited by backticks, we can actually use single quotes and double quotes inside of them without the need to escape them with the \. But as you would expect, if you wanted to use a backtick inside of a backtick, you have to escape it with the \, as we are doing in this final example. Now let's say we want to create a string that contains two lines, a line 1 and a line 2. Traditionally, we would have to insert the new line ourselves with the \n, and then to make sure that we can continue on to the next line, we use a \ at the end of the line. This basically means that the same string is continuing on to the next line of code. Template strings, on the other hand, are multi-line by default. So we can just write the code that we would write, which is line 1, press the enter key, line 2, and now we have a string containing two lines, line 1 and line 2, as we can see in the output. The other great thing about template strings is how they greatly simplify concatenation, which is, in layman terms, combining two strings to give a bigger string. Traditionally, if you wanted to combine title and person with a space in between, we could do this with a plus operator. But with template strings, we can actually use this feature called interpolation, where we can use $ followed by curly braces, to jump out of our string context into the surrounding JavaScript environment and bring in expressions like the title and the person so that we have a much neater way of saying title space person. Now, string interpolation will automatically convert any of the passed in variables into their string equivalents. For example, if we have an item count which is of type number, we could use the plus operator to add it to a string to get a bigger string, and the same works when we use interpolation in a template literal as well. The number 11 gets converted to a string and becomes a part of the output string. Now, of course, whenever we have special characters, the question that you should have is what happens if you want those characters as a part of the string? For example, if you wanted to use $curly bracket start, well, the answer is quite simple. You just put a backslash before it, and now the $curly bracket no longer acts like a string interpolation. Modern JavaScript strings are full of useful methods, so let's focus in and look at the ones that we are most likely to use in real-world code. Kicking us off is the trim functionality, which can be used to remove white spaces from the starts and the ends of a string. So here we have a string that starts with the tab, has a few spaces, then hello world, and then on the end, some spaces and a new line. The trim method will get rid of all of the white spaces from the edges of the string, so we are left with just plain old hello world. We can also use trim start to just remove the starting white space, and alternatively, use trim end to just get rid of the trailing white space. And of course, if we run this code, you can see that the results match our expectation. Now, if you want to be more specific about the things that you want to replace, JavaScript also has a replace functionality in the form of the replace method. However, unlike what you might expect, it actually only replaces the first instance of the found value. So the first dog has been replaced with a hound, but the second dog has been left intact. Fortunately, modern JavaScript has another method called replace all, which does replace all instances of the found value. So all instances of dog have been replaced by hound when we use replace all. A thing that often comes up in UI programming is the desire to create repetitions of the same string. For example, we can repeat the character x 3 times to get triple x, or for a more real-world example, we can combine 1 with 100 zeros to get a Google, and repeat also works with bigger character sequences. For example, we can do echo, 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 echo. Now let's talk a bit about search. Modern JavaScript has this lovely method called includes, which searches for a substring within a larger string. For example, we can check if this sentence includes the string fox, which of course it does. We can also use the method starts with to check if a string starts with another string, which this particular string does start with the. And similarly, there is a method called ends with, which we can use to check if a string ends with a particular value. For example, this string does end with a dog. Now, all of these methods are case sensitive, which is a good thing, because if you are looking for a big dog, we really don't want to get a small puppy by mistake. If you want to go more low level with your searches, we can do an index based search as well. For example, here we have a message, brave, brave new world. And if you look for the index of brave, it is at index 0. And we can also look for the last index of brave, which of course in this particular case is at index 7. Now, if the string that we are searching for is not found, these methods will return -1. And just like the other search methods that we saw, these are also case sensitive. Now let's talk a bit about formatting our strings. We have a simple string called heartbreak and a second string called hotel. And right now, if we log out first and second, we get them aligned left. But what if you want to align them to the right by adding some more spaces before the hotel? The concept of adding some space is called padding, and no surprise, there is a method called pad start, which takes a desired length and then automatically adds the correct number of spaces to make the string match that length. So here we are padding the start of the second string to make it match the length of the first string. Now we might want to pad the end of a string. For example, we might want to add these spaces before showing this hotel icon, and we can do that with a similarly named pad end function. Another thing that you might want to do is some slicing and dicing of strings, and JavaScript strings have this lovely method called substring, which you can utilize for most use cases. You can pass in a single argument for the starting index. For example, here we are saying that give us everything after the length of hello. And we can actually even pass in 2 arguments, one for the starting index to start from, and one for the ending index that we want to exclude. And here we are saying that give us everything starting from 0, but before the index of world. As you hopefully noticed, there is a lot of power built into JavaScript strings, and that is to be expected from a programming language that was originally designed to work with user interfaces. As always, thank you for joining me, and I will see you in the next one. Perhaps the simplest data type in all of JavaScript is the humble boolean, but nonetheless it is critical to writing useful programs, so let's take a look. A boolean is a general programming concept, and it always has two values, and within JavaScript these values are represented by the literals lowercase true and lowercase false. Using the JavaScript typeof operator on a boolean data type gives back the string boolean, which is of course why we are calling them boolean. We don't normally use a boolean by itself, as it often shows up as a result of a comparison operator. For example, here we have a variable called person which we have initialized to John, and if we apply the triple equals operator, which is called strict equality within JavaScript between person and the string John, we get back true. Similarly, if we compare it to something else, for example the string Jane, we get back the boolean false. The key use case for a boolean is when it shows up as a result in conditional logic. For example, here we have a person that might be Judy or it might be Kate. If person is going to be Judy, we are going to log to the console hi J, and if it's going to be Kate, we are going to log hey K. Right now we have initialized person to Judy. This means that the triple equal comparison with the string Judy will be true. And similarly, the triple equal comparison with Kate will result in false. The way the if condition works within JavaScript is if the expression provided to if is truthy, and of course true is a truthy value, then the block of code contained within if will execute. And similarly, if the expression evaluates to a falsy value and false is a falsy value, then the block of code will be skipped over. And if we execute this code, no surprise, we see hi J. Now if we were to modify the person variable to be Kate and then execute the code again, of course this time we see hey K. In terms of boolean operators, one that we really need to care about is the exclamation point, which is lovingly called the bang, and when used twice it is called the double bang. The exclamation point is the negation operator, and it is also called the logical not and the logical complement. Its behavior is quite simple. It takes a true and turns it into a false, and it takes a false and turns it into a true. And you can actually use it twice, and for a boolean it would have no side effect, so the true will become false and then will become true again, and similarly false will become true and then false back again. But this is great for converting falsy or truthy values of other data types into true boolean, true and false. An empty string within JavaScript is falsy, so applying double bang to it converts it into a true boolean false. And similarly, a non-empty string is actually truthy, so applying double bang to that converts it to a boolean true. Using truthy and falsy values within conditions is normally frowned upon, and you really want to use real boolean true and false, and using the double bang allows you to convert these into real booleans. We can combine two boolean expressions with the operators double ampersand for and double pipe for or. Here we have a variable defining a state that can be pending or done, and because of some unforeseen circumstances it might end up being something else, in which case we want to show an error. So if it is indeed pending, we show valid. If it is done, we show valid. Otherwise, we show unexpected state. Notice the duplication of code between the pending and the done code blocks. Wouldn't it be great if you could combine these both conditions into a single conditional? And that is where the OR operator comes into play. If either of these conditions, state equal to pending or state equal to done, are true, then the whole of the condition will turn into true. That is how the boolean OR operator works, and it allows us to combine those two conditions into a single conditional block, so we don't have to repeat ourselves again and again. The opposite of the boolean OR is the boolean AND operator, and unlike OR, where either of the conditions being true results in the whole thing be true, with the boolean AND, all of the conditions have to be true for the final expression to result to true. Here we have a variable for an HTTP status code, which can be between 100 and 599. If it is 200, it is success, but if it is in the range 400 to 500, we want to show an error, and to combine the conditions that it must be greater than equal to 400 and less than equal to 500, we use the boolean AND. So as an example, right now it is 200, so it will fall down to success, but if it is 404 not found, it is going to lie in the range 400 and 500, and therefore we will log out error. And for any other value, for example 301 moved permanently, it is not 200, it is not in the range 400 to 500, and therefore we log out unexpected status. When you have a variable that is intended to store a boolean value, some developers have very strong feelings about what these variables should be named, and specifically how they should be prefixed. Here are a few examples to give you an intuition about the most common prefixes. If you want a variable that will be true if the user is logged in, don't call it user logged in because it's confusing if this is a boolean value or an object containing some details about the user that is logged in. Instead, prefer the more obviously boolean looking is user logged in. Similarly, if you have a boolean for when the user has access, don't call it access because it looks more like an object, and instead prefer has access. If you want a variable to be true if the user can dance, then prefer can dance. Similarly, if you want something to be true if the user should provide an address, use should provide address. Notice how the prefixes are naturally appearing in the comments as well, and in terms of the English language, they fall under categories of verbs, but personally, I recommend picking it up from whatever sentence you would naturally use to describe these variables. One thing that even I strongly feel about is when variables have negation in their name. As an example, do not name a variable is not allowed. Don't use any negation term like the word not within a variable name. It's going to be perfectly fine and easy to understand when the value is true. For example, something is not allowed. However, when it's going to be false, you are going to need to do a double negative mapping in your brain. Is not allowed is false, and therefore something is allowed. Things would be much better if we called a variable is allowed, and it's very clear when something is not allowed and when something is allowed, and these are the same as the previous conditions, which were a bit hard to understand. Now that we've taken a deep look at booleans in isolation, it allows us to safely look at more attributes of the core JavaScript data types. As always, thank you for joining me, and I will see you in the next one. One of the harder, often misunderstood primitives within JavaScript is the number data type. So in this tutorial, not only will we look at the basics of number, but also its limitations, some special numbers, fancy modern syntax, and lots more. So by the end, you will have complete mastery of this critical data type. So let's go. The number data type within JavaScript is a 64-bit signed floating value. This means that it can be used to represent integers as well as decimals as well as negative numbers. Now make no mistake, they are the same data type, so 1337 will be exactly equal to 1337.0000 if you wanted to do that comparison. Modern JavaScript numbers can also include an underscore, and this is purely for readability purposes. This does not impact the value that is contained by that number. Additionally, you can declare numbers with the scientific E notation. After the E, you are basically specifying how many times you want the decimal to move towards the right. Here, of course, we are saying that starting with the value of 1, we want the decimal to move 6 times towards the right, giving us 1 followed by 6 zeros, which is a million. We can actually provide a negative value after E as well, and that will move the decimal point towards the left. So here we are saying that starting with 1, move it 6 times towards the left, giving us 0.5 zeros and 1. Similar to other primitive types, the type of operator also works with numbers, and when you apply it to a number value, it returns the string number. Now the number data type within JavaScript is a true binary floating point value, which means that they suffer from the binary floating point error that you might be familiar with in other programming languages. If by any chance this is the first time that you are experiencing this, you can actually visit this website to learn more about this fact. But in short, it exists in most programming languages, including Java, C, and C++. As you would expect, JavaScript numbers support all the common mathematical operators. You can use the plus operator to add two numbers, for example 1 plus 1 is 2. You can use the minus operator to subtract one value from another, for example 5 minus 1 is 4. You can use star for multiplication, for example 5 star 2 is 10. You can use the forward slash for division, for example 10 divided by 4 gives us 2.5. You can use the % sign for remainder, also called modulo. So 3 divided by 2 gives us a remainder of 1, and 6 is a perfect factor of 3, so that gives us a remainder of 0. JavaScript also has the exponent operator, which you might be familiar with as power, and it is represented by double stars. For example, 2 to the power 3 gives us 8. Now with these mathematical operators, there is also a concept of shorthand assignment. As an example, consider a simple variable which we have initialized to 1, 2, 3. We can do a mathematical operation, for example +1, and then assign the value back to the original variable. Now of course this does work because 1, 2, 3 plus 1 is 1, 2, 4. However, there is a shorthand syntax for this particular statement. We can do the same thing with plus = 1, and what this does is actually takes the variable adds 1 to it and assigns it back to the variable. As far as the runtime behavior is concerned, these two statements are perfectly equivalent. And of course, this shorthand version exists for all the other mathematical operators that we've seen as well. For example, 123 minus 55 gives us 68. 123 star 2 gives us 246. 123 divided by 2 gives us 61.5. 5 divided by 2 gives us a remainder of 1. 16 to the power of 0.5, that is the square root of 16, gives us the value 4. Just like other C-inspired programming languages, JavaScript also has the double plus and the double minus operators along with their prefix and postfix support. So you can take a variable and add plus plus after the variable or plus plus before the variable, and both of these will increment the variable. For example, we start with 0, we go to 1, and then we go to 2. And the same is true for minus minus as well. We can do example minus minus to get minus 1 or minus minus example to get minus 2. The difference between the postfix version and the prefix version becomes obvious when we try to do the same within an assignment expression. Here we have the same code written twice, but the first time we are using the postfix ++, and in the second example we are using the prefix ++. To understand the difference, focus on the terms post and pre. With post ++, the runtime returns the current value immediately, and post that we update the value of the variable. So the value that goes into the result is the original value, which is 0, and then example gets updated to the value of 1. Similarly with pre++, the value gets pre-updated, so example is immediately going to become 1, and that is what is returned into the result. And the same thing applies to the minus minus postfix and prefix operators. With postfix, the result is going to be the value before the update, and with prefix, the result is going to be the value with the minus minus pre-applied. Now it shouldn't come as a surprise that these operators only work on variables that can be mutated. For example, alpha is a let variable and therefore alpha++ is perfectly fine. However, if you just have 3 standing by itself, it's not actually a variable, so 3++ is going to result in an error. And similarly, if we have const beta, then beta is a const and therefore it cannot be reassigned, and beta++ will not be allowed. And of course, if you have TypeScript configured as we did in a previous lesson, then it'll catch these silly mistakes for you at compile time. To make code execution decisions based on a value, we need to be able to compare numbers, and of course, JavaScript comparison operators have got your back. You can compare two numbers with a less than operator, and of course, 1 is less than 3, so that's true. You can use the greater than operator. 1 is not greater than 3, and therefore that is false. There is also less than or equal to. For example, 3 is less than or equal to 3 because it is equal to 3, and that will be true. There is greater than or equal, and 4 is not greater than or equal to 5, which is actually less than 5, so therefore it will be false. And there is also strict equality. For example, 1 is equal to 1, and of course that's going to be true. And strict inequality, which is not equal, so 5 is not equal to 3, and therefore that is true. Because JavaScript numbers have a fixed bit size of 64, there are limitations on the size of integers that it can safely represent. There is a global number module that has this member called max safe integer, which represents the max safe positive value, and similarly there is a min safe integer which represents the minimum safe value. Now safe in this context refers to the fact that the value cannot be the result of a rounding error. The unsafe values are +1 away from max safe and -1 away from min safe, and what that basically means is that there is no guarantee that the result that we get at this point is not the result of a rounding error. So max safe +1, while correct, is ambiguous because +2 will give us the same value. So max safe and min safe, you are perfectly fine. Outside of that range, numbers can be represented, but there might be a chance that they might have been rounded. Now to check if there is a chance that a rounding might have occurred on the value, you can use this function called number is safe integer, and of course max safe integer is safe, but anything else outside of that range is not going to be safe. For example, +1 is not going to be safe, and similarly any other number that we write that is going to be outside that range is not going to be safe. If you go out of bounds of what values can be represented in the 64 bits, you will end with infinity, which is still a well-defined numeric value within JavaScript. As an example, if you decide that you have had enough and raise 10 to the power 1000, you will get infinity, and if you multiply it with -1, you will get -infinity. Dividing a positive number by 0 will give you infinity, and dividing a negative number by 0 will give you negative infinity. Now, as I mentioned, these are well-defined literals, so you can actually type it in yourself as well, and it is equal to itself. So infinity is equal to infinity, minus infinity is equal to minus infinity, and they work with comparison operators as well. So infinity is greater than any other positive number that you can think of, and minus infinity is smaller than any other negative number that you can think of. Now these values also exist as members of the number module. So number has positive infinity, which is of course equal to infinity, and negative infinity, which is of course equal to minus infinity. Since the origin of JavaScript lies in user interface programming, working with strings is often required, and so the interop between numbers and strings is quite well built within JavaScript. Let's first look at converting a number into a string. Now numbers have a method called toString, which can be used to convert the number into a string, and this actually gets invoked automatically when we add a number to a string, and we've seen examples of that in our string lesson. When we are working with floating point values, we might want to format it a bit further because the default toString might give us a really long string that we might not like. For a bit of formatting control, there is a function built into strings called toFixed, which takes the number of decimal points that we want to display. So if we invoke toFixed on change and pass in a value of 2, we get back a string that contains 2 decimal digits. Additionally, toFixed will also round a value, so as an example, if we invoke toFixed 1, it rounds it up to 4. Now toFixed will always try to add the required number of digits, so if we don't have any, for example 42 clearly doesn't, it will add zeros instead. Now let's talk about the opposite, where we take a string and we try to parse it into a number. JavaScript has a global function available for us called parseInt, which takes a string and tries to parse it into its integer equivalent. If the string in question has a decimal portion, that portion is completely ignored by parseInt, so 23.55, we only get back the number 23. Now if we do want to parse the value as a float, then JavaScript has another built-in function called parseFloat, which takes that string and parses it into a float, so 23.55 string gives us the numeric 23.55. Now just like we use the double bang to convert other values into true booleans, JavaScript has the unary plus operator that can be used to convert a string into their number equivalent. When I have a string that I trust is going to parse correctly, then this unary plus is normally what I would use. But what about the case when we have a string that is not going to parse correctly? For example, sugar, spice and everything nice, although excellent, is not a valid number. For these cases, JavaScript has a special numeric value called nan, which stands for not a number. Beyond parsing things that clearly cannot be a number, the nan literal also shows up in other scenarios, for example when we try to divide 0 by 0. There is a very peculiar but completely reasonable behavior observed within nans that is best explained with a simple example. Here we have two variables, first and second, which are the result of parsing two different strings. Now both of these are going to be nan, but clearly alpha and beta are not equal to each other, therefore it makes reasonable sense that first should not be equal to second. And indeed, this is the case within JavaScript. However, this does mean that a nan is not equal to a nan. This poses a slight problem because if a nan is not equal to nan, then a nan equal to nan will be false. This will actually prevent us from checking if a particular value has resulted in a nan, but fortunately JavaScript has a very nice global function called isNan that will tell you if a particular numeric value is a nan or not. And as a side note, these silly mistakes of comparing directly with a nan instead of using the isNan function are caught as a compile time error by TypeScript. In addition to literals in the decimal number system, the number data type also allows us to express our ideas in other digital bases, but make no mistake, they are still backed by the same binary 64-bit value. Consider the simple integer 32, which is of course 2 to the power 5. Representing this value in binary should be 1 followed by 5 zeros, and we can actually write that literal within JavaScript with 0b followed by the binary value. Note that this is still the same number underneath, which is 32, which is of course why perfect is equivalent to this binary literal. In addition to binary, we can do octal with 0o, and this is 40 in octal, and hexadecimal with 0x, and this is 20 in hexadecimal. Now all of these notations are case insensitive as well, so it doesn't matter if b, o or x are lowercase or uppercase. In addition to expressing ourselves in these numeric literals, we can actually take a numeric value and express it out as a string in any of these number systems. Now by default, toString will render it out in decimal, but toString actually optionally also takes in a base for the number system. For example, binary is base 2 and we get that 1 followed by 5 zeros. And similarly, octal is 8, we get 40, and hex is 16 and we get 20. And now that we know how to express these numbers as strings in different bases, we can actually parse them from the different bases as well. Now by default, parse int will parse it as a decimal. However, we can pass in a second optional argument to parse int for the base, for example, 2 for binary, 8 for octal, and 16 for hexadecimal. All of these strings in the different bases will parse to the numeric value of 32. JavaScript comes with a built-in global math module that provides a lot of utility functions and some constants that make it easier to work with numbers. For example, there is math.floor, which will get rid of the floating portion. There is math.ceil, which if there is a floating portion, it will bump up the integer value. So here 1.01 becomes 2. And then there is math.round, which will round it to the nearest integer most smartly. For example, 1.99 becomes 2. 1.01 becomes 1 and 1.5 gets rounded up to 2. And there is also math.random, which is perhaps my favorite function, and it returns a floating point starting from 0 but ending right before 1. And by combining this with multiplication and math.flow, we can actually scale it to whatever value that we want. For example, if you multiply it by 2, it is going to be in the range 0 to 1.99999, and therefore if you floor it, it is either going to be 0 or it is going to be 1. And similarly, if you want 6 distinct integers, multiply it by 6 and use math.flow to get 0 to 5. Math also has functions maths.max and maths.min. Max returns the maximum value within a set of numbers and min returns the smallest value within a set of numbers. And these functions come in quite handy. And speaking of handy, math also has some constants, for example, maths.pi, which comes in handy when you are working with circles. For example, here's the circumference of a unit circle. As you can see, there is a lot of power built into JavaScript numbers, and for most user interface programming purposes, you will be well looked after. As always, thank you for joining me, and I will see you in the next one. Objects are one of the two key forms of containers for other data types that we have within JavaScript. A core part of being a successful JavaScript engineer is having mastery of how to use objects effectively, and this tutorial is designed to do exactly that, so let's go. At its core, JavaScript objects are collections of properties where each property is a key value pair separated by commas. Here we have a simple object specified by an object literal that contains a name property with the value of the string magic Mike and a gender property with the value of the string male. We can access the properties of an object by using the dot notation. For example, Channing.name will give us magic Mike, and we can even modify the values by doing an assignment statement. For example, assigning Channing.name to the string Tatum will make Channing.name equal to that string. Now, if we assign to a property that isn't a part of the object right now, magically that does get added as a property of the object. So now Channing has a new property with the key skill and a value of the string dance. Now we've actually been using string values, but you can actually use a value of any data type within JavaScript. For example, we can create a new property born with the value 1980, and objects can even have properties that are objects themselves. For example, now the key planet has the value of an object with name Earth. To access the properties of an object contained within an object, you simply use the dot notation as many times as you need. For example, to get the value of Earth's string, we need to go from Channing to planet to the planet's name. Now, after making all of these modifications, just as a quick recap, this is the current object that is contained within the Channing variable. If we try to access a property that doesn't exist on the object, for example, here we are trying to access citizenship, the JavaScript runtime returns the special value that we've seen a few times before called undefined. Something that I often find beginners struggling with is the difference between an immutable reference and the mutable nature of an object. Objects within JavaScript are mutable references. What that means is that if we have a variable pointing to an object, in addition to using its keys to read the values, we can actually write to the key as well. So if we modify the key name to point to a new string Tatum, the object is going to get mutated. Now this is independent of the only guarantee that is offered by const, which is that with a const variable, you cannot do a reassignment. If the value that is contained by the const is mutable, you can of course mutate it as we have done right now. The primitives that we've looked at within JavaScript are all immutable. So if we have a const person pointing to a string, even though there are methods on the string to return new modified strings, the original string is always left unchanged. And since with the const an assignment is not allowed, it is always going to be true that person is going to be the string Channing Tatum. And as a side note, the silly mistake of trying to reassign a const to a new value is always caught by TypeScript at compile time. Keys in JavaScript objects are always strings. Even though they look like identifiers, we can actually use any string that we like, and there is a special syntax to allow you to create, read, and write arbitrary string keys. Before we begin, let's just create a very simple variable called diet, which points to the string food. We create an object stored in a variable called alien with the property having the key name and the value string Martian. In addition to having identifiers as keys, we can actually even use a string as a key. For example, have age as a key. Now this is going to be exactly the same as having an identifier age, so we don't necessarily need to quote age. But the advantage of using quotes is that we can actually use any string over here, something that might not even be a valid identifier. For example, current status with a dash in between is not a valid identifier, but we can create it as a key by using quotes. If we want to take it to the next level, we can actually even use square brackets around our keys. And this actually allows us to use any JavaScript expression within the key name, and the final key will actually be the evaluation of that expression. For example, in this particular case, it is going to be the same as a key with the name home planet. The ability to use expressions means that we can even generate key names from other variables. For example, here we are generating the key name favorite food by using the diet variable. Now, if you have a valid identifier for a key, we can use it with the standard dot as we have been doing till right now. But JavaScript objects also support the index notation that allows you to pass in a string expression. For example, for the name property, we can pass in the string name using the square bracket index notation. And of course, the advantage of using the bracketed index notation is that we can pass in any string that we like, for example, strings with dashes inside of them, or even calculate the string based on simple JavaScript expressions. For example, here we are accessing favorite food, which of course we previously initialized to pizza. As we mentioned in previous lessons, the interop between string and number in JavaScript is excellent, and in fact it is so seamless that you can safely assume numbers as keys in objects even though they are still strings underneath. To demonstrate that, consider a very simple object called digits that has some keys as numbers and other keys as identifiers. Now we already know that using DOS as an identifier with the dot notation or using the square bracketed string index lookup, it is going to be the same property. With number keys, we cannot actually use the dot notation because of course numbers aren't valid identifiers within JavaScript. However, we can use them with the square bracket lookup, and it doesn't really matter if we pass in the number or the string version of the number, they are going to be exactly the same. And just like with reading, where we can use a number or a string version of the number, we can actually write with a number or a string version as well, and the same underlying property is the one that gets modified. Unlike primitives like number, string, and boolean, equality on objects works by reference and not by value. So even though two objects might be completely equivalent structurally, unless they point to the same reference, they will not be equal. Consider two simple variables, person A and person B, pointing to two different JavaScript objects, which are both structurally equivalent, that is, they both have the name property pointing to the string John Doe. However, whenever we use an object literal, we are creating a new distinct object as far as JavaScript is concerned, so person A will not be strictly equal to person B. Of course, person A will be equal to person A and person B will be equal to person B. Now, if we create a new variable called person C and point it to the same object that is contained within person A, then in that particular case, person C will be equal to person A because they are the same object literal. And to further drive this point home, if we modify a property on person C, because person A is a reference to the same object, when we read the name for person A, we see the updated value of Jane Doe. Modern JavaScript comes with some pretty neat shorthand syntax that can help simplify how we create objects. Let's first focus on additional syntax for creating objects or structuring objects, and for that purpose we have three simple variables, make, model, and color, and our objective is to create a car with all of these members. Now, of course, we can do it the way that we have been doing with key value pairs. As an example, the key make points to the value of the variable make and so on. Now, if the identifier used for the key and the value are exactly the same, we can actually use a shorthand syntax where we do not need to specify the value, and it's automatically assume that the key is going to be make and the value is going to be whatever is contained by the identifier make. So the result of creating an object in either of these two ways is exactly the same. Another nice feature offered for creating objects within JavaScript is the spread operator. Consider a simple point 2D that has members x and y, and we want to create a point 3D that has the same x and y members along with the additional z member initialized to 0. Now we could totally list these members out and copy them over, but there is a shorter syntax known as the spread operator which can be used to spread the key and the values of one object into another. So these two statements are equivalent. Point 3D will have all of the properties of point 2D, which is x and y, along with this new property z of 0. One thing to be aware of with the spread operator is that order is important. So here we have an object task pending that has title, when, and is completed, and we want to create a new version of this object with is completed set to true. Now the right way to create this new object would be to take all of the properties of task pending, spread them in, and then overwrite the is completed property to be the value true. If we were to reverse the order, that is have is completed first and then replace all of the properties from task pending, then this is completed is actually going to get completely ignored, as the task pending version of is completed false is what's going to win. As a side note, silly mistakes like this are caught by TypeScript, and here TypeScript is complaining that there is no point in providing this property as it will always get replaced by the task pending version. Now, just like JavaScript has fancy syntax for putting stuff into objects, that is structuring, it has fancy syntax options for pulling stuff out of objects as well, which in programming language terms is called destructuring. Consider a simple object containing x, y, and z members. Now, if we wanted to pull out the members x and y from this object, we can do that by using point.x and point.y, but as you can see, there is a repetition of point dot between these two variables. We can actually use the shorthand destructuring syntax offered by JavaScript to pull out the members x and y into their new variables by using a pattern very similar to structuring on the left-hand side of the equals operator. These two statements are completely equivalent, and as you can see, the destructuring version is much nicer. Now within destructuring, there is a long form syntax as well that allows you to rename the value that you are reading. For example, here we are reading the values x, y, and z from point and then renaming them into local variables called point x, point y, and point z. Now just like there is a spread operator for structuring, there is a spread operator with the triple dots for destructuring as well. What this does is it takes all of the properties that haven't already been destructured and puts them into an object with a variable name of our choice. Here we are saying that take out x and put it into the variable x, and for everything else, y and z, put them into a variable called rest. And if you want to really impress your colleagues, you can actually even use destructuring within destructuring. To demo this, we have a simple center object that has a name property and a location property, which itself is an object containing members x, y, and z. As we already know, we can pull out the member location from center and give it a local variable name called lock. What we can even do at this point is that instead of using a local variable called lock, we can apply destructuring again to destructure that object and pull out any of its members. For example, here we are pulling out the member x from location. Even though JavaScript's type of operator does work on objects, it doesn't provide enough clues to disambiguate between different structures. So I definitely recommend using a discriminating field commonly called type. Here we have two simple objects. One is of a type point and the other is of a type person. Now, as far as JavaScript is concerned, these are both JavaScript objects, and with the type of operator on an object, JavaScript runtime returns the string object. Clearly, this is not enough information to discriminate between the different structures, so the recommendation here is to add another property to the individual objects. For example, here we are adding a property called type, which is going to be point for points and person for persons, and this will actually allow us to easily determine what kind of structure might be present within the different objects. Now, this isn't really a JavaScript feature, this is mostly just clever programming, but this is a pattern that is used commonly enough that it is worth knowing as a professional developer. JavaScript comes with delete and in operators that can be used to effectively manage and test for presence of properties on objects. For example, here we have a simple bird object that has a property type with the value chicken. Now, as we know, we can add additional properties to the bird at any point. For example, we can set bird.name to live2, and now the bird will have two properties, type chicken and name live2. But what about removing properties from an object? Now, you might think that you can just set that property to the value undefined and that property will go away, but that will not be the case. The bird will still have the two properties, it's just that the second property value will be turned to undefined. And there is an operator within JavaScript called in, which can be used to test the presence of a property on an object, and of course, bird still has the name property present. The proper way to get rid of a property from an object is to actually use another JavaScript operator called delete. Here we have completely deleted the name property from bird, and now of course when we log out bird, it has only one property with the key type and a value chicken. With this property deleted, name in bird will return false, and of course type still exists in bird and we can use that in an if condition. Clearly, there is a lot of power and sweet syntax baked into modern JavaScript objects, and honestly that makes working with data quite enjoyable. As always, thank you for joining me and I will see you in the next one. Within JavaScript, functions are the fundamental way of defining reusable code blocks. We've been using functions all along this course, whether it was console.log or the various methods that we looked at when working within the data types. So in this tutorial, we will kick it up a notch and take a deeper look at how you can create your own functions and lots of their technical features. Even if you've used JavaScript for a while, I can guarantee that you will learn something new in this tutorial, so let's go. Let's first discuss the main objective of functions, and that is code reuse. Consider we have a value and a % discount and we want to calculate the discounted value. We can do that quite easily with a JavaScript expression, but if we want to do it again for a different value, we will have to write that expression again, and this sort of code is not very maintainable. And this is where functions come in. We create a utility called calculate discounted value that takes a value and a % discount, calculates the result and returns that from the function. And now whenever we need the discounted value, we simply invoke the calculate discounted value function and it gives us the result that we are looking for. Let's take a deeper look and discuss the various JavaScript syntax elements that are at play right now. First up, we have the function declaration. This consists of the function keyword, followed by an identifier for the function name, followed by the various parameters that the function can accept, followed by a function body that consists of various statements with an optional return statement to return a value back to the caller. To use the function, we make a function call. There are two function calls over here, and the structure of the function call consists of the function identifier followed by brackets where we pass in the different arguments that get assigned to the parameters within the function. A curious fact about function declarations within JavaScript is that they get hoisted, which means they can be used. For example, we can call them or invoke them before they have been declared. And just like other JavaScript data types, the type of operator is supported for functions as well, and it returns the literal string function. JavaScript functions are fairly resilient and they will actually work without throwing an error, even in the presence of possible coding mistakes. So even though this function only accepts two parameters, we can actually pass in three arguments, and what will happen in this particular case is that the third argument will get unused, which is pretty much the same as just putting a random string somewhere in our code. It's not doing any harm, but it's not doing any good either. What is more dangerous is that we might potentially forget to pass in a required parameter. In this particular case, we have forgotten to pass in a % discount, and the JavaScript runtime will actually pass in that magical value that we've looked at before called undefined. Additionally, trying to do math between a number and an undefined value will give us another thing that we've looked at before in our number lesson, which is the NaN special type. The obvious guidance here is that don't pass in more or less arguments than you need, because the JavaScript runtime may or may not throw you a useful error. Return statements in JavaScript functions are optional, which means that not only can we use functions for calculating results, but we can also use them for carrying out tasks where we do not need a return value. As an example, consider a simple sayHi function whose sole purpose is to log a full name to the console. And of course, if you pass in an object that has the first name and the last name, it will calculate the full name and log that out as you would expect. What is interesting is that functions always return a result within JavaScript. So we can actually store that result and log it out. And because this function does not have a return statement, JavaScript returns that special value undefined. Now this is perfectly fine as we do not expect this function to return a value. However, it is easy to make a programming mistake where you forget the return statement when you intended one, in which particular case you might end up with an undefined. So obviously, don't forget your return statement if you need one. Modern JavaScript offers a special syntax to take a single array argument and turn it into multiple parameters that get passed into the function. You might recall the math.max function from our number lesson, which returns the maximum value that exists between the different arguments. Arrays in JavaScript are a simple collection of items separated by commas within square brackets, and here we have an array of 3 items. Now if you wanted to pass these individual items from the numbers array to math.max, we would have to look up the individual items. We would have to look up item 0, then item 1, and then item 2 as different arguments that we send to math.max. And this is where spread arguments come in. We can actually take an array and use the triple dot to spread those array members as different arguments that get passed to the function. Just to get a bit more practice with spread arguments, consider a simple example function that takes 2 values, a and b, and we have a message array that consists of 2 strings. If you want to pass those 2 strings into the example, we can take that array and spread it into the different arguments. Within JavaScript, functions are first class. This is a programming language concept, and what this means is that functions can be treated like other data types and moved around as variables and even passed into other functions, which are called higher order functions. We can actually take a full function declaration and assign it to a variable, but this will actually not be a function declaration as we saw before, and instead, this will be what is known as a function expression. What this means is that the identifier for the function, which is example, is not going to become available in this scope. And our only access to this expression is where we assigned it to. Here we assigned it to hello, and we can use that to invoke the function. Now obviously, since the function name does not become exposed, it is common to use function expressions without a name, and these are known as anonymous function expressions. Now when we are using functions as variables, they are going to follow the rules of the variable. For example, here this is a let variable, which means that we cannot use it before it has been assigned. Another common use of a function expression is in a pattern what is known as an IFI or an immediately invoked function expression. Consider a simple function example that we want to invoke immediately. If this is the only time we invoke this function, then we might as well just use a function expression and wrap it up with parentheses and invoke it immediately. And now that we know what function expressions are, I think it makes obvious sense why this is called an immediately invoked function expression. Now just like we can assign a function to a variable, we can even pass it in as an argument to another function. For example, here the runTwice function takes a callback function and invokes it twice. So when we call runTwice, we can pass in a function that logs a message hello world, and then runTwice will run it twice, giving us 2 console.log messages. Now functions that take other functions as parameters in programming language terms are called higher order functions. And they show up in JavaScript all the time. For example, there is a built-in function called setTimeout, which takes a callback parameter and a duration in milliseconds, after which that callback will be invoked. So this code will log a second has passed after 1 second, and we can make another call after 2 seconds and log out 2 seconds have passed. Now of course, if we run this code, we see a second has passed, and after 2 seconds, 2 seconds have passed. Beyond setTimeout, we will look at lots of functions that are built into JavaScript that work on top of callbacks. Inspired by functional programming, Modern JS offers a neat syntax for defining functions called arrow function expressions. Consider a simple sum variable where we want to assign it a function that takes 2 arguments, a and b, and returns the sum of those values. Now of course, we can use a function expression and that works fine, but there is a newer syntax called arrow function expressions which allow you to shorten the amount of code that you need to write. Syntactically, you drop the function keyword, provide your parameters, use the equals and the greater than sign to create what is lovingly called an arrow, followed by the function body. Now if your function body consists of a single return statement, you can shorten it even further to remove the body curly braces and only use the expression that you were previously using in the return statement. And if you only have a single parameter within your function, for example, add10 only has a single x parameter, then you do not even need the parentheses around that parameter. JS functions offer a special parameter syntax that allows it to accept multiple passed-in arguments as a single array, and these are known as REST parameters. For example, consider a simple log function that logs the value of 2 passed-in parameters. Now, of course, this works perfectly fine when we pass in the required number of arguments, but it doesn't work as well if we pass in only one argument. As we know, we are going to get undefined, and it completely ignores any additional arguments that we might pass in. For example, we are passing in 1, 2, 3, and 3 is completely ignored. The original console.log method that we are wrapping actually works much better. It works with one argument, it works with 3 arguments. It works perfectly fine irrespective of how many arguments we pass in. And this is where REST parameters come in. They allow you to take a variable number of arguments and convert them into a single array parameter. So now if we call a log with 1, 2, 3, we get all of these 3 arguments converted into a single array, and as you can see, that is what gets logged out. One thing to note is that REST parameters do come in as a single array, but what about that objective of making it similar to console.log, where it would log out 3 different items? To do that, we would need to invoke console.log with multiple arguments, and we already know how to do that because we just looked at spread arguments. So we can take this single array and spread it into multiple arguments when we are calling console.log. Now, one more thing to be aware of with REST parameters is that it must be the last parameter within a function definition. So if we use triple dots before any other parameter, we would actually get a syntax error. Now, of course, we can mix REST parameters with other parameters as long as the REST parameter is the last one. Here we have a nice prefix log function where the first argument is a prefix that is going to be pretty printed, followed by the REST parameters. A welcome modern syntax offered by JavaScript functions is the ability to define default parameters. Consider a simple sum function that is designed to sum 3 numbers. Now, of course, if we pass in 1, 2, and 3, it is going to provide the sum, which is 6. But if we forget one of the arguments, we're going to get back that thing that we looked at before called not a number. This is because we just tried to do math on an undefined. We can actually provide a default value for a parameter by adding an assignment expression after the parameter name. So this still works if all those 3 parameters are provided. So 1, 2, 3, sum it up, we get 6. But we can also provide only a few of the arguments. For example, only provide 1 and 2, and we get back the sum 3 because C has defaulted to 0. One thing to know about default parameters is that they basically work on top of undefined, so we can actually use them in any position, and if you want to use the default value for any of the parameters, simply pass in undefined for that particular argument. So here, since we are passing undefined for B, B is going to default to 0, and 1 plus 0 plus 3 equals 4. If you've worked with other programming languages, you might be familiar with the concept of arguments being passed by reference versus passed by value. Let's take a look at what this means and how it applies to JavaScript. In JavaScript, arguments are always passed by value. What this means is that assigning the parameter to a new value does not impact the original argument. And this is true for all types. For example, here we have a primitive number, and when that gets passed in, we try to assign the parameter a new value, but the original primitive still stays at a value of 3. And we can verify that the same also works if we were to accept an object. For example, here we have an object with the property name of value John. We pass it into the function, and the function tries to do a reassignment, but the original object, of course, remains unchanged. Some programming languages have a concept of reference parameters that allow such reassignment. That is not something that is supported by JavaScript. A great mental model to have is that the conversion from argument to parameter is the same as assigning a value to a variable. Consider that object again with the property name of value John. We can assign this object to another variable, for example person, and right now mutations to person would actually mutate the original object. But if we reassign person to a completely different object, it's going to become completely disconnected from the original object, which of course means that the original object.name will continue to be John. And this assignment expression where person equal to object is exactly what happens when we pass an argument to a parameter. This means that if we make the parameter point to something else, then that has no impact on the original argument. Now, if we take that object that person is pointing to and modify some of its properties, for example, modify the name, then of course, since person is still pointing to that original object is exactly what is going to get mutated. And since argument to function parameter is nothing more than an assignment, if we take that object and mutate it, the original referenced object is exactly what's going to get mutated. Needless to say, mutating past and values in JavaScript is normally frowned upon, as these side effects can be quite hard to reason about. So let's talk a bit about pure functions. Consider a simple global variable and an increment function which modifies that global count variable. Now, of course, this does work. We can initialize count to 0, increment it impurely, and now count is incremented. But that's not going to be particularly maintainable. There is no indication reading this code that count is going to get changed. A much better implementation is something that takes an input and returns the result. So here increments depends upon nothing other than its parameters, and it does not modify the parameter or any other global variable for that matter. Now when we use increment, we are responsible for making sure that we store the result as we see appropriate, and for anyone else that reviews our code, it will be very clear that the count is going to get changed. Just like we can use destructuring in variable assignment, we can use destructuring in function parameters as well, because after all, argument to parameter passing is sort of like a variable assignment. Consider a very simple ranged function that takes a value min and max and makes sure that the value does not exceed the boundaries of min and max. Now, of course, this does work perfectly fine. For example, we can pass in a value of 100, a min of 0 and a max of 10, and it clamps it down to the value of 10. But if someone were to review this code by itself, it would be very hard to understand which one is the value, which one is the min, and which one is the max. So a better option is to actually pass in a single object where the different keys identify the nature of the properties. And now that a single object is going to get passed in, instead of using a single identifier, we can destructure it into its members, which of course are value, min, and max. From a runtime perspective, again, this is exactly like doing an assignment. So just like within an assignment, we can do destructuring from an argument to a parameter. One of the most powerful features of JavaScript functions, and something that was critical for things like Node.js, is the JavaScript support for closures. It should come as no surprise that when we have a variable outside of the function, we can access that variable from within that function. So over here, example is incrementing alpha, and of course, once we invoke example, alpha is going to be incremented from 0 to 1. A closure is nothing more than the fact that a variable in an outer scope has been closed over and bound to a function. What is interesting is that this binding continues to exist even after the outer scope has returned. So here we have a function called counter that has a local variable called count, and then it has an inner function that of course can access this outer variable called count. Now even after the counter function will return, this particular instance of the count variable will continue to be bound to this particular instance of the function that gets returned. And we can prove this with a simple example by creating an increment function which is returned from counter, and then as we invoke it again and again, we get back constantly incrementing versions of that original count variable. We can combine JavaScript support for first-class functions and its support for closures to create a very popular design pattern called factory functions. Because functions are first class within JavaScript, we can create objects that contain functions. And because JavaScript supports closures, these functions will have access to variables that only exist within the containing function. So here our createCounter function creates an object that has increment, decrement, value, and reset functions, and all of these functions operate on top of a local count variable. So when we create a counter, we get to provide an initial value, and of course if we don't provide one, it defaults to 0, and then our only access to that variable is via these controlled methods that are a part of the returned object. As you can see, JavaScript functions by themselves allowed people to create some pretty well-structured modules even before the support for native classes was added. When we are defining functions within objects, which in object-oriented programming are called object methods, JavaScript provides an additional shorthand syntax called object method definition. As an example, consider an object cat-dog that has a method called speak, which is a function that logs two simple statements. Here we are using the key value syntax of objects that we have looked at before, where speak is the key and the value is the function. The object method definition syntax gets rid of that colon, gets rid of the function keyword, and provides a much tighter experience. There is no functional difference between the two. If the body of the function is a simple expression, I would use an arrow function, otherwise I would use the object method definition. Defining functions as a part of objects also unlocks two additional types of functions, which are getters and setters, which look like functions when we define them, but behave more like standard object properties when we try to use them. Consider the example where we want to create an object that has a single property called value, but we want to make sure that whenever the value gets set, it stays within a range of a minimum and a maximum. We can do that by providing our own custom setters and getters for the value property. Instead of defining a property like you normally would with the colon, we use a modified syntax of an object method definition where we precede that by either the get keyword or the set keyword. Let's discuss the behavior of these getters and setters a bit more by first creating an instance of this object. We use these just like normal properties and not really methods. For example, we can read the result by simply range.value. This will internally invoke that function, but for consumers, it feels like just another property. We can also assign a new value to this property, and internally it will invoke the function for the setter and pass in the new value. But again, in terms of consumers, it feels like just another property. This ensures that the value can never escape the range that we originally provided, which is 0 to 10. And as you can see, the updated value goes to 10 instead of going to 15. In case you were wondering, you can create recursive functions in JavaScript, that is, functions which in their body make a direct or an indirect call back to themselves. And a classic example of a recursive function in computer science is the Fibonacci sequence that follows the definition that Fibonacci of 0 is 0 and Fibonacci of 1 is 1. And then for all other positive integers, the Fibonacci for n is the Fibonacci of n minus 1 plus n minus 2. So let's create a function that follows this specification. It takes an integer n, and if it is 0, we return 0, and if it is 1, we return 1. Otherwise, we again invoke Fibonacci with n minus 1, and then add it to another invocation of Fibonacci with n minus 2. So as an example for the curious, the 11th Fibonacci number should be 89, and of course, when we run this, that is exactly what we get. We've covered lots of features of JavaScript functions, and trust me when I say that as a professional developer, you will interact with functions so often that it's good to be aware of all the tools that you have available in the JavaScript tool belt. As always, thank you for joining me, and I will see you in the next one. After object literals, JavaScript arrays are the second main data structure that we use to create a collection of values. An array can be declared with square brackets containing the individual values separated by a comma. Here we have an array that consists of two items, both are of type string, the first one being Jane and the second one being Pete. JavaScript arrays come with the length property that indicates the number of items that are present. For example, here we have two people, so people.length is going to be the numeric 2. We can access the individual items within the array using a square bracket notation and passing in the index for the element that we want to access. Like all good programming languages, JavaScript arrays are 0 indexed, which means the first element is 0 and the second element is index 1. Now if you pass in an index that is actually not present within the array, the JavaScript runtimes gives us that special value that we've talked about before called undefined. Now just like we can read a value using the index notation, we can write a value to a particular index as well by using an assignment expression. So here we are replacing the first element, which is the element at 0 index, from Jane to Kim, and now if you log out people again, you can see that it is now updated. We started off with an array that contained 2 items, but of course we can create arrays that have no items, have a single item, or as many items as we need. JavaScript arrays are completely untyped and they don't really care about what values you put inside of them. For example, here is an array that contains a string and an object and even a nested array. We can access the individual items as you would expect. For example, things 0 is gold, and we can continue our selection syntax based on the element that is present at that index. For example, the item at index 1 is an object and therefore we can access its properties using the dot notation. Similarly, the item at index 2 is an array, which means that we can continue selecting the individual items of the subarray by using further index selections. And of course, in addition to reading, we can use the assignment expression as well. For example, here we are replacing the string house with the string home. Now technically within JavaScript, an array is an object. So as an example, if we have an array and we use the type of operator, we get back the literal string object. Now this poses a bit of a problem because this is exactly what is returned for all objects. Fortunately, modern JavaScript has a function built in as a part of the array module called isArray, which will return true if the variable is an array, and for other objects it will return false. Arrays provide methods push, pop, shift, and unshift to add and remove individual tail and head items, and this allows us to build stacks and queues. So let's take a look at how they work and get some understanding of their runtime complexity. We start off with an array that has 2 items, first and second, and we can push additional items at the end of the array using the built-in push method. This gives us the array containing first, second, third, and fourth. We can remove items from the end of the array by using the corresponding pop method. So we get fourth and then third, and now the original array contains just the strings first and second. If you continue to pop, once we run out of the elements, it will start to return undefined. The time complexity for array methods is based upon how many index need to be changed. So for push and pop, only one index needs to be changed, which is the last element, and therefore the time complexity is O of 1 or constant time. Now JavaScript methods also provide the opportunity to modify the start of the array. For example, we start with an array consisting of economy and deal, and we can push to the start using unshift, business, and then VIP to give us the array VIP business economy deal. JavaScript also provides methods to remove an element from the start of the array called shift, and if we remove the first item, it would give us VIP, then we would get business, leaving just economy and deal within the array. Now just like pop, if we continue to shift till we run out of elements, it will start to give us undefined. For shift and unshift, n indexes need to be changed as all the items need to be either shifted right for unshift or shifted left for shift, and therefore the time complexity for these functions is O of n or linear time. So let's take a look at how we can implement stacks and queues in JavaScript and the impact of these operations. First up, let's implement a last in first out data structure, also called a stack, and we can do this quite easily by using the built-in push method to push items into the array and then pop the individual items from the end of the array so that they come out in last in first out order. As we've discussed, both push and pop are O of 1, so this is actually quite a nice performing stack. Now let's talk about how we can create a first in first out data structure, also called a queue. For this, we would still use push to push the items at the end of the array because it performs quite nicely. However, since we need them out in the first in first out fashion, we will shift them out from the front of the array using shift. However, as we've discussed, shift does perform in linear time, so this is not ideal. However, when you are looking for a convenient queue, you can use the built-in JavaScript array for that purpose. JavaScript offers special syntax for destructuring arrays, that is, taking the members of an array and distributing them into different variables. For example, here we have an array consisting of 3 items, gold, iron, and copper, and we can get the first 2 items and put them into their individual variables by using the destructuring syntax, which looks very similar to the structuring or creation syntax, except that it is on the other side of the equal sign. This syntax also allows us to skip over an item by using 2 commas consecutively. For example, here we are skipping over the second member, which is iron. We can also use rest elements to grab all the remaining items and put them into their own array. For example, here the first item gold is put into uno, and the other 2 items are put into their own array in the resto variable. One thing to be aware of with rest elements is that they must be the last element in the destructuring. If you try to use them before that, we will get an error that it should be the last one. Now we can destructure more elements than they actually are in the array. For example, here we don't have 4 elements, and yet we try to destructure the 4th into quatre, and of course the JavaScript runtime in this particular case gives us undefined. Now with destructuring, you can also provide default values, and they will kick in whenever the value would have been undefined otherwise. For example, in this particular case, since there is no 4th element, it would have been undefined, and therefore it is going to default to silver. The modern spread operator that works with JavaScript object literals is also supported for JavaScript arrays. The spread operator can be used to spread the items of one array into another one. For example, here we have some white minerals, and then we have some more minerals within which we want to use all the white minerals, and we can spread them in with the triple dot spread operator. You can actually use the spread operator in any portion of the array. For example, here we are putting silver and platinum between gold and copper, and you can even use it multiple times. For example, starting with iron, we are spreading in the white minerals followed by yellow minerals to get iron, silver, platinum, gold, and copper. The spread operator is actually quite useful, and it has a number of use cases. For example, it is the recommended modern syntax for combining 2 arrays. So if we want to combine the white and the yellow minerals, we can spread them both into a new combined array. Now you might recall that push and shift causes a mutation of the original array. So if you want to add an item at the end or the start of an array without mutating the original, you can spread the original into a new array at the required place. Spread can also be used for the simple task of creating a copy of an array to prevent accidental mutations to the original. For example, here we create a copy of the white minerals, and when we push iron into this copy, the original white minerals remain unchanged. Arrays in JavaScript come with helpful methods that allow us to iterate over all the items in the array, map them to new items, and even filter them individually. When you want to carry out the same task for all of the items in the array, the built-in for each method saves you from having to write a full for loop. For example, if you want to log out all of the prices, we can use products.forEach, and then for each product, use it within a function to log out the product.price. The callbacks for all of these iteration methods also take a second optional argument called index, which is the index of the element that we are currently looking at. So for Apple, it will be 0, and for orange, it will be 1, and so on. And this can actually become really useful if you want to do any sibling analysis beyond the current item. Very similar to the for each method is the built-in map method, which is inspired by functional programming. Just like for each, map also gets passed in the individual items and its index, but unlike for each, the whole map function returns a new array that contains the results from the individual callbacks. So here within the callback for map, we are returning a new object that consists of all of the properties of person along with a new property called full name, which is calculated based on the person first name followed by the person last name. So for each member of people with full name, we will have an object that has a first name, last name, as well as a full name. And of course, you can see the full name being logged to the console. Another iteration method that is built into arrays is filter, which can be used to filter only the items that match a particular criteria. For example, from this numbers array, we can create separate arrays just for the evens and the odds. To create these new arrays, we use the filter method, and within the callback, we only return true if the number is even, or only return true if the number is odd. Now, of course, based on the input array, the only even numbers are 50 and 14, and the only odd numbers are 1773, 19, and 59. It is worth pointing out that in programming lingo, functions that return a boolean based on a passed-in argument are called a predicate. Therefore, the two functions that we are passing to filter are predicates for even and odd numbers. A common task with arrays is to find an item that matches our requirement, and JavaScript provides some neat methods for this purpose. For example, consider an array of people with Percy, Wally, and Harry, and we have the age-old task of finding Wally. Arrays provide a find method that take a predicate, and if this is the item that you are looking for, you simply return true. In our particular case, we want to return true if person.name is equal to Wally, and based on this example, the JavaScript runtime will return the object that contains the name Wally, born 1987. Now, if the item that we are looking for is not found, for example, there is no person with the name Jenny, then the JavaScript runtime will return that value that we've looked at 100 times called undefined. Now, this poses a bit of a problem when the item that we are looking for is in itself undefined. For example, if we try to find undefined within this array, we get back undefined, but we can't be sure if we have actually found it, because if we search for 4 as well as an example, we would still get undefined. And in this particular case, of course, it is because 4 is not found. So there is an alternative method called findIndex, which returns the index of the found item. And there is no ambiguity here, because if the item is not found, it returns -1, and -1 is not a valid array index. Another use case of the findIndex function is when you want to use the returned index to look at some of the item's siblings. For example, here we can see that the item before undefined has the value 3. Sometimes you want to take a smaller subsection like a slice of an array as the new array, and for that we have the built-in slice method. Consider a simple array consisting of animals: ant, bison, camel, duck, elephant, and we want to get everything starting at index 2. We can use animals.slice to get back those items camel, duck, and elephant. We can also pass in a second argument to slice to provide the index from where we want to start excluding. For example, here we want everything starting at index 2 but before the index 4. And if you want to start from the beginning but terminate before a different value, then pass in 0 for the starting index, and of course provide the second argument where you want to terminate. Here we are grabbing only the first two items, ant and bison. As a matter of fact, you can actually call slice without any arguments, simply to create a copy of the array. One thing to note is that the returned array from slice is always a copy and not a reference. As an example, let's take a slice consisting of one element. If you push another element into this sliced array, the original array will remain unmodified. The cat is not a part of the original animals. There are some neat methods built into JavaScript arrays that allow us to deduce some collective facts about all of the members of the array. Consider the array consisting of products, some of which are cheap, for example, Apple is only 50, and some of them are really expensive, for example, saffron is 2000. For our example, the definition of expensive is anything that is greater than 1000, so we have this predicate that determines if a product's price is going to be greater than that value. Arrays have a method called sum, which take a predicate function and determine if some of the items within the array match the predicate. If any of the items return true for the passed-in predicate, the sum function resolves to the value true. And it pretty much reads like standard English. For example, here we can say that for the products, if something is expensive, then is some product expensive should be true. Similar to sum, there is another method called every, which basically makes sure that the returned value is going to be true for all of the predicates, and if it is, then every is going to resolve to true, otherwise it is going to resolve to false. You could pretty much read this as standard English as well, thinking that for the products, is everything expensive? In this particular case, it isn't, which is why it resolves to false. Now, even though we isolated our predicate into its own little function, you don't actually have to do that. You can just pass it inline. For example, is some product cheap? You could just check if any of the products are less than 100. And of course, Apple is, which is why this will resolve to true. And similarly, we can do that with every as well. Is everything less than 100? No, it is not, which is why it resolves to false. One of the most powerful functions built into JavaScript and the bread and butter of functional programming is array reduce. The best way to understand array reduce is with a simple example. So consider this array consisting of 5 numbers 1, 2, 3, 4, 5, and your mission, should you choose to accept it, is to find the sum for all these numbers. Fundamentally, we can do that by starting a sum with a value of 0, then adding 1, then adding 2, and so on. And that is exactly what we can do with the simple invocation of array reduce. It takes 2 arguments. The first is a reduction function, and the second is an initial value for the accumulator. Like we said, we start with an initial sum of 0, which is the accumulator, and then for each iteration, we get past the accumulator as well as the current item we are looking at, and we simply return the sum of the accumulator combined with the current value. So in the next iteration, we get an updated accumulator value, and the process continues till we run out of items. No surprise, the sum of 1, 2, 3, 4, 5 is 15, which is what we get returned as the final result. Now I want to point out that it is conventional to call the accumulator variable the name of the final value that you are trying to accumulate. For example, here we are trying to accumulate the sum, so that is what we would call that parameter. Now, even though we used a simple number for this particular accumulator, you can actually use any data type that you want. For example, here we have the accumulator as a simple object consisting of 2 members, even count and odd count, both initialized to 0. Our reduction function in this particular case checks if the current item is even, and if it is, it increments the even count, otherwise it increments the odd count. Since our original array 1, 2, 3, 4, 5 consists of 2 even numbers 2 and 4 and 3 odd numbers 1, 3 and 5, that is the answer that we expect, and no surprise, when we log out the final results, that is the answer that we get. Something to be aware of is that certain JavaScript methods are mutating, so in order to use them safely and in a pure functional fashion, you need to create a copy of the array. One example is the built-in reverse method. Consider a simple array consisting of alpha, beta, and gamma, and we can invoke the reverse function to reverse the order. So simple reverse is now going to be gamma, beta, and alpha. But what you might not expect is that the reverse function is mutating. So the original simple array is going to be changed as well. It is now going to contain the same reversed order of items, that is gamma, beta, and alpha. Now the fix is quite simple. We first need to create a copy of the array before we invoke reverse. And we already know how to create a copy by using the spread operator. So we spread the better into a new array before invoking reverse. And now the reversed copy is going to be gamma, beta, and alpha, but the original better array is going to remain unchanged. JavaScript provides a built-in method for sorting arrays, and it does it in nlog n time, which is the ideal case for comparison-based sorting. But one thing to be aware of is that if you don't provide this function with a callback, your result might not match what you expected. Consider a simple array consisting of 2 strings, hello and fam. Now if we sort this, we get back what you would sort of expect, which is fam first because f comes before h. Now let's try the sort example again, but this time with the number array consisting of numbers 1, 3, and 22. Now you would expect the sorted result to be in the same ascending order, that is 1, 3, and then 22, but what we will actually get is 1, 22, and then 3. Now the reason for this is that the default comparer internally to sort uses string Unicode code points. So it works fine if you have strings, they come out in ascending string order, but not good if you have other data types like numbers, because this is essentially the same as sorting the strings 1, 3, and 22, and alphabetically 2 comes before 3, so we get 1, 22, and then 3. Fortunately, the sort method takes a comparer function, so let's try this example again, but this time pass in our own custom comparer, which basically checks the difference between the two values that we are comparing. And if A is going to be bigger than B, then we are going to return a positive number. If they are going to be equal, we are going to return 0. And if B is going to be bigger than A, then we are going to return a negative number. And this returning of negative, 0 and positive values to determine if the first item is smaller, equal, or bigger than the second is how the comparer function works. So now we get the correctly sorted array, which is 1, 3, and 22. Now, if you want to sort in descending order instead of the default ascending order, my recommendation is to simply replace the order of the parameters, so put B before A, and this provides a nice visual hint for the next person that you are going in descending order. One common mistake that beginners make when working with JavaScript is unexpectedly using empty arrays that do not actually support the standard array iteration methods. JavaScript provides an array function that is designed to create an array of a particular size. So here we are creating an array consisting of 5 items. However, by default, it creates an array that consists of empty items. So sure, this array does have 5 items, but all of these 5 items are what are called empty slots. These are actually skipped over by array iteration methods. So as an example, for each will skip over empty slots and we will see no log in this particular case. And similarly, if we try to map these items into another array, like an array of 1 to 5, that will not work either because map will skip over these slots. The solution to this problem is quite easy. We can use that beautiful spread operator to take this empty slotted array and create a completely filled array. Now, of course, those empty slots will be filled by the value which you would expect, which is undefined. But fortunately, now we can use the for each loop. So we can log out the x values and we will see 5 undefined. And similarly, we can map it into any other thing. For example, we can map it into numbers 1 to 5, and that will work as well. Creating empty arrays by using the array function, passing in a number, and then spreading it into a new array is the standard approach in modern JavaScript. Now, instead of undefined, if you want a filled array, for example, you want an array that consists only of zeros, of course, we can use the map function to map all of these undefineds to the value 0. But JavaScript arrays provide another method called fill, which takes a value and fills up all the empty slots as well. So if you want an array consisting of undefineds, use the spread. And if you want an array consisting of some other value, use the fill. Arrays are JavaScript objects, which means that they follow the same rules of equality. So even if two arrays might be completely equivalent structurally, unless they point to the same reference, they will not be equal. Here we have two arrays and they both consist of the same primitive strings, which is car, TV, and remote. Every time we use the array literal syntax, we are actually creating a new instance of an array. So items A and items B are completely different arrays. And if we try to use strict equality between them, we will get back the result false. Of course, items A is going to be equal to items A and items B is going to be equal to items B. And similarly, if we create a new variable and point it to the same reference that is contained within items A, then items C is also going to be equal to items A. And because items C and items A are pointing to the same array reference, if you push an items into that array using the items C variable and then log out items A, since it's the same array, we can see that camera has been added to that reference. Items B, being a different array, is going to remain unchanged, and this is sort of the reason why items A is not equal to items B. Now, if you do want to compare two arrays as equal based on their values, we can actually create a utility function for that quite easily. It's really up to you to define what you mean by equality. In our particular case, we want to make sure that both the arrays have the same length, and then for every item in array A, the item at that index in array A is strictly equal to the item at that index in array B. So if we go back to that example of two arrays consisting of car, TV, and remote, even though they are not strictly equal as far as JavaScript is concerned, the custom function that we wrote, arrays_equal, will return true for these two arrays because they have the same length and the primitive items within the arrays can be compared using strict equality. As you hopefully saw, there is a lot of power built into JavaScript arrays. So even though the original goal for JavaScript was not for it to be a data processing language, its combined support for object literals and arrays makes slicing and dicing data quite enjoyable. As always, thank you for joining me, and I will see you in the next one. A key tenet of programming languages is the ability to branch to different execution paths based on a condition, and the simplest way to achieve that in JavaScript is with if-else statements. Consider the simple example of a function where, based on a passed-in number, we want to determine if we should store the string positive or negative within a result variable. This is where we can use if-else conditions. First off, we check if the number is greater than or equal to 0, and if it is, the result is positive, otherwise we are going to store the string negative and eventually return the result from our function. For an if statement, we have the if keyword followed by a conditional expression, and if that expression evaluates to a boolean true, then the if block is going to execute, otherwise the statements within the else block are going to execute. Let's run through this function with two simple examples. First, we pass in a value 3, which of course is greater than or equal to 0, therefore result is going to be positive and that is what gets returned. If we pass in a value like -5, which is not greater than or equal to 0, is going to fall into the else block and result is going to be negative and that is what gets returned. Now one thing to note about if else within JavaScript is that the else is actually completely optional, and in this particular case we can even rewrite this example without using an else. We utilize the fact that within the if condition we don't necessarily need to assign to a variable that we're going to return anyways. Why not just write the return statement within if? This means that the remaining code within the nature function is not going to execute, essentially turning everything outside of the if condition into a giant else. Of course, we can also verify this by passing in the same examples of nature 3 returning positive and nature -5 giving us the string negative. An additional thing to know about if else within JavaScript is that we can chain additional if statements joined to an else. Let's expand our example to support an additional use case of providing the string 0 when the number is equal to 0. Here, in addition to if and else, we have an else if within our function. So when the first condition turns out to be false, we do an else if and then do a check for the second condition, and if that is also false, then eventually we go to the final else statement. So if you pass in 0, the first condition is true, we get 0. If you pass in a positive number, the second condition is true and we get positive. And similarly, if you pass in a negative value, then the first condition is going to be false and the second condition is going to be false, and we eventually get back the string negative. If you only have one statement in an if or an else code block, you can actually skip using the brackets around the body, but be careful not to overuse it as it can lead to subtle bugs. So we can actually rewrite our last example to be simple if, else if, and else statements each in their own line, where the code blocks are not surrounded by curly brackets. And of course, this code is still correct, it works exactly how you would expect. Now let's talk about some of the hazards of doing something like this. Consider this seemingly harmless function that takes two values a and b. If a is equal to 1 and if b is equal to 2, then it should log out a is 1 and b is 2, and if a is not equal to 1, then it should log out a is not 1. To prove that I'm not lying to you, I will pass in a check value 1 and 2, and indeed this will log out a is 1 and b is 2. Now here's the question, if I pass in 1 and 3, what do you think it is going to log out? This will actually log out a is not 1, and that statement is clearly wrong because a is 1. What has happened here is that I lied about not lying. The else block is actually associated with the second if and not the first if. And if I format it to its correct place, you can see that the console.log statement is actually incorrect. Someone wrote poor code. The console.log statement that makes sense for this particular else would be a is 1 and b is not 2. And of course, now everything makes sense. Since JavaScript is mostly whitespace agnostic, it's a good idea to use brackets to clarify your intent. In fact, we can rewrite the original code to be much better if we use brackets, and you can immediately see that if the intent was for a is not 1 to be associated with the first if, it looks much better with the brackets in place. Another advantage of using the curly brackets within your if and else blocks is that they allow you to pass in multiple statements. For example, in this particular function, if you pass in the password abracadabra, it will print all of these lyrics on the console. If you pass in the wrong password, you get nothing. Pass in the magic word, and you get every time you call my name, I heat up like a burning flame. Let's create a different song, but this time without the curly brackets, and I'm going to lie again over here and say that this is perfectly fine. If you pass in false, we should get nothing, yet we do get everything after the first statement. Because without a code block, only a single statement is a part of the if, so the ho and let's go still execute because they are not associated with the if in any way. So my final tip for this section would be that if you do want a single statement with your if or your else, write it after the if on the same line and enter a new line afterwards just to be very clear. A common trick that developers use when working with conditional blocks in functions is early return statements, and this can help your code look prettier and make it easier to understand. Consider a simple function called birthday that is designed to take a person object And if a valid object is passed in and it has an age property that is not null and it has an experience that is not null, then we want to update the experience by 10 and the age by 1. Instead of this nested if, we can rewrite it into 3 simple early return statements. If there is not a person, we return. If the age is null, we return. If there is no experience, we return. And now we can be guaranteed that the person has an experience and an age that we can update. And of course, we can go one step further and combine all of these different conditions into a single if expression. If we don't have a person, or the person age is null, or the person experience is null, then we simply do an early return. Otherwise, we update the experience and the age. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. Before we can truly understand the JavaScript ternary operator, we need to understand the difference between statements and expressions. Developing a mental model for what is an expression is quite easy. Basically, whatever you can use on the right-hand side of an assignment statement is an expression within JavaScript. So here, the right-hand side, 1, 2, 3 is an expression. Similarly, we can assign variable a to variable b, so the variable by itself is an expression. We can assign b plus a to another variable, which means that b plus a is also an expression. Now, code within JavaScript essentially executes in statements. All of the 3 things that we have over here, the 3 variable declarations, are actually variable declaration statements. Lots of things within JavaScript are statements. For example, if is also a statement, and it consists of a body which then again consists of multiple statements. Here we have 2 console.log statements. Now consider a simple use case where we calculate a condition based on math.random which has a 50% chance of being true. Based on the result of this condition, we want to create a value which will either be head or tail, like a coin toss. Of course, we can use an if statement for this purpose. If the condition is true, we assign value to head, otherwise we assign value to tail. Now sadly, within JavaScript, if statements are not expressions, which means that we cannot sort of write this kind of code where we assign value to the result of the if conditions, if block or else block. This will actually result in an error quite aptly called expression expected. When the result of your if-else conditional decision is going to be an expression, you can actually replace that if-else statement with the conditional operator. The conditional operator consists of 3 operands, a conditional expression, an if expression result, and an else expression result. The first 2 operands are separated by a question mark, and the second 2 operands are separated by a colon. When the condition expression value is to true, the conditional operator resolves to the if expression, otherwise it resolves to the else expression. And we can do a quick demo in this particular case by logging out the condition and the final value. You can see that when condition is true, we get head, and when condition is false, we get tail. And that is the basics of the conditional operator. Depending upon the circumstance, the conditional operator can greatly decrease the verbosity of your code when compared to an if-else. For example, consider this array of items consisting of numbers 1, 2, 4, 10, and 3, and we want to find the max item within this array without using the built-in math module. When you want to go through an array of items and compress them down into a single result, that is a great use case for the array reduce function that we have looked at in a previous lesson. We start off by assuming that we will see nothing and initialize our max to -infinity. And then for each iteration, we check the current max value which is going to be present within the accumulator and compare it to the current. And if current is greater, then we found a new max and return that as the new accumulator. Otherwise, we continue with the accumulator that we already have. No surprise, the final accumulator value is going to point to the maximum, which in this array is going to be 10. Using the conditional operator, we can actually invert this if-else to put the return in front, and then based on current being greater than accumulator, either return current or the accumulator. And converting our body into a single return statement opens up an additional opportunity for a cleanup. When the body of an arrow function is a single return statement, we can actually get rid of the code block, get rid of the return keyword, and the return is automatically implied. And if we run this code, you can see that it is functionally still correct. It is returning that value 10, but it reads much better. You can see that if current is greater than accumulator, then we have a new max, otherwise continue with the accumulator that you have. A great mental model to have with the conditional operator inspired by functional programming is that it is a simple way to map a single value into one of 2 possible results. For example, here we have a simple function called getFee, which returns a different value based on the isMember boolean. For members, we map the fee to 2, and for non-members, we map it to 10. Similarly, we can get a beverage based on the user's age. For example, if the person has an age of 30, we give them beer. And for younger members, for example, age 14, we default to juice. When you want to update multiple variables based on the same condition, a pattern that you can use is to combine the conditional operator with JavaScript destructuring to do it all in one go. Consider the use case where based on the weather, we want to determine our lower, upper, and head gear. Of course, based on the weather, we can make our decision in 3 separate statements. We either go with shorts or jeans for the lower, shirt or sweater for the upper, and cap or beanie for the head. Now, it's not particularly hard to read and I will be completely okay with this, but it doesn't immediately present the fact that based on the same condition, we are making 3 different choices, and there is a pattern of repeating ourselves thrice. Using array destructuring, we can do it all in a single statement. Based on the weather, we can create an array that consists of 3 items, either for the warm weather or the cold weather, and then assign them to lower, upper, and head in a single destructuring pattern. Not saying that the new structure is miles better, but it is worth knowing. A common pattern that you will find with the conditional operator is the nested ternary, and it sounds like it would be messy, but when formatted correctly, it can look like a thing of beauty. Consider a simple function that determines the nature of a number. If the number is equivalent to 0, we return the string 0. If it is greater than 0, we return the string positive, otherwise we default to negative. So for 0, we get 0, for 3, we get positive, and for -5, we get negative. We can actually replace this if return, else return into a single return of a nested ternary expression. No surprise, it is functionally the same as the code that we had before. And the first time that you see code like this, you might be a bit taken aback, but there is a way to read it. You read it like the first statement is an if, the last statement is the final else, and everything between is an else if. If you write your nested ternaries like this, they are quite easy to understand, but if you do it all in one line, don't be that person. Nobody can understand what the hell is going on over here. So the pattern to follow is to have the first if on its own line, the last else on its own line, and in between as many lines as the else if expressions that you need. A common mistake that beginners make when using the conditional operator is not knowing the impact of operator precedence. Fortunately, there is a simple fix for this issue without having to do mental gymnastics. Consider the desire to build this format discount function, which takes a value and then based on a boolean is %, either as the % or the $ as a suffix. Now we can actually write this function quite easily, where we take a value and an is % and then add to the value based on is % the suffix % or the $. Now this looks perfectly fine and we might probably approve this in a code review, but when we run this, you can see that we actually only get the % for both of our format discount calls. And the reason behind this bug is operator precedence. The ternary has a very low priority, which means that whenever we write an expression like this, as far as the runtime is going to be concerned, you can pretty much think of it as the individual expressions being wrapped by brackets. So let's take a look at that expression in our return statement and wrap it up in brackets, and I think you can see the issue now. In this particular case, value plus is % is going to evaluate to truthy, and therefore we are going to map that to the % by itself, which is the result that we are seeing. And the fix is pretty simple. Whenever you have a conditional as a part of a bigger expression, wrap up the whole conditional with brackets so that that conditional evaluates before anything else. With this simple fix in place, if we run our code again, you can see that we get the results that we expected. Alternatively, don't use a conditional as a part of larger expressions and instead pre-compute it into its own variable that you can then use in the larger expression. And as a code reviewer, make a mental note that the ternaries should either be wrapped or stored in their own variables. Fun fact, conditional is the only ternary operator in the JavaScript programming language. That is the only operator that has 3 operands, which are the condition, if and else expressions, and sometimes people, including myself, just call it the ternary operator. As always, thank you for joining me, and I will see you in the next one. We've been using strict equality, which is triple equals, throughout this course, but let's take a moment to discuss what is loose equality or the double equals and why you should steer clear of it as much as possible. When the two data types on the binary equality operator are the same, it doesn't matter if we use double equals or triple equals because the result will be the same. So as you would expect, 0 will be equal to 0, high will be equal to high, and 456 will be equal to 456. And the same is true for loose inequality as well. So not equal behaves the same as not equal equal if the data types are same on both the sides. So 0 is not equal to 456 and high is not equal to by. When the data types on the sides are different, then lose equality does more. It tries to do type coercion as well. So even though the number 42 and the string 42 are not the same, lose equality will try to pass that string into a number and then do the comparison, and therefore it will return true. It will do that for various Boolean comparisons as well. For example, 0 is equal to false, empty strings are equal to false, a positive number like 5 is not equal to false, and similarly a non-empty string like j is not equal to false. And this type coercion is also done by the lose not equal operator. So the number 42 not equal to the string 42 will return false, because once you do the passing on the string 42, they are equal, and therefore not equal is false. From the examples, lose equality seems like it should be fine, and mostly it is, except that it breaks one critical rule of mathematics. And that is the commutative property. So if a is equal to b and a is equal to c, then you would hope that b is equal to c. So let's see if this is true for lose equality. Now, as we've seen before, 0 is equal to false, and similarly an empty string is equal to false. But what might catch you off guard is that a string containing 0 is actually going to be false as well. That is because that string is first going to get converted into a number, and we've already established that 0 is equal to false. And of course, when types are the same, no type coercion takes place, so an empty string is not equal to the string that contains 0, and this is what is breaking that original commutative property. And this is not the only example that breaks this rule, so the question that you have to ask yourself, is it really worth it? To be safe and avoiding silly mistakes which can be hard to debug, the guidance is to use only the strict inequality and strict equality operators and do any coercion that you want yourself. The strict equality and the strict inequality operators within JavaScript are triple equals and not equal equal. And I don't know about you, but I'm personally happy if my 42 number does not behave like a 42 string. And similarly, of course, 42 is equal to 42. So if I really wanted to take that string and convert it into a number, I can do that myself. I can do 42 triple equals, convert that 42 into a number with the plus operator, and now they are equal. And similarly, the not equal equal operator does no type coercion, so just like message is not equal to hello, the number 42 is not equal to the string 42. Because lose equality type coercion has weird edge cases that no one working on modern JS needs to care about, TypeScript will actually mark type coercion lose equality as a compile time error. Now before I actually started recording this tutorial, I actually commented out check.js within my TS config. This is because with this option enabled, TypeScript would never allow me to write the crazy code that you have been seeing. And in fact, if we go back to that example where we proved that the double equals lose equality breaks the commutative property, it will error with a message that this comparison appears unintentional. You are comparing strings and boolean, don't mix your types because you don't know what's going to happen, and even with the same types, it's going to complain that this is always going to be false. What do you think you are doing? I hope you enjoyed this tutorial on JavaScript equality. As always, thank you for joining me, and I will see you in the next one. A fundamental concept in JavaScript is truthy and falsy values, and it sounds hard, but beyond the literal boolean false, there are only a few falsy values and they are quite intuitive. Basically, any value that behaves like a false in a conditional is called falsy, and everything else is called truthy. Now, instead of thinking about which values are truthy, you can basically just memorize the few values that are falsy. Of course, the literal boolean false by itself is falsy, so this particular console.log statement is never going to execute, and additionally, the special values null and undefined are both falsy. In terms of strings, there is only one string which is falsy, which is the empty string, and within the number data type, the values 0 and nan are both falsy. The final value that is falsy within modern JavaScript is the big int 0, which we can represent with 0n. And this is it. This is the entire set of falsy values. And because they are all falsy, none of the console.log statements will execute, and we can verify that by running this code. The logical complement operator, also called the bang, represented by the exclamation point, can be used to convert truthy and falsy values to their boolean true and false equivalents. Applying the not operator to boolean false turns it to true, and the same thing happens for all of the other falsy values as well. So not null, not undefined, not empty string, not 0, not nan, not big int 0, they all turn to true. We can actually use this operator to transparently convert falsy values to false and truthy values to true. If we apply it only once, then false turns to true and true turns to false. But if we apply it twice, then false remains false and true remains true. And what is more interesting is that a single NOT operator converts all other values to their Boolean complement. Applying it twice converts it to their Boolean equivalent. So for all of the falsy values that exist within JavaScript, we get back the literal false, and for everything else, we get back the literal true. This usage of the NOT operator twice has a number of use cases within JavaScript. Consider the requirement that given an array, we want to determine if it has any items. Now when the array doesn't have any items, it will have a length of 0, and we can easily convert that into the Boolean using the NOT operator. Has items is going to be false in this particular case, and for all other cases where the array does have items, length is not going to be 0, and therefore NOT is going to give us the value true. People often confuse truthy and falsy with loose equality type coercion. They are not the same, and as we discussed in our lesson on equality, loose equality is just bad. Truthy and falsy, on the other hand, is something that you can depend upon. Let's create a simple function that logs out the truthy or falsy nature of a value. If the value is going to be truthy, the conditional is going to resolve to truthy, otherwise it is going to resolve to falsy. Now we already know the few values within JavaScript that are falsy, which include the number 0 and the empty string. Now every other string other than the empty string is going to be truthy in JavaScript, and this is something that you can depend upon. You know that J is going to be truthy, the character 0 is going to be truthy, just like every other non-empty string. Compared to this, loose equality is pretty unreliable. As an example, it makes sense that 0 is equal to false, an empty string is equal to false, but a string containing the character 0 is also equal to false, and you might think, hey, sure, I can just exclude this one special case, but you can actually generate a string as long as you want. As long as it contains zeros, it will be equal to false. So in summary, the concept of truthy and falsy is not the same as loose equality with false. They are completely different. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. Null has been called the billion-dollar mistake, and unfortunately, JavaScript has made that mistake twice. So let's first start by looking at undefined. Undefined is something that the JavaScript runtime returns when a value hasn't been initialized. For example, here we have a variable message, and we haven't assigned it any value, so if we try to read it, the JavaScript runtime will give us undefined. Similarly, for a function that does not have a return value, essentially no return has been initialized, and therefore the JavaScript runtime gives us undefined. There are lots of other places that undefined shows up as well. For example, trying to read a property off of an object when that property hasn't been defined, trying to read a parameter when that parameter hasn't been passed in. Needless to say, it is a very fundamental value within JavaScript. The type of operator on an undefined value gives us the literal undefined, and undefined is exclusive in this particular set. No other value will give us this particular string. Also, with strict equality, undefined is exclusively equal to undefined, so we can use this to check if a particular value is exclusively undefined. One thing that often trips up beginning JavaScript developers is the fact that if you want to check for the presence of some global module that you haven't declared yourself, you must do that by using the type of operator. We know that when we declare a variable but we do not provide it any value, then it implicitly has the value undefined, and because at least a declaration for this variable exists, we can use it as you normally would. For example, you can use it to do a strict equality check with undefined. And if we execute this particular piece of code, you can see that it works perfectly fine. We see the console.log statement. However, for some variable that you haven't declared yourself, for example, you want to use some built-in module that is only available on modern JavaScript runtimes, you first need to do a check using the type of operator. If you try to use the variable in any other way, for example, trying to do a strict equality with undefined, we might be using a variable that the runtime has no idea about, and therefore it will throw a reference error. So even though using the type of operator with the variable and then checking if the result of that type of operation is the string undefined looks a bit verbose, that is the only way for checking the presence of a global variable within JavaScript. JavaScript uses null to intentionally denote a value that is not present. For example, if we ask a function for a current username but there is no current user, then the function can return an explicit null. There are plenty of functions built into modern JavaScript that will return an explicit null to denote the absence of a result. For example, here we have a string Bob from Bobbington, and we use the string match function to check if there are any matches to Ben. Of course, there are none because it is just Bob by himself, and therefore the runtime will return null. One thing to be aware of with null is that the type of operator with null will actually return the string object, and this is problematic because whenever we have any object within JavaScript and use the type of operator, we get the string object. So the type of operator cannot be used to disambiguate null from other values. Fortunately for us, only null is strictly equal to null, and that is the way to go if you want to exclusively check if a particular value is null. For null, triple equal to null will be true, and for everything else, it will be false. The developer guidance is that whenever you want to be explicit about something not being present, prefer to use an explicit null over an explicit undefined. For example, here we have a getProfile API that takes an ID. If the ID is 1, it returns John Doe. If the ID is 2, it returns Jane Doe. And then for everything else, we want to specify that there is no profile, so we choose to return null. And because we have an explicit null, it is a lot less ambiguous for consumers because they can be guaranteed that, hey, someone intentionally chose to return null, so they must be saying that this particular ID is not supported. Even though JavaScript made the silly mistake of having two bottom types, that is null and undefined, it comes with an easy way to combine the two into a single concept officially called nullish. We've talked about loose equality or the double equals and how it is unreliable, and that is true except when it comes to null and undefined. Within JavaScript, only null or undefined are loosely equal to null, and only null or undefined are loosely equal to undefined. Anything else that you can think of, like any of the falsy values, they are not going to be loosely equal to null. Any of the falsy values are not going to be loosely equal to undefined. And similarly, anything truthy is not going to be loosely equal to null or loosely equal to undefined. Checking loosely equal to null or loosely equal to undefined are called nullish checks within JavaScript, and it is conventional to use loosely equal to null because of course it is less keystrokes. So within JavaScript, if you want to check if a value is nullish, that is if it is null or undefined, we can do that easily with a double equals to null. This particular function will execute the if condition for null or undefined, and for everything else, it will go into the else block. Memorize this double equal to null because you will see it in JavaScript code all the time. This is the standard nullish check. Just like we can use loose equality to check if a value is nullish, we can use loose inequality to check if a value is not nullish. So in this particular function, we loosely check if the value is not equal to null, and this will be true for everything other than null or undefined, which means that within the if block, we can be sure that the value is not going to be nullish. And of course, this implies that within the else block, the value is exclusively nullish. Not equal to null, that is loose equality with null, is the standard way of excluding both null and undefined without having to worry is it null or is it undefined. So even though null and undefined are two different types within JavaScript, when working with them in conditional logic, it is quite easy to deal with both consistently using nullish and non-nullish checks. As always, thank you for joining me, and I will see you in the next one. Modern JavaScript has excellent support for classes, and you can think of a JavaScript class as the reusable blueprint for creating objects. We can create a car object called Toyota that has a name property pointing to the string Toyota and a drive function that logs toyota.name along with the string driving. And we might have other car objects in our codebase as well, for example Subaru, that follows a similar structure, of course with the name being different and the different name being used in the drive function. Now wouldn't it be great if we could create a reusable blueprint for creating such objects, and that is exactly where JavaScript classes come in. We define a class using the class keyword and provide it a name called car in this particular case, and you can use any valid JavaScript identifier. It is conventional to use Pascal casing for this, so that is why we have made the C of car capital. When we create an instance of the class, if provided, a special function called constructor is what will execute. Constructors are defined using the constructor keyword, and they have access to the instance of the object that is being created by using the special this keyword. So here in our constructor function, we accept a name property and initialize a property name on the object that we are creating using that provided value. We can define the methods that we would want on our object as well. For example, here we just want a simple drive method. Within our methods, we can access the instance of the object that we are dealing with by using the this keyword, just like we did in the constructor. To create an instance of the class, you invoke the class very similar to how you would invoke the function, except that you must prefix with the new keyword. So this new car call will invoke that constructor We are passing in Toyota, and that will set this.name to Toyota, which means that now when we invoke the drive method on this created object, of course, we are going to see that name along with the string driving. Now that we have this blueprint, we can create as many instance objects as we want. For example, we can easily create Subaru by passing in Subaru, and now when we drive the Subaru, we see Subaru driving. JavaScript classes allow you to provide a default value for any member by using the property initializer. For example, consider a simple counter where we have a count member which we want to start from 0. We can declare that by providing an identifier for that member, followed by the equal sign, followed by the initial value that we want. Now all instances of this counter will automatically get this count property with the value initialized to 0. And we can use that just like any other property on the object. For example, within an increment method, we can access it using this and increment the value of count by 1. Let's demo these facts very quickly by creating an instance of the counter, and you can see that the initial value of count from that counter variable is going to be 0. And of course, after we invoke the counter.increment method, the counter.count increments to 1. Modern JavaScript allows us to have private properties on a class, which helps us ensure controlled access to its members. Consider a simple event class, and within its constructor, we take an event name string and we initialize the event name property based on that value. We have a simple method called fire, which is going to log out the fact that that particular event has occurred. As an example, we create a simple event object that is designed to only fire clicks, and of course, event.fire logs the message click. Now by default, all properties on this object are public, which means that we can actually just use event.eventName to modify that to be open, and now this event will start firing open, and we want to prevent this kind of behavior. We want this object to only fire click events. So let's create a better version of this event class, and this time use a private property for the event name. Now all private properties on a class must be declared up front, so here we are declaring the private property event name, and the way JavaScript identifies a property as private is that we must prefix it with the hash character. And then we can create the remaining class body very similar to how we had it before. The key difference is that every single time we previously had this.eventName, now we have this.hashEventName because that is the name of our private property. And in terms of usage, of course, we can create an event instance, pass in the string click, and event.fire will log out click. The key feature of a private field is that we cannot access it outside of the class body. So if we try to access hash event name off of the event object, this is going to result in an error because a private field can only be accessed within the containing class. Of course, if we remove this invalid access of event name, the code will function perfectly fine as you would expect. Just like other modern programming languages, JavaScript classes also support static members, and these are attached to the class and not the instance, and therefore they can be shared across all the instances. Consider a simple class called square, and we have a constructor that takes a size and initializes the size property, and a method that returns the area based on the value of the size. We can create instances of the square quite easily, for example a unit square where each side is 1 and a quad square where each side is 4. Now imagine we are trying to do some performance optimization on our application, and we want to keep track of how many squares we are creating. We could create a global variable, but that might leak all over our code base. Fortunately, we can actually declare a static member on the square class. Here we are saying that the square class has a member called howManySquares, which we are initializing to 0. And every single time we create a new instance, of course the constructor will get called, and we can take this as an opportunity to increment square.howManySquares by 1. As static properties belong on the class and not on the instance, you access them using the class name. So in this example, we are doing square dot. And we use the same syntax for accessing this static property anywhere within our code base. So as an example, after we've created the two squares, we can access square.howManySquares, and of course the answer should be 2. We know that JavaScript objects allow you to define getters and setters, which look like functions when you define them, but behave like simple values when you use them. And you can define getters and setters in your class as well. And of course, the main objective is controlled yet convenient access to the underlying values. Consider this simple class called rangedValue, and our objective is to take a minimum, a maximum, and a value, and to make sure that when a new value is provided, it stays within the range min and max. We back that value up with a private field called current, and this makes sure that this doesn't leak out of our class. So now within our constructor, we accept a simple object that has the members min, max, and value, which we destructure into simple local variables. We initialize the members min to min, max to max, and current to value. We define a getter for the value member by using the get keyword followed by a function definition, which simply returns the value from this.current private property. Similarly, we can define a setter with the set keyword followed by a function definition that accepts a new value, and of course we will use this value, clamp it between the range min and max, and then assign it to the current private property. Now getters and setters are declared like they are functions, but all usage of them is pretty much like standard properties. So we can create a new instance of the ranged value, and then we want to read the current value, we use simply ranged.value. We do not need any brackets like you would with a function call. And similarly, writing to the value is done using the assignment operator. So if we try to assign range.value to 15, which is outside our range 0 to 10, our setter will get invoked and it will clamp it to the max value, which is 10. A key tenet of object-oriented programming is class inheritance, which is one of the ways in which you can create classes that reuse some base features and then extend that with additional utilities. Let's consider the classic example inspired by the animal kingdom. We have a base class called animal that takes a name value in its constructor and assigns it to the name property, and then provides a utility method called eat that simply logs yum yum. So of course we can create a simple animal instance called Dimple, read the name Dimple, and eat our yum yum way. A bird is just an animal, which means that it has all the features of the animal, and to declare this fact when we create the class bird, we use the extends keyword to extend animal. Within our constructor, in addition to the name parameter which is required by animal, we take an additional one called weight. Before we do any of the bird initialization, we want to make sure that any initialization code that exists within the constructor of animal executes, and we can do that with the function call using the super keyword. This will invoke the animal constructor, allowing it to set up the name, and we can continue by setting up the weight property ourselves. We can add additional methods to the bird as well. For example, we can add a fly method, and in this particular case, we will make sure that the weight is not greater than 3. And if it is, then the bird is too fat to fly, otherwise it believes it can fly. Now, since the bird extends the features of animal, when we create a new instance of the bird, it has access to the name property, it has access to the eat function, yum yum, but of course it has its own features as well. So if we log out the bird.weight, since we passed in 2 for Polly, that is what we get. And similarly, when we invoke bird.fly, Polly believes that she can fly. JavaScript comes with a built-in operator called instance of that can be used to determine if a particular object is an instance of a particular class. To demonstrate the usage of the instance of operator, consider 2 very simple classes. In fact, they are so simple that they are completely empty, and they will create empty objects as far as visibility is concerned. We create simple variables, an instance of the alpha and the instance of the beta. Now the type of operator on all instances of classes actually gives back the literal string object, because after all, classes are blueprints for creating objects. Despite this, JavaScript is smart enough that you can use the instance of operator to determine if a particular object was created from a particular class. Since the variable alpha was created from the class alpha, variable alpha instance of class alpha returns true, and alpha instance of beta returns false. Similarly, for the beta variable, beta instance of alpha will return false, and beta instance of beta will return true. Fun fact, JavaScript was around for quite a while before it got the special syntax for class definitions that we have covered in this tutorial, and there is no denying that it has made it a much more accessible language. As always, thank you for joining me, and I will see you in the next one. A core tenet of any programming language is how it deals with exceptions, and of course, it's a first-class concept in JavaScript as well, where it is called error handling. To kick us off, let's first take a look at the built-in error class. Here we have a simple instance of the error class created and stored in a basics variable. Now the constructor for the error takes a simple message value, and we can actually access this from the created instance by using the message property. Perhaps the most useful feature of the error class is the fact that it captures the stack trace into the stack member. It's just a simple string, but there are plenty of tools out there that help you process the string into more meaningful ways. At its core, the string contains the error type, the error message, along with the stack trace up till the point where the error class was created. Here we created the error on line 1 of our index.js, and the remaining stack trace actually shows some of the internals of the Node.js runtime that is executing this code. Beyond this base class, there are a few other error classes built into JavaScript as well, and all of them inherit from this base error class. One such child class is the range error. The key difference in these child classes is that the class name is going to be different, which you can sort of use to hint on the kind of error that you are raising. For example, range error is conventionally used when you want to indicate the fact that a value is out of range. Now, of course, because these are JavaScript classes, we can use the instance of operator on the created objects to check if they are an instance of a particular class. Additionally, because all errors inherit from the error class, instance of with error will also return true. Of course, the base error instance that we created previously is going to return false as an instance of range error and only return true as an instance of error. Now, all of these child classes inherit features from the base error class, which means that they still have the message property, which gives the original message name, as well as the stack property. The stack property is going to be the same as the base error class stack that we saw previously. The only difference is that the name is different. Here you can see that it says range error instead of error. Errors can happen for all sorts of intentional and unintentional reasons. For example, a common error in JavaScript is trying to access members of an undefined value. As a quick recap, we can access properties of objects using the dot notation. So with the person object, we can access person.name, and of course, it's going to point to that string John. Now, if we assign person to undefined and try the same thing again, the JavaScript runtime will throw an error. In this particular case, the error class that the JavaScript runtime uses is called type error, which of course is still an extension of the base error class. If an error happens in your JavaScript code and you do not handle it, no further statements will execute in that stack, which brings us to the topic of gracefully handling errors, which we can do with the try catch. If we try to use a variable that is not defined anywhere and we just assume that it's going to magically exist, of course the JavaScript runtime is going to throw an error. Now, as soon as it does that, any additional lines of code that we have are not going to execute. So this console.log statement, yay we made it, is never going to turn up. And if we execute this code, you can see it in the output. It only contains the reference error that fancy modern stuff is not defined. Our console.log statement, yay we made it, is nowhere to be found. To gracefully handle the error and not have our program exit with code 1, we need to wrap the offending code with a try catch. Here we are telling the JavaScript runtime that try to execute this code, and if it doesn't work for whatever reason, catch that error and give it to me in the variable that we are calling err. So now that we are catching the error and not letting it leak all over our code base, you can see that the console.log statement, yay we made it, can execute successfully. Now, of course, this error object that the JavaScript runtime throws is going to be of type error, which means that if we do instance of error, it's going to return true. It's going to contain the message property and it is going to contain the stack property. And if we run this code again, you can see our assumptions being verified by the program output. This particular error is of type reference error, but of course, since it does still inherit from error, error instance of returns true. Even though errors can happen naturally in JavaScript, you can always throw errors yourself. For example, when some value isn't behaving the way that you expected. Consider the simple sum function that takes two variables a and b and decides to return the sum, and we expect both a and b to be of type number. But this is JavaScript, which means that people can come along and pass in some numbers and some strings. Now ideally we would want an error, but this is JavaScript, which means everything is going to be fine. It's going to give us this concatenated string, and we were really expecting the number 200. Fortunately, we can early fail on silly mistakes like this ourselves. We can just check if type of A is not equal to number or type of B is not equal to number, and if either of these conditions are true, we can throw our own error with the message parameters must be numbers. And instead of getting this random string which is going to cause issues elsewhere, we get a much more reliable developer experience of an error being thrown up front. So when we look at the console, we can see that we are making a mistake, that the parameters must be a number when we are invoking the sum function. When an error happens in JavaScript, it will automatically start propagating back through the call stack till it gets handled by a catch statement. Consider the simple function called tantrum, which always throws an error, no. So when we invoke it from another function, for example, come here, of course it's going to throw an error. So now if you make a call to come here will also throw that error, and we can actually catch it over here and log out the message for the error object. So we invoke come here, come here, invokes tantrum throws an error, and we catch that all the way at the top in our root try catch. Of course, the whole objective of catching an error is that it no longer propagates. For example, if we have a big boy function that throws an error, but it doesn't leak anywhere, we catch it immediately within that function. If we invoke big boy and wrap it up in a try catch, that error is already caught within big boy, and this particular outside catch will never get invoked. With the JavaScript try block, you can optionally add a finally block to make sure any cleanup required happens irrespective of an error. Consider the simple scenario where we have within a try block the desire to open a DB connection and run a query, and we want to catch any errors that might happen within the try using a simple catch block. And finally, irrespective of whether an error happens or not, we want to make sure that the database connection is closed. Irrespective of whatever happens in the try or the catch block, the finally block will always execute. So no surprise, in this particular example, the try block will execute, there are no errors that can happen in try, so catch will not execute, and then finally will execute, and we can verify that from the console. Let's modify our code to represent the scenario where we have a failed attempt to run a query by simply throwing a new error. And in this particular example, the try block will execute. Because we throw an error, the catch block will execute, and of course, the finally always executes, and that is what we see on the console. JavaScript actually allows you to skip the catch entirely as well, so we can actually just use a try and a finally, and in this particular example, the try block will execute, it will throw an error, but before that error propagates, the finally block will execute, and we can see that when we run the code, we see the log from the try, we see the log from the finally, and then we see the error that we didn't catch, which propagated all the way to the Node.js runtime, logging that error to the console. One thing to be aware of with the try catch is that it only catches errors that execute in the same synchronous code block. Here we have a try block within which we set a timeout and we try to invoke a function we exist in the matrix, which is a function that doesn't exist, so we totally expect it to throw a reference error, and to catch that we wrap it up with a catch block where we log out we have neo. Now let's walk through how this code is going to execute. We are going to execute the try block within which we will invoke set timeout, and then the try block will actually terminate, and since no error has happened right now, nothing will be caught, and eventually after 1 second, which is the timeout that we have set up, set timeout is going to start executing the function we exist in the matrix. And because right now when set timeout is executing that function, it is not in the presence of any try and catch, which means that the error will happen and it will propagate all the way to the Node.js runtime, which will log it to the console. Now if you want to catch this error using a try catch, we need to put the try catch in the same synchronous code block that is resulting in the error. We refactor our code to make sure that we exist in the matrix is wrapped by our try catch. And now instead of it being handled by the Node.js runtime, we will catch it effectively and simply log out we have neo. And if we run this code, you can see that that is exactly what happens. There is a key difference in how the server code like Node.js handles uncaught errors versus how they are handled by all the browsers. Consider this simple code where we set up a timeout to invoke a function it's all in your imagination which does not exist, so we totally expect this to throw an error. And then we set a timeout for 2 seconds to log out my own universe. Now here's how the program execution is going to go. After 1 second, it will try to invoke it's all in your imagination, it will throw an error, and because this is running in Node.js, it's going to result in a program failure. And the second timeout, my own universe, will never execute, which is why we do not see that statement anywhere in the console. This makes a lot of sense in a server environment because we don't want an unreliable process running around, perhaps corrupting one user's data with another user's information. It is better to let the whole process exit, log it to a monitoring service, and then just restart the process to make sure that you have a clean, good state. This is different from how we want the browsers to operate. If we take the same code and paste it into a browser console, what will happen is that after 1 second, we do get that error that it's all in your imagination does not exist, but the website doesn't crash, and after 2 seconds, we still get the log from the second timeout, which logs my own universe. And this makes more sense for a browser environment where we don't want the whole website to fail just because a single HTTP request failed. This is also why sometimes you find that the website will not be doing what you want. For example, you click a button and nothing happens. That's probably because there is an error on the click handler, but that's not going to result in the whole website crashing on you. Perhaps you can try different things on the website. For example, press the back button and then you press the next. And now that button that you were clicking will start working again. Browsers only unwind the current synchronous stack and do not crash the whole website in the presence of an uncaught error. One best practice to always follow that beginners and certain tutorials often forget is that you should never ever throw plain strings as errors. Here we have a simple function alpha that tries to be helpful, tries to throw a helpful message, but does not wrap it up in an error object, and this is not good enough. To demonstrate that, consider a more real-world scenario where alpha is invoked by beta, which in turn is invoked by gamma, and we do catch the error that will happen when gamma gets invoked and log that error to the console. Unfortunately, since alpha decided to throw a string instead of an error object, that is exactly what we get within the catch statement, and if we log it out to the console, we only see this message and we have no idea what is the code execution that resulted in this particular error. Compare this to the simple fix where we wrap our error message in an error object and now execute this code again. Now we have a much clearer idea that an error has happened with the message helpful message at alpha, which was invoked by beta, which was invoked by gamma from our main application source index.js. A common pattern worth knowing about when it comes to error handling is that sometimes we handle an error only for logging and monitoring purposes and then immediately rethrow it to let it proceed to its potentially uncaught failure. For example, here is a simple function that just has some pet peeve against the number 1. I don't know why it hates it. It says that it hates it because it's too lonely, but I'm not so sure about it. If the input, however, is not 1, then this function will be happy. And just like in the real world, there is a function called poke that just likes to invoke do not like 1 with the one value it doesn't like, which is 1. Poke, however, only wants to try to catch this error for logging and monitoring purposes. For that, it adds a catch statement, logs the error off to a monitoring service, and then because it doesn't want to handle it properly, it simply rethrows that error for someone else to handle. This pattern of catching an error and only looking at its few properties for monitoring purposes and then rethrowing it is a common pattern that people use when you do not expect an error, but when an error does happen, you do not want to ignore it, you want to be notified about that fact. However, you do not want your program to be unreliable, which is why you still throw that error again. And to demonstrate that, let's just run this poke function and execute this code. You can see that because of that rethrow that we didn't catch, the program has exited. But before it did, we did get the opportunity to log that error off to a monitoring service, which in our case is just a simple console log. I'll wrap things up there. As always, thank you for joining me on this lesson on JavaScript error handling, and I will see you in the next one. Modern JavaScript comes with the neat operator called nullish coalescing to provide a default value in the presence of a nullish, that is null or undefined values. Let's say we want to initialize a message variable based on a provided input. People often incorrectly use the boolean or operator for this purpose, but it has an issue where it does more than what you expect. It does work fine if the value is null or undefined. So here you can see that if null or undefined is used, it fallbacks to the default value. And for other strings, it seems to work fine. For example, here it uses the provided input instead of the fallback default value. But the issue is that in addition to null and undefined, the OR operator actually works on the concept of falsy values. So an empty string will also fall back to the default value. In addition to strings, another example is numbers as well. So null and undefined, sure, the boolean operator does what you expect, and for valid numbers it works except when you provide the number 0. So the OR operator is not the same as a nullish check, it is more like a falsy check. If you wanted to only include nullish values null and undefined, traditionally we would need to do an explicit nullish check combined with the ternary operator. Fortunately, JavaScript now comes with the nullish coalescing operator that does exactly that. So if the left hand side is null or undefined, it goes to the default value, and for everything else, whether it is empty or non-empty, as long as it is a string, it uses the provided value. And we can repeat this example with numbers as well. If the left hand side is null or undefined, then the right hand side default value is used. For everything else, like the number 10 or the number 0, it really doesn't matter, it's not null or undefined, and therefore the left hand side value is what is used. JavaScript is fairly resilient when it comes to undefined properties, except traditionally it hasn't been resilient enough. To demonstrate that, consider a simple Jamie object that has a name and a cat member, and then the cat itself is an object that has a name and a toys member which points to an array. And of course, we can use various access methods, for example, to access the cat name or the cat's first toy. However, we can also access properties that do not exist. For example, Jamie does not have a dog, and the JavaScript runtime will not throw an error and simply give us back the special value undefined. However, if we overextend our welcome and try to read the property of that undefined, then the JavaScript runtime will throw an error and exit the stack. Similarly, getAddress is not a property that exists on Jamie, and if we try to get it, the JavaScript runtime gives us undefined but doesn't throw an error. However, then if we try to invoke it, then the JavaScript runtime suddenly says, hey, you're doing something wrong. And the same for cat.hobbies as well. The cat has no hobbies, JavaScript runtime is fine, it gives us undefined, but if we try to access like its first hobby, then again the JavaScript runtime will throw an error and exit the program. Modern JavaScript comes with the optional chaining operator that allows you to safely use nullish values without JavaScript throwing an error. Consider the simple data structure for people. We have John with a name and an address, and then we have Jane that only has a name and has not provided us with her address. We have the simple logPerson function that takes a person object and is designed to log the person name and the person country based on their address. Now, of course, this function is going to work perfectly fine when we pass in John. We see the name John and the country France. However, if we log Jane, the JavaScript runtime is going to throw an error because Jane does not have an address, and therefore we are trying to look up country from an undefined address. Now, of course, we can handle nullish, null or undefined values explicitly by first checking, hey, does the person have an address? If they don't, then just return undefined. Otherwise, read the person.address.country. And now, instead of throwing an error and exiting the program, we get a more reasonable log of undefined. Fortunately, with modern JavaScript, we don't need to write ternaries like this anymore because we can actually use the optional chaining operator where instead of simple dot, we use question mark dot. And in terms of behavior, it is exactly the same. If person.address is going to be null or undefined, then we're going to get undefined. Otherwise, we are going to get address.country. We could see the value of this operator even right now, but it becomes even more significant when we have optional of optional of optional. For example, if person could potentially be undefined as well, we simply add the question mark dot over there, and now we have a much neater syntax than the nested ternary that you might need to write otherwise. Of course, if the value is going to be there, this is going to have no effect, so we could pretty much go crazy if we wanted to, and we still get the same program output as we did before. The JavaScript optional chaining operator actually supports 3 syntax forms, so in addition to property access, it supports index access and function invocation. Let's take a trip down memory lane and visit our old friend Jamie again, and of course we can look up Jamie's cat name or the cat's toys. But as we know, Jamie does not have a dog, and thanks to optional chaining, we can look up the dog's name, and instead of throwing an error, the JavaScript runtime gives us back a polite undefined. Similarly, Jamie does not have a getAddress function, and we can actually use optional chaining question mark dot to optionally invoke the method that doesn't exist, and again, instead of throwing an error, the JavaScript runtime gives us the polite undefined. Jamie's cat does have toys, however she doesn't have hobbies, so hobbies is undefined, and we can actually use the optional chaining question mark dot along with an index operator to look up a member from an array that potentially doesn't exist. And of course, all of this works as you would expect without any error, as we can see in the demo console. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. A switch statement is something that you can use to execute different actions or cases based on the value of a single JavaScript expression. Consider the simple example where we want to log the price of a fruit. We can easily do that using a switch statement, and at its core, the switch statement consists of the switch keyword followed by an expression that will be used to match against the different case clauses. As an example, if the fruit evaluates to the string apple, we want to log out 1.00. The case clause consists of the case keyword followed by the match value followed by the colon followed by the statements that you want to execute for this particular case. We can add as many cases as we need. For example, let's add a case for a banana and an orange, both with their own console.log statements that log their individual prices. One very important fact to remember is that we almost always add a break statement at the end of individual case clauses, and this ensures that once that particular case is done, we break out of the switch statement. Otherwise, it would actually fall through to the next one. As an example, if we forget this particular break in apple, after logging out 1.00, it would actually jump into the banana section and log out 0.50. But because we have the breaks in place, apple only logs out 1.0, banana logs out 0.50, and there is no fall through between the different case statements. Sometimes you want to execute the same set of code for different values of the conditional switch expression, and for that we can use the fall through pattern. Consider the simple example where we have an HTTP status code that can only be the numbers 200, 300, 400 or 500. For the status code 200, we want to log out the string success, and for all of the other codes 300, 400, 500, we want to execute the same code that logs out the string error. Instead of repeating this code block in the individual case statements, we can simply write the case statements and let them fall through by making sure that there is no break between the individual cases. As an example, if the status code is equal to the number 300, it's going to start executing any of the code that follows till it eventually hits the break statement, and therefore it will execute this console.log error. Adding an optional default clause to your switch statement allows you to handle unexpected values that do not match any of your case clauses. Consider the simple example where we are sending the animal to the ark and placing them properly. For example, if the animal is a cat or a dog, we want to put them on the lower deck. If they are a chicken or a pigeon, we want to put them on the upper deck. And finally, for everything else, we want to make them extinct. If you want to capture anything that didn't match any case statement, we can do that with the default clause. And syntax wise, it is very similar to the case statement. It simply consists of the default keyword followed by a colon, followed by the code that we want to execute. So now if we run this send to ark function, a dog would go to the lower deck, a chicken would go to the upper deck, and any other value, for example the string dinosaur, will fall through to the default clause and we will log out extinct. Internally, the JavaScript switch statement uses strict equality to compare the conditional expression with the individual case clauses. You can recall that JavaScript strict equality works perfectly fine for primitives like strings or numbers, so Monday is equal to Monday and 1 is equal to 1. However, that is not true for objects, so just because two objects are structurally equivalent, unless they are the same reference, they are not going to be strictly equal. With this recap out of the way, consider the simple object person that consists of a name property pointing to the string John. Now we can be a bit crazy and try to use this object as is in a switch statement and say that hey, if this person matches an object name of John, log out hi John, but this is not going to work. This case is never going to match because the underlying strict equality triple equal is always going to be false. The proper way to do this switch statement would be to identify some property that can be used with strict equality and still uniquely identifies the object. For our simple case, using person.name, which is of type string, and using that for the case clauses will work perfectly fine. You can see that hi John is executed, but hi John will not work, is nowhere to be found in the output. If the code in the switch is within a function and you are going to return from some case, then for obvious reasons, you don't need to have a break statement in that case. Consider the example where we have a toss result value, which can be 0 or 1, and we want to return the string version for these values. So if the value is going to be 0, we are going to return the string head, and if the value is 1, we return the string tail. Now, because the case clauses end in a return statement, there is no need for a break, as the code in the switch statement will stop executing just like any other code in the function once we hit the return statement. So toss result 0 will return the string head, toss result 1 will return the string tail, and we can verify that from the program output. Let's talk about some of the best practices regarding switch statements, and a big thing worth knowing is that case statements don't create a block scope and it's up to you to create them using parentheses. Consider a simple action string that can be say hello or say hi, and then based on the value of action, we want to create a message variable which will be hello or hi, and then log that message out. This code looks perfectly fine, but when we actually try to run it, it will actually fail. And the reason why is that we are actually declaring the same variable twice within the same scope, because there is only one block scope over here, and that is dictated by the parentheses of the switch statement. Now the fix is quite simple. We can actually create a block scope whenever we want by simply using parentheses ourselves. So we can wrap the case statement bodies with parentheses, and now they are all isolated into their own individual block scopes, which means that the message variable created in the first case is completely isolated from the message variable declared in the second case. So now the code will execute without any issues. Because the action is say hello, the first case block will execute and we see the string hello logged to the console. When the evaluated result of a switch statement is a simple expression, it is conventional to replace the switch statement with an object lookup pattern to achieve the same result with fewer lines of code. Consider this function office hours that takes a particular day string and then based on the value of that string, returns our working hours for that day. We have values for all the days, Monday to Friday, and then for everything else, which are weekends, we return the string closed. So if we pass in the string Thursday, we get 11 to 4, and if you pass in the string Sunday, we get closed. Note that our function body consists of a simple mapping of one string to another, along with the potentially default value. A feature of JavaScript is that we can actually use simple objects to create a mapping from one string to another. So from Monday to Friday, we can provide the string values, and then we can fetch the desired value from this object by using an index lookup, passing in the provided day. Now, if the provided day does not exist within this object, for example, Sunday does not exist, then the JavaScript runtime will give us the value undefined, which of course we can null coalesce to a default value. For example, here we are defaulting it to the string closed. So if you pass in the string Thursday, it's going to look up the value for that string, and of course it's going to be 11 to 4. And for everything that is not present, for example, passing in the string Sunday, we get back the default value of closed. So in summary, in the object lookup pattern, on the left hand side we have the case clauses, on the right hand side we have the case results, the conditional switch expression is used as the lookup, and null coalescing is used to provide the default result. The object lookup pattern is a more functional programming inspired expression-based version of a switch statement. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. Just like other C-inspired programming languages, JavaScript also supports the standard index-based for loop format. Consider a simple array of people, each with their own name, Jane, John, and Jack. We can actually loop through the items of the array quite easily by using the JavaScript for loop. The standard for loop consists of the for keyword, followed by an initialization statement, followed by a conditional termination expression, and an afterthought statement. The for loop comes with a body block, and you can put as many statements as you want within that. The objective of this simple for loop is to log the names of all of the persons within the people array. Here's how the basic for loop runs. It starts off by running the initialization statement. Next, it checks if the condition expression is true, and if it is, then it runs the body of the for loop. Next, it runs the afterthought statement, and then we basically start to loop around, checking the expression. If it's true, running the body, running the afterthought, and this loop will continue as long as the condition expression continues to be true. In our simple example, we are starting off at index 0. We look up the person from the array using the index and log out the person name. Next, we increment the index by 1, and if index is still within the bounds of the array, we repeat the process till index is no longer less than the length of the array, at which point we terminate the loop. You might recall that JavaScript arrays are 0 indexed, which is why we start the loop at 0 and terminate it at length -1, also known as index less than length. A little known fact about the standard for loop is that the initialization, the condition, and afterthought sections are actually all optional. So instead of using the initialization section of the for loop, we could initialize a variable externally, and this would function exactly the same as if we had written let index is equal to 0 within the for loop. Here we are starting at index 0 and terminating before 5, so we can see on the console we have 0, 1, 2, 3, 4. Similarly, instead of using the afterthought section of the for loop, we could do whatever modification we need to make within the for loop and leave that section out from the for loop, and this functions the same as if we had put that statement in the afterthought. And we can even take the condition expression and leave that out to truly prove that all of these sections are optional. Now in this particular case, since there is no terminating condition, this particular program will execute indefinitely, logging incrementing numbers to the console till of course we exit the program. Modern JavaScript comes with a for-off loop that allows you to conveniently loop through arrays and other iterables in a simpler fashion when compared to the traditional index-based for loop. Here we have the same array of people, Jane, John, and Jack, and we are using an index-based for loop to log the person names. We can actually achieve the same functionality with the more modern JavaScript for-off loop. The for-off loop consists of the for keyword followed by a variable declaration, followed by the off keyword, followed by the item that we want to iterate over. Here we are iterating over the people array, and for each iteration of the loop, we are storing an individual item into the person variable. So the first time this loop runs, person is going to be the object that contains the name property with Jane. The next time it's going to be the object with John, and finally it will be the object with Jack. In each iteration of the loop within the loop body, we are logging out the person's name. So functionally, it is going to be the same as the index-based for loop that we wrote before, but as you can see, it is much neater. Since we don't need an index variable, we don't need to do ++, and we can use const to declare the current item up front. There is less likelihood of making silly mistakes, so unless you have an explicit use case for the index variable, in modern JavaScript, for off is the way to go. All JavaScript for loops support early termination with the use of the break statement. Consider a simple array consisting of a few places around the world. We also have a separate array consisting of a few favorites. Our mission is to find the first place that also exists within our favorites array. For this, we loop through the places with a simple for off loop, and then we loop through the favorites within that using another for off loop. If at any point the place that we are looking at is the same as the favorite that we are looking at, congratulations, we have found a match. Now that we have found our answer, it would be useless to continue to loop through the favorites. We can exit out of the for loop by using the break statement. To demonstrate that the for loop will exit, let's put a simple log statement so that we can be sure that we are not looking at any more items. Now once we have the match, there's no point in looping through the places either, so we will make sure that if we have a match, we will break out of that for loop as well. Finally, at the end of the two for loops, we log out the match that we have found. If you look at the two arrays, the only thing that is common is Tokyo, so we should look at Paris, London, and Tokyo from places, first being compared to Beijing and then being compared to Tokyo, and the loops terminating. And when we run this code, that is exactly what happens. Thanks to the break statements, we terminate the loops as soon as the match is found. You can use the continue statement to jump to the next iteration of the loop, essentially skipping over the rest of the loop body for the current iteration. Consider the simple task of printing out numbers 0 to 14, but skip the log if the number is divisible by 3 or if it is divisible by 5. We can iterate from 0 to 14 with the simple index-based for loop. Within the loop, we check if the index is divisible by 3, and if it is, we skip the remaining body with the continue statement. We can do the same thing with the other requirement as well, so if the index is divisible by 5, we skip over the body with the continue statement. Finally, for all of the other index values, we simply log them to the console. If we run this code, you can see that it matches our expectations. Anything that is divisible by 3 or 5 is not getting logged to the console. JavaScript also comes with a for in loop, but it's more of a traditional feature that you really want to use in modern JavaScript, as there are better ways to achieve the same effect. The for in loop is designed to be used with objects, so here we have a simple object called point that has properties x, y, and z with values 3, 1, and 2. As you might recall from our lesson on objects, we can actually use the strings x, y, and z to look up the values of these properties from the point object. Using a string in such a fashion is called a key, and that is exactly what is returned in each iteration of the for in loop. So when we iterate over the point object using a for in, it'll be the string x, then the string y, and then the string z. We can use this key to look up the value for that property from the point object. For x it will be 3, for y it will be 1, and for z it will be 2. Let's log out the key and the value for each iteration of the loop, and as you can see, it matches our expectations. We have the keys x, y, and z with values 3, 1, and 2. Now, as I mentioned, the for in loop is sort of found within modern JavaScript because it's really up to you to make sure that when you get the key, you get the value for that corresponding key. Fortunately, there is a function on the object module that does this association for you up front, decreasing the chances of mistakes. The object.entries function takes an object and returns an array of tuples with each item containing the key and the value already associated for you. So if we have this array, we can actually just use our standard for off loop to loop through these entries, each time destructuring the keys and the values into their appropriate variables. So if we log out the keys and the values again, you can see that this for off is equivalent to the previous for in. Additionally, object.entries works more reliably compared to for in when it comes to modern JavaScript features like symbols. Many times when you are working with arrays in JavaScript and you want to loop through the items, instead of using the for loop, you can actually just use the array built-in methods. Consider this very simple array of car manufacturers. We can log out the cars with a very simple for off loop, and for each car we use console.log. Now instead of the for off, we could just as easily do cars.forEach and pass that individual item to console.log. The JavaScript for off loop and the for each array method both achieve the same thing, and it's up to you to decide which one looks better for you. I personally like the for each in this particular example. There are other cases where the JavaScript array built-in methods can drastically save you from writing a lot of code within a for of yourself. As an example, consider the boolean has Audi, which we want to be true if the cars array contains Audi. We can determine this quite easily by looping through all of the cars, checking if the car is equal to Audi, and if it is, then has Audi is equal to true, and we can break from this for loop. But there is a JavaScript array method that can achieve the same effect with lesser code. We use the findIndex method to see if any car is equal to Audi, and if the response from findIndex is not equal to -1, that means that we have found a result, and therefore has Audi needs to be true. So the guidance is, if you need to do something complicated that depends upon multiple inputs, then use the for loop. Otherwise, if it is something that falls into a category of an array utility method, then just use the method. A key reason why you might prefer a for of loop over the array for each is that for each does not support early termination, but you can use another array iteration method to achieve the same effect of continue and break in a more functional programming inspired pattern. Consider a simple input array consisting of a few numbers. With the for loop, we want to skip if the value is 2, terminate the for loop if the value is 5, otherwise log the value to the console. We can loop through the input with the simple for of loop. If the value is equal to 2, we continue to skip. If the value is 5, we break the loop with break, otherwise we log the value to the console. So for this input array, the loop will print 3, skip over 2, print 7 and 4, and then terminate at 5. And if we run this code, that is exactly what we see on the console, no surprises here. Let's see how we can achieve the same effect with a simple array iteration method. For the array iteration methods, if you want to continue, you're pretty much going to simply return from the callback function, but the difficulty is in the break statement, and for that, we need to utilize the fact that some of the array iteration methods will stop iterating as soon as they have the answer that they are looking for. The simplest example is the find method, so we can actually loop through the input with the find method. If the value is equal to 2 and we want to just jump to the next item, we do a simple return. Otherwise, if you want to terminate, for example, on value is equal to 5, we simply return true, and this signals to find that, hey, we have found our item, which essentially terminates the loop. For all other items, we simply follow our requirement and log the value. As you can see, the output from for of matches the find method. For both of these, we see 3, 7, 4. Personally, I would just use the for of loop, but bending functions to your will is a pattern worth knowing, if only to understand the existing code bases out there. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. One of the most daunting yet surprisingly easy thing to master as a JavaScript developer is JSON. At its core, JSON is simply a string-based data transfer format. It only supports a limited set of values. For example, here we have an object. The object itself has a few other values over here. For example, we have a string and then we have a number. All keys of an object must be quoted using double quotes. The key and value is separated by a colon, and the different keys are separated by commas. It looks very similar to a JavaScript object, and in fact, if we write the same syntax as JavaScript, it is going to be perfectly valid. So no surprise, JSON stands for JavaScript Object Notation. A key tenet is that unlike some binary format, JSON is very human readable, at least for someone who knows JavaScript. The first JSON parser was written in JavaScript, and if you are using some other programming language, you might still need to install an external library, but for JavaScript, you don't need to install anything extra, as the runtime has first-class support for JSON serialization and deserialization as a part of the built-in JSON module. So here we have some JSON content stored in a very simple string, and we can parse this string into a real JavaScript object by using the json.parse method. This method takes that string and converts it into its JavaScript equivalent. So what we get back for this particular input is a real object. We can access its name property, its age property. We can verify that the types are correct as well. The type of object would be object, the type of object.name would be string, and the type of object.age would be number. The process of converting an input JSON string into its JavaScript equivalent is called deserialization, which we are doing using the json.parse method. We can also do the opposite of taking a JavaScript object and converting it to its JSON equivalent, also called serialization, using the json.stringify method. Of course, this gives back a string which we can verify using the type of operator. Now if we log this string out, you'll notice that it is quite compressed. This is because JSON, like JavaScript, is not whitespace sensitive. So just like it doesn't matter if we write our object in JavaScript on a single line or on multiple lines, it doesn't matter in JSON either. Because it is a string-friendly format designed for simple data transfer, JSON doesn't support the full set of JavaScript data types. In addition to the simple values that we've looked at, which is string, for example John Doe, number, for example 30, JSON also supports booleans, which are true and false, the null value, arrays, and of course the arrays can contain any other data type that JSON supports. For example, here we have an array that consists of 2 objects, which in turn again contain strings and numbers. And then finally, you can have other objects as well. And of course, once this gets parsed, we get the same equivalent of writing this code in JavaScript. JSON is a strict subset of JavaScript, so all valid JSON is a valid JavaScript expression, but on the other hand, all valid JavaScript is not valid JSON. Beyond the type restrictions that we've looked at, there are a few other syntax restrictions that also only apply to JSON. The first restriction has to do with trailing commas, so while you can have trailing commas in arrays in JavaScript, they are not valid in JSON. Since it is invalid, the built-in JSON.parse function will throw an error. Similarly, we can have trailing commas at the end of object properties. That is also not valid in JSON. The other big restriction is that you must use double quotes everywhere, so single quoted strings are not supported. That will throw an error. And similarly, the keys also need to be double quoted. While it is valid to use single quotes for keys within JavaScript, that is not going to work within JSON. If we follow these 2 simple rules, that no trailing commas and always use double quotes, then we will be fine. A little known fact is that all of the supported values in JSON are actually valid JSON even by themselves. Now, of course, we can use JSON.parse to parse an object, but we can actually use it to parse a string as well. We can use it to parse a number. We can use it to parse a boolean, to parse the null value, and of course, we can use it to parse arrays as well. Now, even though these are all examples of valid JSON, most commonly you will be using an object at the root of your JSON content. There are some values that can appear in JavaScript objects that get handled differently by JSON than you might expect. As we've mentioned, JSON supports the JavaScript number data type, and it supports everything that is type of number except for the special values nan and infinity. Whenever JSON stringify finds these values in our objects, it actually replaces them with a null value. The reason here is that these values might not be supported in other programming languages, so converting them to null makes for a better cross-language experience. In addition to these special values, there is one more special value that you should watch out for, and that value is undefined. Since age is pointing to undefined, if we try to read person.age right now, the JavaScript runtime gives us undefined, but that is also the value that the JavaScript runtime gives us for any property that doesn't exist on the person object. And based on this fact, JSON stringify treats an undefined pretty much as an absent property. So name still gets serialized, but the age property, which is pointing to undefined, gets completely removed from the output. Now, if you do want to serialize the fact that a property exists, but its value is absent, then of course the answer is use an explicit null. And now JSON.stringify will preserve that property with the value pointing to null. The JSON stringify method actually takes a few additional optional arguments that can be used to customize the generated JSON string. Consider the simple JavaScript object consisting of foundation pointing to string Mozilla and year pointing to the number 1998. We can customize how this object will get serialized by creating our own custom replacer function. For each property that JSON has to serialize, it will invoke this function with the key and the value. We can do lots of cool stuff in this function. For example, we can remove all of the properties where the value is of type string by returning undefined, because as we know, undefined values result in property omission with JSON stringify. We can return some other value as well. For example, for the key year, we can sort of mask it by returning the string star 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 star. And for everything else, we can leave it unchanged by returning the value as is. To use this replacer function, we pass it as a second optional argument to JSON.stringify. And of course, for our Mozilla example, foundation is removed because it is of type string and year is masked. In addition to the second optional argument, stringify actually takes a third optional argument as well, which is used to determine the indent. As we know, if we have an object and we try to JSON stringify it, we get back a pretty compressed string. Using the third argument, we can pass in a number to nicely format the generated string. For example, here we are formatting it with 2 spaces. You can also customize how your JavaScript classes get serialized by adding a custom toJSON method. For example, here we have a simple class person that takes a config object and then notes it down as its config property. We can customize how this class instances get serialized by providing a toJSON method, and whatever we return from this method is what will actually get serialized by json.stringify. Here we are saying that when the person gets serialized, it should contain everything that gets passed as the config, and in addition, the type property with the value person string. To demonstrate that, let's just create a new person with the name John and the age 25. And now if we try to json.stringify the person, our toJSON will get called and the resulting output will contain type person in addition to the config that we passed in, which is name John, age 25. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. For most looping needs in JavaScript, you will most likely use the for loop, but when you are getting values only on demand, then the while loop is an excellent candidate. Consider the simple array consisting of people Jane, John, Jack, and Joe. If we want to log out the names of all of these people, we can do that quite easily with an index-based for loop. We can actually achieve the same effect with the while loop provided by JavaScript. The while loop is syntactically much simpler than a for loop because it only consists of a condition and a while loop body. It starts off by first checking the condition. If the condition is true, it's going to execute the body, and then it's going to check the condition again, and as long as the condition is going to be true, the body is going to execute for another iteration. Unlike the for loop, we are responsible for doing our own initialization, which we are doing with the simple statement before the while loop, and we are responsible for our own afterthought, which we are doing as an additional statement in the body of the while loop. There is a slight advantage of using a for loop here in that it doesn't leak its initialization variable to the outer scope. However, the while loop does, which can result in variable conflicts with the other loops. However, with the while loop, you do have more control in how you want to structure your initialization and the afterthought. A strong reason for using the while loop is when your action is going to have an impact on the items that you are iterating over. As an example, consider wanting to remove the person one by one from the people array and then logging it out. This is quite easy to do with the while loop because we simply pop the last item, store it in a person variable, and then log it out. This sort of thing is not a great experience for a for loop, as you really shouldn't use a for loop when the item you are iterating over might change. Once this while loop terminates, the people array should be empty, and we can verify that with a simple log statement. And when we run this code, you can see that it matches our expectations. Sometimes you want to execute the body of the while loop at least once, irrespective of the condition being true, and for that we can use the do while loop. Consider the example where we want to log out the Fibonacci numbers which are less than 100. We know that the first Fibonacci number is 0 and the second Fibonacci number is 1. Since the initial Fibonacci number is less than 100, there is no point in checking if it is less than 100 up front. So we use a do while loop. Within the body, we log out the current Fibonacci number, and then we move the next Fibonacci number, which is current 2, into current 1, and calculate the next upcoming by simply adding current 1 plus current 2. Now we will repeat this process as long as the current Fibonacci number is less than 100, and for that we add the while with the condition that current 1 should be less than 100. And if we run this code, you can see that it works as expected. We start off with 0, then 1, and then continue till current 1 becomes greater than 100. I hope you enjoyed this short focus tutorial. As always, thank you for joining me, and I will see you in the next one. JavaScript comes with a built-in date class that we can use to manage datetime values. We can create a new instance of the date object by using the date constructor. If we don't pass it any arguments, it's going to get initialized to the current date. For example, this particular piece of code is running on Friday, 10th March 2023. If we use the date toString method, it renders it out in the current time zone, but the date itself is actually independent of any time zone, and it is a particular point in time. It is actually tracked from UTC, and if we log it out by itself, we can see the UTC equivalent of this particular date value. Since we are in GMT plus 11, the 5 PM is going to be equivalent to 6 AM in UTC. Now this particular string that we are looking at is called the TZ string, as indicated by the presence of a T and a Z. Everything before the T is the year, month, and day, and after that we have the hour, minute, seconds, and milliseconds, followed by the Z. The TZ string is actually an ISO standard, so the date object also comes with a function called toISO string, which actually gives us the string that console.log is logging out. The date constructor also accepts values in the local time zone, so we can initialize a new local date. And here we are initializing a new local date for the year 2025, January 1st, with the hours, minutes, and seconds at 13, 30, and 15. This constructor should make obvious sense except for the one thing that you should always remember, which is that month within JavaScript is tracked with index 0. So January is going to be 0 as we are seeing over here, and December is going to have the value 11. The values that we are providing over here are in the local time zone, so the R13 for GMT plus 11 is going to be the UTC2, which is what we will see when we log this value out without applying any formatting or using the toString function. Just like other JavaScript objects created from JavaScript classes, the type of operator for this will give us the string object. And if you want to check if a particular object is an instance of date, we can use the built-in instance of operator. And of course, today is an instance of date. The date object provides various methods to access its subcomponents, which can be used to format the date to our liking. As an example, consider the new year 2050 in local time zone. Our mission, should we choose to accept it, is to display the date in local time zone with the format YYMMDD RR minute minute second second. Now, in order to pad the different values, for example, the day 1 to become 01, we are going to create a nice utility function that looks at the number. If it is less than 10, then it pads a 0 before it. Otherwise, it simply converts it to a string. With this simple utility in place, let's start creating our format function. Our function will take the date object and format it to the desired string. First up, we can get the 4-digit year from the date object by using the getFullYear method, and then we convert this numeric value to a string by simply using toString. Next, we are going to generate the month as and for that we use the date.getMonth function, and as we mentioned, the month is returned with a 0-based index, so we need to increment it by 1 for a more human presentable format. Once we have that value, we wrap it with our pad0 utility. The remaining portions of our format are going to be pretty easy. They are simply going to be padded 0 versions of the get date for the day, the get hours for the hour, get minutes for the minutes, and get seconds for the seconds. Once we have these values, the final result is going to be simply a concatenation of these into a nice string that gives us the desired format. Let's verify that this function behaves the way that we want by using the date value that we have, passing it to format, and then logging that out to the console. And if we run this code, you can see that it matches our expectations. We created a date in local time zone for 2050 New Year, and we get that presented out in the desired format for the user. A programming term worth knowing is epoch. It is the absolute point in time, which is midnight January 1st of 1970 at UTC 0. A key way that developers interact with dates is milliseconds since epoch, and this millisecond value is also called Unix time and also called the timestamp. I want to point out that I am in UTC plus 11, so here I am creating the new year 2030, passing in the R11, so it is indeed 00 in UTC. I can get the timestamp for this value by using the built-in date getTime method. We can actually create a new instance of the date by using this timestamp. Unlike the year, month, day version of the constructor, when we only pass in the timestamp number by itself is by definition from UTC, and the date constructor accepts it as UTC as well. So irrespective of what your machine time zone is, if you use the same number, you will get exactly the same string, which is 2030 New Year at UTC. A key use case for the timestamp value is that it allows you to do date math quite easily. As we mentioned, the timestamp value is in milliseconds, so if we wanted to calculate what date it would be one day before the new year 2030, we can actually do that by calculating a new timestamp and subtracting the required number of milliseconds for 24 hours. Once we have this new timestamp, we can pass it to the date constructor, and now of course we can look at what that value is going to be, and of course it is going to be 2029 December 31st. The JavaScript date object transparently accepts and presents values in the local time zone, but it also provides some utilities to create dates in UTC time and provide information about the local time zone. Here I am creating a date in the local time zone for 2025 New Year at 11 AM. Of course, since I am at plus 11, using the R11 gives us midnight at UTC. We can get the hours in the local time zone as we saw when we were doing date formatting by using the built-in getHours method, and of course, for this particular time, the local hours would be 11. The date object actually also provides us methods to get the UTC version of this time. For example, we can get the UTC hours, and of course, for this particular time, it's going to be 0. Just like get hours is local and get UTC hours is the UTC version, we have UTC versions of the other formatting functions as well. For example, get UTC date, get UTC minutes, get UTC seconds. As we can see, the date constructor takes values in the local time zone, but we can actually create a date at a UTC point in time as well by using the built-in date.utc static method. This method takes the same values as the date constructor, however it accepts them at UTC time zone, so here we are creating a date at UTC R0. This method also only returns a timestamp and doesn't actually create a date object, but as we know, we can convert a timestamp to a date object quite easily by passing it to the date constructor. Now time is absolute, and actually this is the same point on the dimension of time as R11 in our local time. So if we log it out, you can see that it is the same value as the one we created before. In addition to allowing us to create time in UTC values, JavaScript also offers us a simple method to get the time zone offset compared to UTC. There is a method called getTimeZoneOffset offered by the date object that gives us the difference of UTC minus local in minutes. Since we are in time zone plus 11, local is going to be ahead by 11 hours or 660 minutes, and therefore the minute offset local time zone is going to be minus 660. Use this value however you see fit. For example, let's just create a formatting function that displays the current time zone in plus or minus RR minute. We start off by creating a new date object and capturing the result of getTimeZoneOffset. If the offset is greater than 0, it means that local is less than UTC and therefore we will use minus, otherwise we will use the plus sign. The minute remainder after we remove the hours would simply be the absolute value of the offset remainder 60. And for the R value, we will simply divide by 60, take the absolute, and then use math.float to get rid of the remainder as that is already accounted for by the minutes. With these values in place, we simply return the formatted string sign hours:minutes. And now for the moment of truth, if we log out the formatted time zone for the current time zone of plus 11, we should see plus 11:0. And if we run this code, you can see that it matches our expectations. The date class comes with the static now method that provides the current numeric timestamp, and a common use case for this function is simple timing or performance testing. We've looked at timestamps before, and we know that we can get the current timestamp by creating a new date object and using the getTime method. The date object comes with a static now method that does exactly the same thing but with lesser, neater code. And of course, the value of the timestamp is the number of milliseconds since epoch. The dateNow method gives us convenient access to the number of milliseconds at the current point in time, so let's use it to create a nice utility function that can be used to measure the performance of a particular callback function. We take an approach string for logging and then a callback function. We start off by noting the current milliseconds using dateNow, and then we run through a loop for 100,000 times, each time invoking the passed-in callback. After this loop terminates, we note down the milliseconds again by using date.now, and now we have the start and the end, and we simply log out the approach took n-start milliseconds. For our example, we will compare the performance of the various ways you can create non-empty arrays of size 10,000. We kick off our test by first logging the array scar. One approach to creating a non-empty array is to pass the size to the array function and then use the fill method. Array size creates an empty array with empty slots which cannot be used for iteration. Invoking the fill method fills those slots up with undefined, so we can use functions like for each and map. Another approach to creating a non-empty array is to first create that empty array with array size and then using the built-in spread operator. Finally, after both of these functions return, we will log out the racing flag. Now let's kick it off and see which one wins. On my machine, fill takes about 1.7 seconds and spread takes about 1.4 seconds, and I've tested it on other machines as well. Spread is always faster than fill, and this is one of the reasons why in our JavaScript lesson on arrays, we recommended that we use the spread operator to create non-empty arrays. How JavaScript dates get serialized by JSON is actually quite nice, and it makes sending and displaying date values across devices in different regions quite simple for user interface purposes. Let's create a date in our local time zone of UTC plus 11 for 2049, January 1st, R11. Now, of course, if we log it out in our local time zone, you can see that it is 11 a.m. on January 1st, 2049, but we can also get the ISO version of this date, which is always going to be normalized to UTC. And of course, at +11 in our time zone, at UTC, it is going to be R0. The JavaScript date object also overrides the toJSON method to do exactly the same thing as the toISO string method. This means that when JavaScript serializes the date object to JSON, all dates get serialized to UTC tz date strings. And in reverse, we can actually create a date from the tz date string as well. So here is that same point in time. And of course, if we log it out, that is what we see. But if we use the toString method, we get that value formatted for the local time zone, which of course is going to be 11 a.m. Now that we are familiar with the toJSON method that gives us the tz string and the date constructor that accepts that tz string, let's look at a JSON example. We create an object Blade Runner that has a property year that points to the date 2049 New Year at 11 a.m. in the local time zone. If you want to send it off to a server using JSON, we can use json.stringify, and this gives us a string such that the year is going to point to the tz string that we saw before. There is no ambiguity about this particular point in time because it is always in UTC, and it doesn't matter where the server is located or where the user sent it from. On the flip side, when the server sends it out to someone, we would use a json.parse to parse it into an object. And of course, this particular string value is going to get serialized to a string, but we can convert it to a date object quite easily by passing this string to the date constructor. And now we have a date object that points to the same absolute point in time, and we can render it out however we want. For example, when we render it out using toString, it renders it in the local time zone, and of course, because we are 11 hours ahead, the user's perception of the time over here would be 11 a.m. In case you haven't noticed, I do have a passion for time because after all, time is the most valuable asset that we have. As always, thank you for spending your time with me, and I will see you in the next one. A common source of bugs in JavaScript is how this is handled. It can be simplified quite easily if you remember that this is the devil. Sorry, calling context. I meant to say this is the calling context. To demonstrate the calling context nature of this, consider a simple function that takes a value as a parameter, and in addition to logging the value, it also logs whatever is contained by the this keyword to the console. If we invoke the function by itself, in modern JavaScript, there's not going to be any special this that gets passed in, and in fact, it will point to the value that we've looked at a few times, which is undefined. Let's look at one way how we can pass a value in for this context if we wanted to. Consider a simple JavaScript object with the name property containing the string John. Just like we can specify what the parameter will be for a function when we invoke it, we can actually also specify what the this context will be by invoking the function using a special method that exists on all functions, which is call. Here we are saying that invoke the simple function, use the person object as the value for this, and use 456 as the argument, which of course is going to get assigned to the parameter value. In addition to how we can explicitly pass in a this value, this can get implicitly automatically passed in as well, depending upon how the function is invoked. To demonstrate that, let's add a property to the person object called simple, which points to the simple function. Now, if we invoke simple on the person object, whatever exists before the dot is what gets passed by JavaScript as the value for this. Since here we have person.simple, person is the value that gets passed for this to the simple function, and that is of course what we see within the logs and the program output. The passing of this based on the object that the function is invoked on is the main usage of this, and it is fundamental to how modern JavaScript classes work. We've looked at JavaScript classes and how they use the this keyword, but let's take a fresh look to add some additional depth to the meaning of this in classes. Consider a simple class called point that takes in its constructor the values of x and y. When the class constructor gets invoked by JavaScript, it actually creates a new object for that class and then passes it in using the this keyword. And all that we are really doing within this constructor is adding some stuff to this object. And this is the same object that gets passed back to us within our methods, so we can use it to access its values. For example, here we are reading this.x and this.y. When we create a new instance of the class, we do that with the new operator, and this is the thing that triggers JavaScript to create a new object and pass that into the constructor. Additionally, the constructor has an implicit return of this value back to the calling point, which of course is why we see that point is that object that we mutated to have x of 1 and y of 2. And just like any other JavaScript object, we can access these values using the dot notation. The real interesting thing to note over here is that when we invoke the log method on the point object, the value of this is actually getting passed simply because of the fact that we do point dot before we invoke the log method. This means that methods within JavaScript are actually quite lightweight, and they can actually even be shared by all of the instances of the class, because the correct instance will get passed in when we invoke the method on that instance. This is most commonly used in classes, but now that we understand that it is just a calling context that gets passed in, we can use this fact to create utility functions that can be attached to any object. Consider a simple growOlder function that simply increments the age property of whatever will get passed in as this. We can take the growOlder function and attach it as a member of any JavaScript object that we want, and that will actually automatically ensure that when the function gets invoked, that object will get passed in as the calling context. Here we've provided the growOlder method as a property of Jane as well as a property of John. So as an example, if we invoke it on Jane, who is currently 32, the age will get incremented by 1, and now when we read jane.age, we should see 33. And the same should be true for John as well. When we invoke growOlder on John, John will automatically get passed in as this, and John's age will get incremented from 21 to 22. And now if you run this code, indeed that is exactly what happens. We see the updated ages of 33 and 22. The JavaScript this will always be the calling context except for two scenarios. The first scenario is when we explicitly bind the value of this by using the function bind method. Consider a simple logname function that logs the value of the name property of whatever this gets passed in. Here we are using optional chaining to look up the name property, so if this is undefined, then the whole chain will resolve to undefined. If we invoke logname by itself, of course there will be no this, which means that undefined is what will get logged to the console. If we create two objects with the logname method, one with the name Jane and one with the name John, when we invoke jane.logname, then Jane is what gets passed in, and that is what we will see on the console, and the same will be true for John as well. John will get passed in and we will see the log John. We can actually create a standalone version of the function that always passes in a particular value for this by using the function's built-in bind method. Here, logname Jane is a modified copy of the original log function, such that whenever we invoke logname Jane, the value of this will always be Jane. Now this is a copy of the original function. The original function is still completely the same as it was. It will happily log the value of undefined. Since logname Jane is bound to Jane, it will always use Jane as the calling context. So even if we try to attach it to a different object with the name Jack and try to invoke it on the Jack object, it's not going to matter. Jane is what's going to get passed in, and that is what we will see on the console. Beyond the bind method, the other scenario in which this is not the calling context is arrow functions. Arrow functions capture this from the lexical context, which is just a fancy term for the surrounding scope. Consider a simple auth class that has a member is logged in, which we initialize to false, and then we have utility methods login, which set it to true, and logout, which set it to false. If we create an instance of auth and then we invoke the login method, the auth object will get passed into login, and auth.isLoggedIn will get set to true. And of course, if we do auth.logout, then again auth is what gets passed in, and auth.isLoggedIn is what gets set to false. If, however, we manage to invoke these functions without using auth. For example, we store a reference to the login method into its own variable and invoke it that way, then this auth object is not the thing that will get passed in as this. Undefined is what will get passed in as this, and it will cause a runtime error. And you might think that, hey, of course, this is never going to happen on me. I'm always going to do auth.login. But as we've seen before, this implicit assignment of a method to a variable is exactly what happens when an argument gets assigned to a parameter. So if we decide that we want to log out after 1 second using setTimeout is not actually going to invoke auth.logout. It's simply going to invoke the logout function by itself, just like we were invoking the login function by itself. And of course, this is also going to result in a runtime error. And this is where the arrow functions come in. We can actually replace our methods with instances of arrow functions, and arrow functions automatically capture the value of this from the surrounding scope. So in this particular case, they will capture the instance of the auth class, which means that this no longer depends upon the calling context and it will always point to the auth instance. With this simple change in place, it doesn't matter how we invoke the login method or how we invoke the logout method. So our independent call for login will also work. We should see is logged into true. And similarly, our call to auth.logout made by set timeout will also work. So if we set another timeout for 2 seconds and logout auth.isLoggedIn, we should see false. And indeed, when we run this code, that is exactly what we see. There is a slight performance difference in using a method versus using an arrow function as an instance property. The method is shared by all the instances, which means, of course, that it needs to be called correctly so that it gets the correct instance, whereas an arrow function captures this correctly and is not shared between the different classes. However, the performance difference in modern JavaScript is pretty negligible. In addition to using arrow functions when declaring class methods, we can also use arrow functions when creating callbacks inside these methods to ensure that this is preserved. Let's expand our simple auth class that manages an isLoggedIn boolean with the new method called logoutSoon. This method first checks if the user is logged in, and if they are, sets a timeout to log the message logging out and then invokes this.logout. Let's test it out by invoking auth.logoutSoon and then set a timeout for 2 seconds, that is 1 second after the logout should have happened, to log out the auth.isLoggedIn value. If we run this code, we should see the auth.isLoggedIn value of true, then we should see the message logging out, and then we should see auth.isLoggedIn value of false. The observant among you might already know that this particular piece of code is not going to work, and no surprise, it does not work. It fails to call this.logout because, as you might have guessed, this is going to be undefined. The function that is being invoked by setTimeout has no magical knowledge about the this context, but notice that this is available just one line before. So we can actually use our magical arrow function once more to capture the value of this from the surrounding context, and that will ensure that this within the set timeout is going to point to the this within the logoutSoon method, and therefore this.logout is going to work just like this.isLoggedIn is going to work. And now if we run this code, it executes without any issues. We see the logged in true, we see the logging out message, and then because this.logout was successfully called, the logged in value turns to false. A common use case for this is to create classes which offer what is called a fluent API. A few built-in JavaScript APIs do this, and we can achieve the same effect ourselves quite easily by simply returning this from our methods. Consider a simple calculator class that starts off with an initial value which we store within the value property of the object that gets assigned to us with this. We create a method add that accepts a number n and then adds the value with that number, but then we do something interesting. We return the value of this from the add function. It makes the object that we are dealing with immediately available as the response for the add method. We can create other fluent methods on our calculator class as well. For example, here we are creating subtract that simply subtracts from the value and then again returns this. Let's demonstrate the fluent usage of this API by calculating the result of 1 plus 3 minus 2. We simply create an instance of the calculator passing in the value of 1, then we invoke add with the number 3, then subtract with the number 2, and then read the final value as the result. Because the new operator automatically returns this, we can chain off of that to invoke add, and within add we are explicitly returning this, which means that we can chain off of that to invoke subtract, and finally from subtract we also return this, which means that we can chain off of that to read the final value. And of course, if you run this code, no surprises, it calculates the correct result. The result of 1 plus 3 minus 2 is going to be 2. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. We've looked at the main use case of JavaScript template literals, also called template strings, which is smooth string concatenation. You can actually provide your own custom function before a template string to completely customize the interpolation, and this is called a tagged template. Here we have two simple variables, one for a person pointing to Mike and one for the age pointing to the number 28. We can put them in a simple string by using template literals, and no surprise, the output will match what we expect. we can actually put an identifier or honestly any expression that evaluates to a function before a template literal to create what is known as a tagged template. In syntax terms, the identifier that we are using over here is called the tag function. We define it just like any other function in JavaScript, and there are two key parameters for a tag function. The first is an array of strings, which contains the string portions of the tagged template. So for our example, it will contain the person, the age, and the full stop strings. And then the remaining parameters to our tag function will contain the expressions that get passed in. And here we are consolidating all of them into a single array by using the JavaScript REST parameter as indicated by the triple dots. So for our example, it will be an array containing the person string and the age number. Note that the original type of the expression is preserved. So since age is just a number, we get a number, we do not get a string version of that number. Anything that we return from this function will be the result of the tagged template. As an example, we can simply concatenate the strings and the expressions the same way the built-in function would do, and if we log out the final tagged result, it should match what we got in the simple version. And no surprise, if we run this code, the contents of the simple and the tagged are the same final string. Let's take a deeper look at the parameters of tagged templates to get a deeper understanding of the strings and the expressions that get passed in as the arguments. We create three simple variables x, y, and z, 10, 20, and 30 that we will be using for our expressions, and then we create a simple tag function which we will use to debug the strings and the expressions that get passed in. Let's run our first experiment. We pass in a simple string containing three expressions x, y, and z. What do you think will be the strings and what do you think will be the expressions? What might surprise you that in addition to the three expressions, we will also get passed in 4 empty strings. That is because we still have 4 empty strings that surround these 3 expressions. To simplify it further, if we only have a single expression, we essentially have 2 empty strings that surround that expression. Additionally, all expressions get evaluated before they get passed in, so if we have an expression x plus y plus c, we will actually get passed only one expression, which is the final result of this, which is 60. And of course, at this point, it should make obvious sense that if we only have an empty string, we will still get passed a string, and since this string has no expressions, the expressions array is going to be empty. Let's implement the same functionality as the built-in template string that works with any number of arguments. And this will give us the basic structure to easily create custom tag functions. We create this tag function called interpolate that takes the strings and the expressions, and then we simply use string.reduce to generate the final result. We use the strings array because, as we saw, we are guaranteed at least one item. In each iteration of the reduce, we will get back the currently computed result, the string that we are currently looking at, and the index for that string. As we know, we may or may not have any further expressions to look at, so to make sure, we check if I is less than the expressions.length, and if it is, we have an expression and we pick it up from the expressions array. Otherwise, for the expression, we default to an empty string. Finally, for the updated result, we will have the previous result plus the current string plus the current expression, and to kick everything off, we provide an initial seed value of an empty string. And this gives us exactly the same functionality as if we had never used this interpolate function. And to demonstrate that, we create 2 simple variables, pineapple and capsicum, and generate 2 strings, the first one without using the tag, and then another one using this tag. And now if we run this code, you can see that the output from both of the calls is exactly the same. The difference here is that now we have a framework to do any customization that we want to. For example, we can turn any of the passed in expressions to their uppercase equivalent with a simple call to toUppercase. And now if we run this code, we get pineapple and capsicum in capitals with our custom tag function. The return value from a tagged template function doesn't have to be a string, and really, tagged templates open up a whole avenue for creating custom domain-specific languages. As you might know, JavaScript does have a star operator, also called the exponent, so 2 to the power of 4 is 16. But what if we wanted to use the caret for the same purpose? Unfortunately, the caret operator does exist within JavaScript and it's a bitwise XOR, but let's be fancy and create our own custom DSL in which caret has the same meaning as star, that is power. We create our own calculate tag function which takes the strings and the expressions, and then within the strings that get passed in, we replace any existence of the caret with the star, and this allows us to pass the final resulting string directly to JavaScript eval function to get the evaluated numeric result. So for our simple example where we have a pointing to 2 and b pointing to 4, if we calculate a caret b, we should get back the result 16, and indeed that is what we see in the program output. The domain-specific nature of tagged templates is extremely powerful and used quite effectively in modern JavaScript ecosystems, for example GraphQL and lit-HTML. As always, thank you for joining me, and I will see you in the next one. Before we can really take advantage of the wonderful modern features of async await, we need to get a firm understanding of the built-in JavaScript promise class. We can create a promise in JavaScript by using the built-in promise constructor. The promise constructor takes an executor function as an argument and then invokes that with two parameters. The first one is resolve and the second one is reject. And these two arguments are what will determine the eventual fate of the promise. Within the executor function, we can do some async work and then eventually invoke either resolve or reject. The resolve function can be used to provide a value which will fulfill the promise with that value, and the reject function can be used to provide an error which will result in the promise being rejected. In either case, whether the promise is fulfilled or rejected, it is considered settled, and we can actually subscribe to that event as well by using the finally method. Right now, we are not invoking resolve or reject, and this will put the promise into a pending state, and none of the then, catch, and finally method callbacks will get invoked. Let's change that by first doing some async work and then settling the promise. We don't have to do asynchronous work within the promise constructor, but really the ability to do so is the reason why we want to use the promise. Here we are setting a timeout of 1 second and then resolving the promise with the value of the string arrived. Once the resolve gets invoked, the promise will be considered fulfilled, which is a subset of the category called settled, and we will see fulfilled with the value that we provided along with the string settled on the console. The unhealthy fate of a promise is that it might get rejected, and we should always reject with an error object. So we invoke the reject method, pass in an error object with a nice descriptive string, and this will result in the promise getting rejected with the error, which in turn will invoke the catch handler. And since we are using an error object, we get a nice stack trace for the origin of the error. And just like fulfilled, rejected is a final state of the promise, which means that the finally callback will also execute and we see settled on the console. So in short, promise is simply an object that is used to manage async tasks that start off as pending and then settle with either a status of fulfilled or rejected. Promises come with simple static methods that allow you to create promises which immediately resolve or reject the promise with a given value. For example, we can easily create a function ourselves called resolve that takes a value, then returns a promise which we immediately resolve to that value. Similarly, we can create a function called reject that takes an error and then returns a promise which we immediately reject with that error. So if we create a promise with the resolve callback, it will immediately get fulfilled, which means that the then callback will get called. And similarly, if we create a promise with reject, it will immediately get rejected, which means that the catch handler will get called. And having these utility functions can really help understand some of the behaviors of promises, but fortunately we don't have to create them that often, as JavaScript comes built in with static methods promise.resolve and promise.reject that offer very similar features and even do a few performance optimizations. As an example, if you give promise to promise.resolve, it just gives it back to you, it doesn't wrap it up any further. Our versions of these functions as well as the promise static versions of these functions will log exactly the same thing, which is success and fail, and we can verify that in the program output. A key feature of JavaScript promises is how the promise then method chains together. It even allows transparent unwrapping of promises, which means that we don't have to untangle a mess of nested then calls. We start off our chain with a simple promise, which we resolve to the value of 1, 2, 3, which means that the then callback should be called with 1 through 3. Each then callback actually creates a new promise, and that promise will in turn resolve with whatever value we return from our then call. So as an example, if we return the value 456, the next then callback will get the value of 456 because that is what this new promise will resolve to. Now again, this then is actually creating a new promise, and whatever value we return from here will determine the fate of that promise. We can actually return a promise from our then callback, and that will actually tie the fates of our return promise and the promise created by then to be the one and the same. The promise we are returning is going to resolve to 789, and the promise created by then is going to resolve to the same value, which is what we will see in the next then callback. Let's run this code and you can see that it works as expected. The first time you see this collapsing of promises, it can look a bit weird, but this is a fundamental part of the power of promises. Notice that we've been using the term fulfilled a few times instead of resolved, and the reason is that a promise can be resolved to another promise, at which point its fate becomes dependent on the other promise. If the other promise gets fulfilled, our promise gets fulfilled. If the other promise is rejected, our promise is rejected. We create this utility function called resolved that takes a value and then returns a promise that is clearly resolved to that value. We have another utility function that returns a promise that just chills around for 1 second and then becomes fulfilled. And very similar to this, we have a utility which returns a promise which again just chills around for 1 second and then becomes rejected. Let's create two promises, alpha and beta, and both of these promises are clearly resolved because their resolve method has been invoked. As we have been seeing, when we invoke resolve with a value that is not a promise, the promise immediately moves into the fulfill state and the then callbacks get called. However, when we resolve a promise to another promise, as we are doing over here, then the fate of the promise becomes dependent upon the passed in promise. So both alpha and beta are clearly in the resolved state, but they haven't settled yet as their fates are dependent upon the past and promises, and eventually once their fate is decided, alpha will get fulfilled and beta will get rejected. And we can verify that by attaching then and catch to both alpha and beta and logging out the results, and as you can see, alpha gets fulfilled and beta gets rejected. So to recap, with the non-promise value, a resolved results in an immediate fulfilled, but with the promise value, the fate is dependent upon the past and promise. Even without async await, promises by themselves help clean up the callback hell, also called the callback tower of doom. And the critical feature that offers this is the fact that the promise then function automatically waits for any past promise to settle before continuing. Consider the simple task of creating a run function that takes a callback and then simply calling the callback 3 times each time after a delay of 1 second. With the knowledge that we already have, it's quite easy to do with the set timeout. We set up a timeout, invoke the callback, then set the new timeout, invoke the callback, and then set the final timeout and invoke the callback. And of course, all of these timeouts are going to be for 1 second. And we can prove that it functions the way it should by giving it a simple callback that logs high, and we see the 3 high calls each time after 1 second. And I think you can see this sideways tower of doom that is forming because of this nested callback hell. So let's take a look at how we can achieve the same thing more cleanly with promises. Since we have a requirement to wait a particular amount of time, we'll just create this utility function that takes a number of milliseconds and then returns a promise which we will eventually resolve after the desired number of milliseconds using set timeout. Let's recreate our run function that takes the callback as an input, and we will kick things off by creating the promise that will wait for 1 second before resolving, and then we will invoke the callback, and then we can just return a new promise that will again wait for 1 second, and then invoke the callback, and finally repeat the process one more time. The automatic promise unwrapping and chaining just makes this code much neater than the set timeout version. Let's demonstrate this run function by giving it a callback that logs hello to the console, and if we run it, we see hello after every second for 3 times. Perhaps the most amazing feature of promises is its graceful error handling and how it cascades through the promise chain. Consider the simple promise chain where we start off with a promise that resolves to high, and then we log out this value and then return a new promise which will resolve to hello, and then we log out that value and then eventually add a catch handler that will log the message of any error that it might receive. Of course, there are no errors in the code right now, so if we execute it, we see then hi, then hello, and we do not see any catch. It should come as no surprise that if we throw an error in the final then call, it will result in a promise rejection, and our catch handler will get called, and we can verify that from the console. But what might actually surprise you is that this catch handler is actually handling the error that can happen anywhere within this promise chain. As an example, if an error happens in the promise constructor that will result in that promise getting rejected, the error will cascade all the way to the catch callback and all the intermediate promises will also fail. Similarly, if an error happens in the first then callback, the remaining promises after that will get rejected and we will jump straight to the catch as we can see in the output. Here, we are the ones that are throwing an explicit error, but an error can be thrown by the JavaScript runtime as well. As an example, if we try to use a variable that hasn't been defined called magic, then of course we're going to get a reference error and that error cascades all the way to the catch. Additionally, at any point if we return a promise, then the fate of the remaining chain becomes dependent upon that promise. For example, here we are returning a promise that will reject. So of course, just like any other error, the remaining chain will reject and we will jump straight to the catch, as we can see in the program output. This graceful error handling cascade means that we don't have to litter our code with validation, and this is also what makes it possible to easily map promises to the JavaScript try catch with async await. In modern JavaScript, understanding the concept of promise fates, how the promise then chain works, and how the catch cascades is sufficient to start using async await, which really takes the utility of promises to the next level. As always, thank you for joining me, and I promise to see you in the next one. JavaScript was popular even before async await, back when life was full of callbacks. But now async await is fairly mainstream and it's actually quite easy to use, and at its core, we have the async keyword. To specify that a function is an async function, we use the async keyword, and you can use it pretty much whenever you would create a function, for example, a function declaration, a function expression, even arrow expressions, and even class methods. A key thing to remember with async functions is that they always return a promise. So even though these functions don't have a return statement, we will still get back a promise when we invoke them. This promise will resolve based on the returned value, and as we know, when a standard synchronous function does not have a return statement, JavaScript still returns the special value of undefined, so all of these promises will actually resolve to that same special value of undefined. We can verify this behavior by running this code, and as you can see, we get back 4 promises that resolve to the value of undefined. Just like when we resolve one promise to another promise, the fates of the two become one and the same. It also applies to async function return values. When an async function does not return a promise, for example, here we are returning a simple string, then the promise from the async function immediately resolves to that value. However, when an async function does return a promise, then the fate of the returned value is going to be the same as the fate of the returned promise. In this particular case, the promise that we are returning gets fulfilled with the string value of fulfilled. So of course, that is what we will see in the then callback for the returned value. However, if the promise that is returned from the async function gets rejected, then the returned value will also get rejected. And here we are handling the scenario with a simple catch and logging out the error message. So now if we run this code, we see the simple value immediately, then fulfilled gets resolved, and then the rejected value goes into the catch. Async functions gracefully handle all errors that occur inside of them and turn them into nice and easy to deal with rejected promises. To recap, when we have a standard synchronous function and we make a mistake, for example, we are invoking a function that does not exist, magic is not even defined. If we invoke it, then it will result in a synchronous throw from the JavaScript runtime, which must be caught with a try catch. Async functions, however, always return a promise, which means that they do not throw an error synchronously, so it is perfectly safe to call an async function and store the value in a result. And as we've seen, what we really get back is a promise of the result. So if an error does occur in the execution of the async function, what happens is that the promise that is returned is what gets rejected. So in this particular case, the result promise will get rejected with an error by the JavaScript runtime, and of course the error message will be the same as what we saw before, which is magic is not defined. Now of course, magic is not defined is sort of a coding error, and the JavaScript runtime is what is throwing that error, but we can throw an error ourselves as well using the throw keyword, and this too will get converted into a promise rejection. This is why we have always been using an error object whenever we are rejecting a promise, because a promise rejection is an asynchronous version of a synchronous throw, and we've already discussed during error handling that you should always throw an error object and not some random string. Now let's run this code to verify it works as expected, and of course it does. We have our synchronous error caught with the message logged, we have our asynchronous errors caught as promises and logged using catch handlers. Now that we understand how the async keyword works, we can take a look at the await keyword and how it behaves in an async function. We start off with a simple async function that allows us to use the await keyword, and to kick us off, let's look at when we use the await keyword on something that is not a promise. There is absolutely no point in doing this. This await operator is completely useless. It just gives back whatever is passed in, and as you will see, it will be exactly the same as the original string. The real use case of the await operator is when we use it on something that is a promise. For example, here we have a promise that gets fulfilled to the string fulfilled after 2 seconds. If we use the await keyword before this promise, the code execution within this async function will essentially pause till the promise fate is settled. In this particular case, this promise will get fulfilled and the await keyword will give us back the fulfilled value. So for this particular example, if we log out the fulfilled result, we should see that string fulfilled. Let's create another promise, but this time we will make this promise reject with an error after 2 seconds. If the promise that we are awaiting results in a rejection, then the JavaScript runtime will throw a synchronous error into this async function. The thing that will be thrown will be exactly the same as the value used for the promise rejection. If we don't catch that error, it will go all the way to the async function result, which of course will be that rejection value, but we can catch it within an async function by using the standard try catch. Here we are using await on the promise that will eventually get rejected, but we have been smart enough to wrap it up within a try. And of course, as soon as this error gets thrown, no further statements within the try will execute and it will jump straight to the corresponding catch block. So within our catch, we should see that error message, which of course is that string rejected. If you run this code, you can see that for not a promise, there's no point in using the await keyword. Then we wait for 2 seconds till the second promise gets resolved and we get back the result. And then we wait 2 more seconds till the next promise gets rejected and we catch that within our catch handler. We've looked at how even promises by themselves clean up the callback hell, and async await just takes that to the next level and brings the true convenience of everyday synchronous programming to the async world. Consider the simple task of creating a function that takes a callback and then it should call it 3 times each time after a delay of 1 second. We create a simple utility function that we've seen a few times, which simply takes a millisecond value and then returns the promise, which we eventually resolve after those milliseconds have passed by using a set timeout. Now let's work on the function that meets the requirement specified. Of course, it's going to be an async function that's going to take that callback. And now we can just create a promise using our wait utility that will resolve after 1 second and use the await keyword to pause execution till that promise resolves. Once that promise resolves, we will invoke our callback and then we will again wait for 1 more second, then again invoke the callback and then do it 1 more time. Let's demo this main function by giving it a simple callback that logs the message hi, and now when we run this code, we get that hi message each time after a delay of 1 second. You might argue that what's the big deal? I could do this pretty easily with the promise then chain, but what async await really unlocks is the ability to do any synchronous programming you want, like a for loop that does the same thing 5 times or any number of times that you provide, and in each iteration we have that simple await for 1 second followed by a call to the callback. With async await, you almost don't even have to think about the fact that you are writing asynchronous code. Async await has made asynchronous programming extremely easy, and it's most apparent when working with backend APIs over a network. For this demo, we will use the simple API provided by GitHub, which is api.github.com/users, and you can provide any user ID. For example, here I'm providing my own, and you can see the sample response. And there is a lot of stuff on screen, but let's focus in on how we could read the name, the Twitter username, and then make another request to the organization's URL to read all the organizations that this particular user belongs to. We will be working within an async main function, and we start off by using a built-in API called fetch, and this API is available on browsers as well as Node.js. It takes a simple URL string and returns a promise that eventually resolves to an HTTP response object. As we know that the body of this response is JSON, we can actually convert it into a JavaScript object by using the JSON method on the response object, which again returns a promise, so we simply await that as well. This gives us a JavaScript object version of the JSON payload that we were looking at, and we can easily read the name and the Twitter username properties. We can also read the organization URL, and let's make another fetch request using the organization URL to get another orgs response, and again parse that from JSON by using the JSON method, and this time we will get back an orgs array. Each item in the array has a login member, which is basically the name of the organization. So for the organizations, we simply log out the individual org.login properties. And now for the moment of truth, let's open up the terminal and execute this code using Node.js. And as you can see, we can read the name, the Twitter, and the organization names. And this was all pretty simple thanks to promises, the fetch API which works on promises, and async await. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. We've looked at the main use case of JavaScript template literals, also called template strings, which is smooth string concatenation. You can actually provide your own custom function before a template string to completely customize the interpolation, and this is called a tagged template. Here we have two simple variables, one for a person pointing to Mike and one for the age pointing to the number 28. We can put them in a simple string by using template literals, and no surprise, the output will match what we expect. We can actually put an identifier or honestly any expression that evaluates to a function before a template literal to create what is known as a tagged template. In syntax terms, the identifier that we are using over here is called the tag function. We define it just like any other function in JavaScript, and there are two key parameters for a tag function. The first is an array of strings, which contains the string portions of the tagged template. So for our example, it will contain the person, the age, and the full stop strings. And then the remaining parameters to our tag function will contain the expressions that get passed in. And here we are consolidating all of them into a single array by using the JavaScript REST parameter as indicated by the triple dots. So for our example, it will be an array containing the person string and the age number. Note that the original type of the expression is preserved, so since age is just a number, we get a number, we do not get a string version of that number. Anything that we return from this function will be the result of the tagged template. As an example, we can simply concatenate the strings and the expressions the same way the built-in function would do, and if we log out the final tagged result, it should match what we got in the simple version. And no surprise, if we run this code, the contents of the simple and the tagged are the same final string. Let's take a deeper look at the parameters of tagged templates to get a deeper understanding of the strings and the expressions that get passed in as the arguments. We create three simple variables, x, y, and z, 10, 20, and 30 that we will be using for our expressions, and then we create a simple tag function which we will use to debug the strings and the expressions that get passed in. Let's run our first experiment. We pass in a simple string containing three expressions x, y, and z. What do you think will be the strings and what do you think will be the expressions? What might surprise you that in addition to the three expressions, we will also get passed in 4 empty strings. That is because we still have 4 empty strings that surround these 3 expressions. To simplify it further, if we only have a single expression, we essentially have 2 empty strings that surround that expression. Additionally, all expressions get evaluated before they get passed in, so if we have an expression x plus y plus c, we will actually get passed only one expression, which is the final result of this, which is 60. And of course, at this point, it should make obvious sense that if we only have an empty string, we will still get passed a string, and since this string has no expressions, the expressions array is going to be empty. Let's implement the same functionality as the built-in template string that works with any number of arguments. And this will give us the basic structure to easily create custom tag functions. We create this tag function called interpolate that takes the strings and the expressions, and then we simply use string.reduce to generate the final result. We use the strings array because, as we saw, we are guaranteed at least one item. In each iteration of the reduce, we will get back the currently computed result, the string that we are currently looking at, and the index for that string. As we know, we may or may not have any further expressions to look at, so to make sure, we check if I is less than the expressions.length, and if it is, we have an expression and we pick it up from the expressions array. Otherwise, for the expression, we default to an empty string. Finally, for the updated result, we will have the previous result plus the current string plus the current expression, and to kick everything off, we provide an initial seed value of an empty string. And this gives us exactly the same functionality as if we had never used this interpolate function. And to demonstrate that, we create 2 simple variables, pineapple and capsicum, and generate 2 strings, the first one without using the tag, and then another one using this tag. And now if we run this code, you can see that the output from both of the calls is exactly the same. The difference here is that now we have a framework to do any customization that we want to. For example, we can turn any of the passed in expressions to their uppercase equivalent with a simple call to toUppercase. And now if we run this code, we get pineapple and capsicum in capitals with our custom tag function. The return value from a tagged template function doesn't have to be a string, and really tagged templates open up a whole avenue for creating custom domain-specific languages. As you might know, JavaScript does have a star operator, also called the exponent, so 2 to the power of 4 is 16. But what if we wanted to use the caret for the same purpose? Unfortunately, the caret operator does exist within JavaScript and it's a bitwise XOR, but let's be fancy and create our own custom DSL in which caret has the same meaning as star, that is power. We create our own calculate tag function which takes the strings and the expressions, and then within the strings that get passed in, we replace any existence of the caret with the star star, and this allows us to pass the final resulting string directly to JavaScript eval function to get the evaluated numeric result. So for our simple example where we have a pointing to 2 and b pointing to 4, if we calculate a caret b, we should get back the result 16, and indeed that is what we see in the program output. The domain-specific nature of tagged templates is extremely powerful and used quite effectively in modern JavaScript ecosystems, for example GraphQL and lit-HTML. As always, thank you for joining me, and I will see you in the next one. In order to truly appreciate JavaScript generators, we need to look at iterators, and fundamentally an iterator is an object that has a next method, and this next method should return something with two properties, a value and a done boolean. Let's demonstrate the usage of an iterator by creating a function that will give us one, and of course the iterator is simply an object that has a next method, and whenever we invoke the next method we should get back a value and a done boolean. An excellent candidate for an iterator is the return value of a range function, which sadly is not built into JavaScript, and this is a function that should take a start value, an end value, and a step size, and should start iterating at the start and then continue each time incrementing with the step till the value becomes more than the end. We kick off the value with the provided start, and then we return an iterator, which again is simply an object that has a next method. We should stop returning values when the value becomes greater than the targeted end, and we can determine that as the done boolean where value is greater than end. If this done becomes true, we simply return an object where value is undefined, and of course done will be true. Otherwise we create a new result object with the current value, and of course the done boolean which will be false. And then for the next iteration, which may or may not happen, we want to increment the value with the provided step. With this value maintenance out of the way, we can simply return our result object. And that's it, we successfully manually created our first JavaScript iterator. Let's create an iterator to play around with it by invoking the range function, passing in a start of 0, an end of 2, and the default step of 1. The first time we invoke the iterator next method, we get back an object with the value which is the same as the start, that is 0, and of course it is not done yet. For 2 more times when we invoke the next method, we get the value incremented by 1 and done will still be false, but after that the value becomes greater than the end, and therefore we start getting that object value undefined and done true. This means that the iteration is complete and we should really stop bugging the iterator for more values. Iterator by itself is a very simple protocol and becomes really powerful when we put an iterator in a well-defined place inside an object, and that is what makes an object iterable. An iterable is an object that will have a property defined by the well-known symbol symbol.iterator, and this property will be a function that should return something that follows the iterator protocol. We've looked at symbols and well-known symbols before, and the symbol.iterator is simply a well-known global symbol that has special meaning within JavaScript. And in fact, this is the heart of how iteration works for many of JavaScript's built-ins. As an example, we know that a JavaScript array is iterable using a for-of loop, and the secret reason why is simply because array defines a property symbol.iterator which points to a function that will give us back an iterator. And in fact, we can go really crazy and actually invoke it ourselves if you wanted to get back an instance of the array iterator. And if we invoke the next method a few times, you can see that it behaves in the same fashion as our range iterator. Every time it gives us a new value and done false till it is out of values, at which point it gives us value undefined and done true. And this magic of getting the symbol.iterator function, invoking that, getting the iterator, and then looping over the results is exactly what happens behind the scenes when we use a JavaScript for-of loop on any given object, including arrays. A fun fact worth knowing is that we can actually iterate over a JavaScript string as well. So if we use a for-of loop with this message variable, we get back the individual characters in individual iterations, which of course will be H, O, L, and A. And no surprise, message does have a property defined for symbol.iterator, which is a function which we can invoke to get the iterator, and as we invoke next again and again, we get back the individual characters with done false, and when we run out of characters, we start getting value undefined done true. It is worth pointing out that we don't have to return value undefined when done is equal to true. It's just a nice convention to follow. You could pretty much drop the value as well when done is true, and it would still work. Now that we understand the iterator protocol and how a well-known symbol iterator can make an object iterable, we can actually build our own custom iterables. To recap, an iterator is simply an object that has a next method which gives us back a value in a done boolean, and an iterable is simply an object that has a well-known property symbol.iterator, which must be a function that gives us back an iterator. Armed with this knowledge, let's uplift our range function to return an iterable instead of returning a simple iterator. We kick things off as normal. We have the range function which takes a start, end, and a step, and we initialize the value that we intend to return using the start, and then we create our iterator, which is simply an object that has a next method, and the next method returns results such that they have a value and a done boolean. The object contained within the iterator is exactly what we previously returned when our range function was only returning an iterator. But now we've kicked things up a notch and we are going to return an object that has a well-known property symbol.iterator, which is going to be a function that returns the iterator. And that's it. We've actually created something that can be used in the built-in iteration processes within JavaScript. As an example, we can use the for-of loop on a range of 0 to 10 with a step size of 2, and we should get back the individual values, which are 0, 2, 4, 6, 8, and 10. And if we run this code, that is exactly what happens, as we can see in the program output. The most common iterable we use in JavaScript is the built-in array. So of course, JavaScript has convenient ways to convert any iterable into an array. So we've looked at this function which returns an iterable because it returns an object that has a property symbol.iterator, which is a function that gives us an iterator. If you wanted to convert the result of a range invocation into an array, we could do that quite easily by creating an array, looping through the results using for-of, and pushing the individual values into the array, and this would work, but as you would expect, there are better ways to do this. JavaScript array comes with a built-in function called from, which takes an iterable and returns an array. So you could use this function to take an iterable and convert it into an array, but there is actually special syntax built into the language that makes this even more concise. And we've actually already looked at this when we were looking at arrays, and the syntax is the array spread operator. And we've used these triple dots to spread one array into another, but underneath it doesn't really care if what you pass in is an array or any other iterable. Underneath it simply uses the iterable protocol, so it will work with our range function as well. And as you would expect, all of these approaches return the same result, but the spread operator is the way to go. What often confuses people is the fact that you can actually create an object that is both an iterator and is iterable. And that's actually important because JavaScript generators create such objects. But it's actually quite easy to do that ourselves even without generators. So we start off with a clean slate of the range function and we've defined the next method in isolation. Let's look at how we can create an iterator, then an iterable, and then combine the two concepts. For an iterator, it's going to be simply an object that has this next method. And then for an iterable, it's going to be an object that has the well-known property symbol.iterator, which is a function that gives us an object which has that next method. So there's actually no conflict between the two, and we could create an iterable iterator that has the properties of the iterator and the properties of the iterable. And there's actually even an easier way to do this by using the JavaScript this keyword, which we looked at in a previous lesson. Because the object that contains the symbol.iterator already has that next property, we can simply return that object by using the this keyword. And now our range function is something that returns an iterable iterator. Let's play around a bit with the result of a simple range call. For people that want low-level access, they can do that by using the result.next method. They get back the values in the done and they can log out the values as long as the done is still false. But of course, most people will not want this low-level access provided by the iterator and instead use the result as an iterable. As an example, using the spread operator to take that iterable and convert it into an array. In terms of behavior, both of these things work with the result. It is an iterator and it is an iterable. And the only reason why we are covering this is because this is the kind of object that a generator function returns. There is a lot more to iterables, but honestly, you already know more than you need to because you will most likely be using them transparently with generators, which is what we will look at in a future tutorial. As always, thank you for joining me and I will see you in the next one. JavaScript generators make it super easy to create iterables with special syntax for defining the generator using function star and returning individual values with yield. Here we are defining a generator called simple, and what makes it a generator instead of just another function is the fact that we are using function star, where star is also called the asterisk character. A generator is essentially a function that can be paused every time we return a value, and the way we return a value is with the yield keyword. So when someone asks this function for values, it will first give back the numeric value of 1 and then essentially pause the function execution. Execution will resume when the next value is requested, and here we are going to yield 2. Then execution will again pause, and when the next value is requested, execution will resume and we will yield the value of 3. And then again the execution will pause, and when the next time the value is requested, as we do not have any more statements, the generator will then terminate. You invoke the generator like a standard function and it gives back a generator object. An individual generator object essentially controls the particular execution of the generator function. The generator object actually follows the iterator protocol that we've looked at in a previous lesson, and what that means is that it has a next member which is of a type function. And we can actually get the individual values back from the generator by invoking next every single time we need a new value. Each invocation of next gives us back a result that has a value, and of course the first value that we are yielding here is 1, so value is going to be 1, along with the done boolean, which will be false as long as there are more statements to execute within the generator. So for our particular generator, if we invoke next again, we get back the value 2 done false. We invoke it again, we get back the value 3 done false. And now the generator execution has completed, so we get back the value undefined and done true. The main use case for the generator is not the fact that it follows the iterator protocol, it is the fact that it follows the iterable protocol. So let's invoke the generator again, and this time store the generator object that is returned into a variable called iterable. And as we saw in a previous lesson, we can actually prove that it is an iterable because it has a well-known property symbol.iterator, which is of type function. We've seen how JavaScript has special syntax for using iterables. For example, we can use them with the JavaScript for-off. And of course, if we for-off on this particular generator object, we get back the values that we saw before, which is 1, 2, and then 3. So to recap, we invoke the generator like a standard function, but instead of giving back a result, it gives back a generator object. And this object is both an iterator and it is iterable, and most commonly you would use it as an iterable. With generators, it's really important to understand how the order of execution works, so let's add some logs to monitor everything that we can about the generator. We create a simple generator and add a log statement before and after every yield statement. When we invoke the generator, we immediately get back a generator object, and the execution of the generator body actually doesn't start. Only when a value is requested does the generator start executing, so at this point we will see the starting log as well as the value that will be returned after the first yield call, which is value 1 done false. And again the generator will be paused, and only when we request the next value does it resume and yield the next value, and again it pauses, and only when we request the next value does the execution resume and we have a simple console.log complete, at which point all the statements within the generator have been executed and it simply returns back the value undefined done true. Generators greatly simplify real-world handling of iterables, and just like with async await, which really makes promise-based code look like simple synchronous code, with generators we sort of don't have to constantly think about the underlying concept of iterators and iterables. You might recall this code from our lesson on iterators and iterables, and I won't even bother explaining it again because we can actually do it much more simply by using generators. So here we are defining a generator called range that takes a start value, an end value, and a step size. And we need to generate values that start at start, end at end, each time getting incremented by the step size. We can do that with a very simple for loop, and in each iteration simply yield back the current value of the loop variable I. We can use the result of the generator as a simple iterator by invoking next and getting the individual values. So for range 0 to 2, we get 0, 1, 2, and then done becomes true, and even more efficiently by using it as an iterable with a simple for-off loop, or even convert this range into an array by simply using the spread operator that, as we saw, also works on top of iterables. This example really demonstrates the beauty of generators and how they greatly simplify creating our own iterables. The real advantage of creating an iterable result over a standard JavaScript array is that an iterable allows lazy, on-demand return of individual values. As an example, if we wanted to generate all of the whole numbers, of course they are unbounded on the top side, and we couldn't do this with a standard JavaScript array, but we can still iterate over them by simply using a generator. And now we can loop over whole numbers using a simple for-off loop, and of course we don't want to do this for infinity, so I will still add a break statement if the number becomes 100,000. As we've seen, we normally return a value back from the generator by using the yield keyword, but you can also use an empty return statement within the generator whenever you want to directly move the iteration into the done state. For example, we can create a class called cancellation token, which has a simple boolean property is cancelled, which we initialize to false. We will utilize this cancellation token if we ever want to stop executing a particular generator. We create a simple generator called iterate that takes a max value and a cancellation token, starts off with I equal to 1, and then starts incrementing I, returning the values individually till I is no longer less than or equal to max value. Within the loop, we also check the cancellation token, and if it has been cancelled, then we will early terminate the generator by using a return statement. To demonstrate how this return statement will work, we create a new cancellation token and start iterating till a max value of 10 by using this cancellation token. If at any point the value becomes divisible by 5, we will cancel the token by setting its isCancelled boolean to true, and then for the rest of the loop, we will simply log out the current value that got generated. The generator is designed to generate values 1 to 10, but since we cancel at 5, that is the last value that we will see. Behind the scenes, the return statement is essentially turning the iterator's done boolean to be true. In addition to standalone function start declarations that we've been looking at, JavaScript generators can also be defined as methods of objects and classes by simply prefixing the member with a star character. To set us up for success, consider a very simple generator which yields two values, the string A and the string B, and we can invoke it pretty much like a standard function. It gives back an iterable, and we can spread it into an array if we wanted to. To convert the method on an object into a generator, we simply prefix the name of the method with the star character, and this turns that method into a generator, which means that we can yield values, for example, A and B. This star does not become a part of the method name, so to use it, we simply invoke it using the generator name, which is just simple, and of course, we can iterate over it to turn it into an array if we wanted to. Converting a class method into a generator is exactly the same. You simply prefix it with a star, and of course, invoking it gives us a generator object, which is both an iterator and is iterable. We can even prefix computed members with a star to turn them into a generator. So let's do something really cool. Define a computed property using the well-known symbol.iterator. And of course, since it is a generator, it's going to return an object which is going to be an iterator, and therefore instances of the class fancy itself will become iterable because they will follow the iterable protocol which we looked at in a previous lesson. This is really useful when you are building your own data collection classes and want to support something like for off. And in terms of behavior, all of these generators yield the values A and B, and that is what we see in the program output. In addition to the yield operator, which returns a single value, generators allow you to queue the return of entire iterables simply by using the yield star operator. Here we have a very simple generator called 1,2, which yields the values of 1 and then 2. Now let's create another generator that we will call fancy and use the yield star operator. The yield star operator works with iterables, and as we know, calling a generator returns an iterable, and a yield star basically yields those values one by one. So for our call to 1,2, yield star will first yield 1 and then yield 2. And of course, we can yield star from any generator just like we can yield from any generator. And one thing worth pointing out is that I said that yield star works with iterables, which means that we can use any iterable, even the JavaScript built-in array if we wanted to. So if we iterate over the result of fancy using a simple for-off loop, we will see the values from 1, 2, which is 1, 2, then 3, then 4, and then the values from 5, 6, which is 5 and 6. If I had to rank the coolest features of JavaScript, it would be a close match between async await and generators. In terms of utility, async await would win, but in terms of geeking out, generators are pretty awesome. I hope you enjoyed this tutorial. As always, thank you for joining me, and I will see you in the next one. Prototypes are not something that you need to know for modern JavaScript, but they definitely open a world of possibilities if you want to do some low-level programming or take a look behind the scenes of the magic of modern JavaScript. At its core, we have the secret proto member. We create an object called alpha that has a very simple name property pointing to the string John. So of course, type of alpha.name will be string, but in addition to name, it has a few other properties as well. For example, it has a toString, which is of a type function. So the question is, where are these things defined? And the answer is that when we created this object, it got a special property called proto, which itself is an object, and that object has the toString property that we are looking at. When we access a property off of a value, the JavaScript runtime first looks at the object. For example, that is what is happening with alpha.name. And if it doesn't find it over there, then it looks at the proto. And that is what is happening with alpha.toString. So we can actually create an object called beta and provide a proto ourselves. And if we point the proto to alpha, then in addition to the properties that we defined on beta, for example age, it gets the properties that we defined on alpha as well, for example name. And we can actually prove that the name property is coming from alpha because when we modify alpha.name to be Jane and try to read the name property from beta, then we will get Jane. We can actually create a whole proto chain, and when we look up a member, JavaScript sees if that object has that member, and if not, it transparently travels through the proto chain till it finds something that has that member, or the proto becomes null. So let's do something crazy and create a person that is an object that has a proto of a proto of a proto that points to an object that has the member's name and age. And if we try to access person.name, JavaScript travels up the chain till it finds something that has it. And the same for the age property, it travels up and finds the age 18. But if we try to access a property that does not exist anywhere in the proto chain, for example weight, then JavaScript gives us that special value that we've talked about called undefined. And what's really happening behind the scenes is that JavaScript has looked at person.proto.proto.proto till proto itself became null, and at that point gave up and gave us undefined. And the first time you see it, it can be a bit hard to believe, so let's just run this code to prove that this is how JavaScript functions. Not to be confused with the instance proto, there is a special property called prototype that exists on classes and functions, and spoiler alert, classes are just fancy functions. So we've been using this property __proto__, which we've been calling proto, but the JavaScript language specification actually calls this proto concept as prototype square bracketed. But we will call it proto because calling it prototype gets confusing because there is an actual property that exists on functions called prototype. Let's create a very simple class called alpha that has a method log. What might surprise you is that the type of alpha is actually going to be function. And functions have a special property called prototype, which is an object, and any methods that we define on the class actually get defined as functions on the class prototype. So classes are actually just glorified functions, and we can actually achieve the same effect with a function within JavaScript, and this is what people used to do before we actually got classes. We define a simple function called beta. Of course, it is going to be of a type function just like the class, and it is going to have the prototype property just like the class. Additionally, any methods that we want on the class, we can actually just add to the prototype of the function. As far as the JavaScript runtime is concerned, the class alpha and the function beta are actually equivalent. We've talked about how the new operator impacts this during object creation. One more thing that the new operator does is that it assigns the function prototype to the created instance's proto. Let's create a local variable that will help us see some of the effects of new. We create a simple class called newEffects, and within the constructor we take a message property which we add to this, and additionally we save the this value into the created variable. We also add a simple log method that logs the message that we previously saved. Now when we create a new instance of the class by using the new operator, what happens is that JavaScript creates a new object and passes it to the constructor by using the this keyword. And this created object is what is eventually returned from the constructor which we are storing in the instance variable. So whatever was this within the constructor which we stored using created is exactly equal to the instance that is returned. So that is the main effect of the new operator, but it does something more. Note that the instance is only going to have one property which is going to be message which we set in the constructor. Yet we can actually use instance.log. We know that class methods are actually defined as properties on the function prototype, so newEffects.prototype.log will be that method. So how does it end up on instance? And the answer to this mystery is another effect of the new operator, which is that it takes the function prototype and assigns it to the created instance's proto. And since the log method is defined on the prototype, it's going to be available on instance.proto. And as we know, when we access a property, JavaScript magically looks up the proto till it finds it, and that is how instance.log just works. At the heart of a lot of magical features of JavaScript is the transparent assignment of a well-known prototype to the proto of the created value. We know that functions come with prototypes, and the new operator assigns the prototype of the function to the created instance's proto, and since classes are just glorified functions, that is exactly what happens for the class as well. But what might surprise you is that a proto assignment also happens for primitive types. As an example, when we create a string, the created value has a proto member that points to the well-known string.prototype. And similar prototypes exist for other primitives as well. For example, with a number, the created values proto is going to point to number.prototype. And this is how these JavaScript primitives actually get their built-in methods. The number prototype has a member called toPrecision, which is a function, and because the prototype gets assigned to the proto, it magically shows up on the created numbers proto, and therefore when we do number.toPrecision, it's really using the toPrecision method that is actually defined on the number prototype. Because prototypes exist for the primitive types within JavaScript, it makes it super easy to add newer features of JavaScript to older JavaScript runtimes, and that is how polyfills work. Let's say a new JavaScript spec has come out, which means that all JavaScript strings now get this magical method called uppercase trim. Even without updating our JavaScript runtime, we can actually polyfill that method into our existing runtime by simply defining it on the string prototype. The only simple trick that we have to use over here is that instead of taking the string as a parameter, we use the this keyword, which we saw in its own dedicated lesson. By using this keyword, the string will automatically get passed in as this based on the string that is used to invoke the method. Now we know that every single time someone creates the string, it gets the magical proto property which points to string.prototype, which means that any created string has access to the uppercase trim because that is what we defined on the string prototype. So if we call uppercase trim on a string with spaces at the edges that is all in lowercase, the spaces at the edges get trimmed and the string turns to uppercase. Needless to say, you shouldn't modify the built-in prototypes unless you are creating a polyfill because you will end up with conflicts. Instead, just create a utility function. It's easier to create without making a mistake and much easier to understand at the point of usage for the next person. Here's a little known fact. JavaScript class inheritance with the extends keyword actually also works by utilizing proto-chaining. So we create a simple class animal with the method eat, and we create a simple class bird that extends animal and adds another method called fly. When we create an instance of the bird by using the new operator, we already understand how the fly method will end up on the instance. The way it works is that the new operator assigns the prototype to the proto, and since the prototype has the fly method, it is going to be available on the bird proto, which means that bird.fly just works. What we haven't explained yet is how does bird.eat work? And the answer to this mystery is that the extend keyword actually creates a proto chain between the two prototypes and assigns the prototype of the base class as the proto on the prototype of the child class. So if something is not found on the bird prototype, it will automatically be looked up from the animal prototype. And since the bird class prototype becomes a proto on the instance, methods defined on the animal prototype will magically become available on the bird instance. And that, ladies and gentlemen, is why we can just do bird.eat, all thanks to the proto chaining done by the extends keyword. We've been using the secret proto property, but there is actually a low-level API that allows you to create simple prototype-based inheritance. Let's create a simple animal that has a property eat, which is a function that returns yum yum. We can actually create a bird that inherits all of these properties by assigning the proto property to animal and then adding anything else that we want, for example, fly, flap, flap. And now we can do bird.eat as well as bird.fly. Using underscore underscore proto underscore underscore is actually not something that is officially standardized, and we've just been abusing it as it is a pretty known secret. The official recommendation is to actually assign a prototype by using object.create. So object.create actually creates a new object and sets the proto to whatever is provided. So bird will be an object that has its proto member pointing to animal. So all that is left for us to do is to assign anything else that we want for the bird, which is just the fly method flap flap. And this is equivalent to what we did before. We have the bird with the proto pointing to animal and the fly method added, and we can prove that by simply eating yum yum and flying flap flap. Using a null value for a proto actually allows you to completely opt out of the default object prototype assignment, and this is great when you want complete control over what properties should show up on an object. Let's create a simple object that we intend to use as the dictionary data structure used to track who came to our party and who didn't. As an example, John came, so that is true, and Jane didn't come, so that is false. But as we know, dictionary also has its proto assigned to the object.prototype. And since object.prototype has a number of things, for example, the toString function, it seems that toString is also present in dictionary, so it seems that toString also went to the party. What would be great is if we could create an object that didn't have anything other than what we wanted, not even proto, and that is exactly what object.create does with a null value. It creates an object that doesn't even have the proto property, so when we say that John came to the party and Jane didn't come, John and Jane are the only things that are in the dictionary. That toString or anything else within the object prototype is not going to pollute our nice clean object. I hope you enjoyed this tutorial and some insights into how JavaScript actually works under the hood. As always, thank you for joining me, and I will see you in the next one. Having a proper O of 1 set data structure is critical for high performance computing, and it didn't get added to JavaScript till after JavaScript had already exploded in popularity. Fortunately, now that we have this built-in set class, it makes trivial work of a number of popular programming interview questions. We simply create a new instance of the set by using the set constructor with the new operator. A set has a number of features, and we can add new items to the set by using the add function. So if we add 5, the set has a single item, which is the number 5. We can add another item, for example 1, and now the set has 2 items, the number 5 and the number 1. A set only stores unique items. Internally, it does that by using hashing, and sets can quickly see in constant time if a particular value already exists in the set, and if not, it adds that to the set. So if we add the number 5 to the set, it will see that it already has 5 present within it, and it will not add it again. This high performance lookup and deduplication is the key reason for the existence of the set data structure. In addition to adding items using the add method, we can also pass an iterable to the constructor of the set, and the set automatically adds all of those items by iterating over the input. In the array that we are passing right now, there are only 2 unique strings, hola and mundo, and those are the only 2 values that will be present within the set. Notice that the set constructor accepts any iterables, which means that in addition to arrays, we can pass it anything else. For example, we know that within JavaScript, strings are also iterables, so we can even pass in a string if we wanted to. And of course, it will iterate over the different characters within the string, and again ensure that only unique values get added. Notice that within the string hello, the character L appears twice, but it will exist only once within the characters set. Just like any other JavaScript class, we can check if a particular value is an instance of the set class by using the instance of operator, and over here the values, numbers, messages, and characters are all an instance of set. We've seen that the set data structure accepts iterables in the constructor, but what's worth noting is that the set itself is also an iterable. Let's create a set that consists of 3 strings, John, Jane, and Jack. Because the set is an iterable, we can use it anywhere else we can use an iterable within JavaScript. For example, with the for-off loop, if we loop through the people set, we get back the individual strings, John, Jane, and Jack. Additionally, just like any other iterable, we can spread the set into a JavaScript array. And of course, in this particular case, we will get back an array that contains the 3 strings that we put in the set. Because the set constructor accepts an iterable and the set itself is also iterable, it makes it a trivial task to create a copy of a set. We can simply take a set and pass it to the set constructor to create a copy. Since people copy is a copy of the original set, any mutations that we make to the people copy will of course be only in the people copy. So here we are adding Jill to the people copy, and of course it's present in people copy but not present in the original people set. A little known fact particular to JavaScript and different from other programming languages is that the JavaScript set guarantees that it will maintain insertion order. So if we create a set with the array pizza and ice cream, it will have the items pizza and ice cream in that order. If however we create a set with ice cream and then pizza, then again the order will be different. And we can demonstrate this preservation of insertion order. If we convert the set back to an array, the items will display in the order that they were added to in the original set. This is actually great because order is significant for arrays, and it allows for an easy conversion of an array into a set to remove any duplications, and then a conversion back to the array while preserving the order of the items. To demonstrate this, consider the example that we've received missed calls from Jane, then Jack, then Jane, and then Jill. We should only call back the individuals only once. However, we want to call them back in the order that they called us. So we really want to only call Jane once, then Jack, and then Jill. We can find the unique callers so that we can call them back in the correct order quite easily by simply taking the array, passing it through a set to only get the unique items, and then converting it back to an array with a simple spread operator. So here we get the answer that we are looking for. We need to call back Jane, then Jack, and then Jill. And as an aside, we might not even need to call Jill, because when we will call Jack, he'll probably tell us that they went up a hill. The JavaScript set is a pretty easy data structure to master because it only has a handful of properties and methods. We already know that the set constructor takes any iterables. For example, here we are passing an array of the spices nutmeg and ginger, and we can add more items by using the add method, and now we have the set that has nutmeg, ginger, and cumin. There is a method that is the opposite of add, and we can remove items from the set by using the delete method. This method also returns true if the item was present within the set. So now that we have deleted ginger, if we run it again, this time it will return false because ginger was no longer present within the set. Sets also come with the has method that tells you if an item is present within the set or not. For example, here the set does have cumin. However, since we've removed ginger, ginger is not present within the spices. So right now the set only has two spices, which are nutmeg and cumin, and we can check how many items are present within the set by using the size property. Of course, since there are two items, size will be the numeric 2. Sets also come with the clear method, which removes all the items from the set. And of course, once the set is empty, the size will turn to 0. Let's run through a simple example to prove that using the set data structure is truly more performant than raw arrays, and get some understanding of how stark the difference really is between O of 1 for sets and O of n for arrays. Let's consider the simple task of removing duplicates from a given input array. To start off, we will create an array that will consist of 10,000 items. We create an array of 10,000 items and ensure that there will be some duplicates around half of them by creating numbers that will be in the range 0 to 10,000 divided by 2. Let's measure the time of removing the duplicates from this input, first by using just plain arrays and then by using sets. With arrays, we create an output array and then simply loop through the input items, and each time we check if it is not already present within the array by using index of. And if index of is -1, meaning that the item is not already in the array, then we simply push it into the end of the output. We are going to time it using JavaScript's built-in methods console.time and console.timeEnd. Now let's repeat the same process, but this time by using a set, and as we know, we can remove duplicates from an input array by simply creating a set from that array and then converting that set back to an array by using the spread operator. If our algorithm is correct, then the result of using an array and the result of using the set should result in the same number of items, so we will simply log out the length of the array output as well as the length of the set output. And now for the moment of truth, let's run this code to see what are the results from the array versus the results from the set. As we can see, they both contain the same number of items. However, the array took around 11 milliseconds and the set was done within 1 millisecond. Now with 10,000 items, even though the time difference is still quite large, 11 milliseconds doesn't feel like a big deal, so let's just bump it up to 100,000. You can take a moment to guess how much of a difference it will have. Because every time we add a new item, the array has to look at all the existing items, the difference will be quite significant. If we run the code, you can see in the output that the array takes around 1 second, whereas the set is still done within 4 milliseconds. The difference between a second and 4 milliseconds is the difference between a responsive and an unresponsive application. The key motivation for using the set data structure is its O of 1 item addition and lookup, and this has a number of real-world high-performance use cases like removing duplicates and finding repeated items. To demonstrate some applications, we create a simple array that has characters A, B, and C, where A is duplicated. We can create a utility method that removes duplicates from a given input array, and all that it needs to do is to pass that array through a set and then return that iterable back into an array. And of course, for our input example, we get back the strings A, B, and C. We can also easily create a utility method to check if a given input array has duplicates by simply passing that array through a set and checking if the size of the set is equal to the input array length. Of course, for our particular example, it does have duplicates, and indeed, when we pass it through the hasDuplicates function, we get back the boolean true. In addition to removing duplicates, we can also use sets for finding the repeated items within a given input. We create two sets, one for the items that we have already seen, and one for the items that we have found are indeed repeated. Then we simply loop through the input, and if we have never seen this item before, we add it to the seen array. Otherwise, if we have seen it, then of course it is a repeated item, and we add it to the repeated set. Once the loop terminates, all our repeated items will be in the repeated set, and we can convert that back into an array by using the spread operator, and that will contain our repeated items. If we run our original input with the duplicated a through find repeated items, we get back an array with that duplication pointed out that a is the only item that was repeated. A proper built-in implementation of the set data structure is truly something that makes JavaScript a modern programming language. As always, thank you for joining me, and I will see you in the next one. Just like the set data structure that we've looked at, JavaScript comes with a built-in map class, which is a very effective constant time key to value lookup and maintenance data structure, and it really makes JavaScript a very powerful modern programming language. We can create an instance of the map by using the new operator with the map constructor. At its core, a map is a key value store, and the intent for this name to age is to have the person name as the key and the person age as the value. As an example, we can state that John is someone who has an age of 25, and then Jane is someone who has an age of 28. This map now has two keys, John and Jane, with corresponding values of 25 and 28. Every key in the map needs to be unique, so if you want to update John's age because he's just had his birthday, we can do that by setting John to a new value of 26. Just like the set data structure, internally map uses hashing to ensure constant time over fun reading and writing for any given key. We've done some writing using the set method, and we can do some reading by using the get method. So of course the current age for John is 26, so if we get John, that is the numeric value that we get. If we try to get something that is not present within the map, as an example, Jill has never been set, so the JavaScript runtime will give us that special value of undefined. In addition to providing values to the map by using the set method, we can also provide values to the map by passing an iterable to the map constructor. Each item of the iterable must be a key value pair, and as an example, we are providing an array over here where each item in the array is a key value pair, like France is the key and Paris is the value. So essentially here we are creating a map with the values preset, France pointing to Paris, Italy pointing to Rome, and Australia pointing to Canberra. Within JavaScript, there is a convention of using the term entry for a key value pair. Just like any other class within JavaScript, we can use the instance of operator to check if a particular value is an instance of a map, and of course, name to age and country to capital are both maps. Maps in JavaScript work nicely as iterables. The map constructor accepts an iterable of entries, the map itself is an iterable of entries, and it even comes with convenience methods to just iterate over the keys or the values. We already know how to create an instance of the map by using an iterable of entries, like an array of entries, and here we have a map of prices with cucumber pointing to 50 and tomatoes pointing to 35. Map provides an entries method which returns an iterable of entries, so here we can log the entries cucumber 50 and tomato 35, and in fact the map itself is also an iterable of entries, so we don't even need to invoke the entries method, we can simply loop through the entries of a map. And just like any other iterable, we can also easily get the output as an array by using the spread operator. We can also iterate over just the keys of the map by using the keys method, and even just the values of the map by using the values method. Now because the map itself is an iterable of entries, and it accepts an iterable of entries in the constructor, we can actually create a copy of the map quite easily by just passing it to a new map constructor. So here prices copy will be a new map that contains the same key value pairs as the original map. Traditionally, before we got a proper built-in map class, people used objects even for dynamic key value pairs. But in modern JavaScript, for the key-based lookup data structure, the map class provides a number of benefits over just using, or rather abusing, an object. As we saw in our prototype lesson, we can create a clean object free from any standard object keys like toString by using object.createNull. And this does allow us to have strings as keys with values being whatever we want, and even works with symbols reliably. But for any other type of key, it can be pretty darn unreliable. For example, if we set the number 123 to salam, it can get overwritten by the string 123 hola. And if we try to use an object as a key, it is going to be completely useless. That is because all objects will get converted to the same string key. So even though we are trying to set 6 different keys over here, we will only get 4 distinct keys in the final object. The map data structure, however, has no such restrictions. You can use any value that you can assign to a variable as a key within a map. Let's create a new instance of the map and set high to high, set a symbol to bonjour, set a number to salam, set a string 123 to hola, set an object to konnichiwa and a different object to namaste, and if we log out the map, it has all of these keys and all of these values without fighting with one another. So the guidance is pretty simple. If you need an object with a known structure with only identifier friendly or string keys, use an object, but if you need a dynamic key value data structure, use the map instead. The JavaScript map always preserves insertion order, and this can greatly simplify any complicated sequence preservation requirement when processing data. Consider a simple array of entries where we have different orders as they come in. John placed an order for a burger, Jane placed an order for a steak, and then John placed an order for a salad. Your mission, should you choose to accept it, is to consolidate the values under the same name and to make sure that whoever placed the order first continues to be first in the queue. We can create a grouping of these quite easily by using a JavaScript map. We simply loop through the entries present within the orders, collect the name and the item, and check if it already exists within the map. If it does, then we get the array by that name and push this item into that array. Otherwise, this is the first time we have seen this name, and we simply set the name key within the orders to an array of that individual item. Once this loop terminates, we should have all of the items grouped by the name pointing to the array of the items that the person has ordered, and because the insertion order is preserved, John will appear before Jane. Just like the set data structure, the map class has a very laser-focused utility and therefore a very easy API to master with just a handful of properties and methods. We create a very simple map to keep track of who owes us how much money. We've used the set method before, but what you might not know is that we can actually chain the set calls because it is a Fluent API. So here we are saying that John owes us 10 and Jane owes us $18. Another method that we've already looked at is the get method, which can be used to get a value for a particular key, and if that key is present, then the value is returned, and if that key does not exist within the map, then it returns undefined. We can remove items from the map by using the delete method, so if John manages to pay us back, we can remove him by using delete John. The delete method will also return true if that key did exist within the map, and since John did indeed exist, we get back true. However, if we invoke it with something that does not exist within the map, it will still pass. However, it will return the value false to indicate that Jill never owed us any money. We can also check if a particular key exists within the map by using the has method, so has Jane will be true and has Jill will be false. Now right now there is only one person that owes us any money, and it is Jane, who owes us $18, and we can see how many items exist within the map by using the size property. Since it's just Jane, we get back the numeric 1. We can also remove all keys and corresponding values from the map by using the clear method, and of course once we've invoked that, this map will be empty. Because objects are such a critical part of the core of the programming language, JavaScript comes with built-in convenience methods to convert from an object to a map or convert from a map into an object. We create a simple map country to flag with some countries: United States, France, and Australia, with their corresponding flag emojis. We note that a map is an iterable of entries, and we can actually create an object from such an iterable by using the JavaScript built-in method object.fromEntries. So this object will have the properties United States, France, and Australia, with the corresponding values being the flag emojis. Just like the JavaScript built-in object.fromEntries takes an iterable of entries and returns an object, there is a built-in JavaScript method called object.entries that takes an object and returns an array of entries. And since we already know that a map constructor will happily take an array of entries and create a map, we can use the chain object.entries followed by a map constructor to convert an object into a corresponding map. So here we have a map that is functionally equivalent to the country to flag map that we originally started with. A key thing to remember about the map data structure is that keys are checked using strict equality, and this can impact your decision on what you want to use as a key and what you want to use as a value. We already know about JavaScript object equality. Just because we have two objects that are structurally equivalent, they will not be strictly equal because they are distinct instances. Only object 1 will be equal to object 1 and object 2 will be equal to object 2. So if we try to create an age map and set an object with the name Alice to the age 20, and on her birthday we decide to create another object with the name Alice and update the value to the age 21, we have made a mistake. We have made a map that has two objects, both with the name Alice, with the ages 20 and then 21. There is nothing stopping you from using objects as keys, and in fact, we can still do that quite easily. We just have to make sure that we use the same object every single time we update the value. So here we are storing the ls object into a simple variable, and we make sure that we use that every single time we are setting the age. So now when we look at age map, it only has one object as the key, with the value now updated to 21. Making sure that you store a reference to the object before you start using it into a variable can definitely become inconvenient, so another solution would be to rethink how we structure our map. Ideally, think of some string or a number property that exists on the map that you can use as a key instead. For our simple object, it seems that the string ls is quite important, so we will use that as a key instead. We store an object against the key ls, and we just provide a new object whenever we want to modify any property. So now after the two calls, the person map will consist of a single entry with the key ls pointing to the object that has the name ls and the age 21. I hope you enjoyed this comprehensive tutorial on the built-in JavaScript map class. As always, thank you for joining me, and I will see you in the next one. When it comes to async programming within JavaScript, we have a lot of options on how we can manage multiple tasks using promises. Let's set up a simple structure that will help us demonstrate the different flows. We are not going to do anything complicated, we are going to keep it very simple. So here is a utility called pass, which takes a value and then returns a promise which we resolve to that value after 1 second. And we create a similar utility called fail, which takes an error message and then returns a promise which we will then reject with an error pointing to that error message after 1 second. We are going to be demonstrating our code by executing an async main function, and within the main function we have a very simple try catch to demonstrate any promise rejection that might happen. Now the work that we are doing in our tasks pass and fail is just waiting for a timeout, but it might as well be any async work that you can think of, like a backend API call. Now that we have the scaffold ready, let's discuss the different execution options. The simplest execution of async in JavaScript is to simply await each call as you make it, and this results in a sequential flow where tasks are executed one after another. As an example, we execute a task which will eventually pass with the value alpha, and we do not continue program execution till this task resolves by using the await keyword. Once it resolves, we get the value of alpha and we log that to the console, and we can do a similar thing as many times as we want. We can execute other tasks, beta, Charlie, and delta, and then await the results with the await keyword as soon as we execute them. We wait for alpha till it resolves, then we wait for beta, then we wait for Charlie, then we wait for delta, and all of them do succeed in this particular case. We know that at any point, if any of these promises result in a rejection, for example, we fail Charlie, then the await results in a standard throw of the error which we are catching, and when we run this code, that is exactly what we see. Alpha and beta pass, then Charlie throws an error, and we never execute delta. Series execution is pretty easy to understand, and you can pretty much use your standard synchronous mindset when working with code that executes in sequence. The hard opposite of a sequential flow is parallel execution, and with JavaScript we can actually fire off all of the async work in parallel and analyze the results using built-in promise static methods. JavaScript comes with a number of such methods, and the first one we will look at is promise.all, as this is the most common one that you will use. So instead of awaiting the results individually, we just fire off the work and then store the results into different promise variables. This means any of the tasks within the pass function, which is just timeout, has already started, and they will pretty much complete at the same time. To get the fulfilled result of all of these promises, we can use the built-in static method called promise.all. It can take an array of promises as an input and then combines them into a single promise. We can await this promise to get an array of the resolved values of the original promises. So since our promises resolve to the strings alpha, beta, and Charlie, if we execute the code, that is exactly what we see. You can think of promise.all as the parallel BFF of the sequential flow, and just like in a sequential flow, a promise failure on any of the sequence results in a throw at that point, and we jump straight into the rejection. Promise.all will also reject the combined promise if any of the individual passed-in promises fail. So here we are failing beta, so the combined promise will fail with the error of beta, and that is what we see in the program output. Promise.all will result in a rejection immediately after any single promise in the argument settles on a rejection. But if you want complete knowledge about the fates of all of the promises in the input, That is where promise.allSettled comes in. Consider the simple example where we have 3 promises. The first one will pass with the value alpha, the second one will fail with the reason beta, and the third one will pass with the value Charlie. Since we are not awaiting any of these tasks have already started executing in parallel. The promise.allSettled function can take these promises and then combine them into a single promise, which will resolve as soon as all of these promises have settled on their fates. The resulting promise will always resolve into a single array, so let's just log it out to understand more about its structure. The individual items in the result array indicate the final status of the original inputs. The status field will either be fulfilled if the promise got fulfilled, or it will be rejected if the promise got rejected. Additionally, if it got fulfilled, it will have a value, and if it got rejected, it will have a reason field. Alpha got fulfilled with the value alpha, beta got rejected with an error object with the reason beta, and Charlie got fulfilled with the value Charlie. Now that we understand the structure of the result array, it is actually quite easy to destructure it into individual results, and as we have seen, alpha result.status will be fulfilled, which means that it will have a value which is alpha, and since beta result.status is going to be rejected, it means that it will have another member called reason, which will be the error object that beta was rejected with. We use promise.all and promise.allSettled when the promises are distinct tasks with their own results. But sometimes we use parallelization for a set of similar tasks. An example use case would be network redundancy, where we make the same call to 2 backends and really only care if any of them succeed. For this, we have the built-in promise.any. We fire off a task to one server, alpha1, and we fire off the same task alpha to another server, alpha2. We don't really care if any of these fail. All that we really care about is whichever one passes first. And for that purpose, we have the built-in promise.any. It takes the 2 promises and combines them into a single promise, which will resolve as soon as any of these get fulfilled. We log out the value of whatever got fulfilled, and just in case nothing gets fulfilled, the promise will actually reject, and we can catch that with a simple catch. And this particular error will be an instance of an aggregate error because it actually combines the errors of all of the promises that we passed in. It will have a message property, which is going to be simply all promises were rejected, and it will also have an errors property, which are the actual rejections from the individual promises. Let's do a few walkthroughs to understand promise.any a bit better. Right now, both alpha1 and alpha2 are going to pass, and since we kicked off alpha1 first, that is the one that will succeed first, and that is indeed the result that we get for first fulfilled. If, however, alpha1 were to fail, then promise.any will keep waiting till alpha2 settles, and of course it will pass, so that is what we get for first fulfilled. If, however, all of the promises that we are passing to promise.any get rejected, then the resulting promise will also get rejected. And as we have mentioned, we will see an instance of aggregate error with the message all promises were rejected, and the errors point to the individual rejection reasons. Sometimes you might run the same task multiple times in parallel when we are trying to optimize for speed. One instance of the task might complete faster, and we'd rather hear back from whoever can get back to us the quickest. And for these kinds of use cases, we have the appropriately named promise.race method. We fire off 2 tasks, alpha1 and alpha2, and of course we don't await them because we want to run them in parallel, and we really only care about who can get back to us the fastest. These tasks might be running in 2 different corners of the world, and we really care about getting the result as quickly as possible, which is why we are starting 2 tasks instead of calling to just one machine. And the built-in JavaScript method promise.race does just that. It takes a number of promises and then combines them into a single promise, which will resolve as soon as any of the input promises resolves. So if the fastest among alpha1 and alpha2 get fulfilled, we will get back the fulfilled value, and if it results in a rejection, we will get a rejection which we tackle with a try catch. Right now we know that both of these promises will pass, and since we kick off alpha1 first, that is the thing that will actually get fulfilled, and we see that in the program output. This means that even if alpha2 were to fail, it wouldn't change our outcome because alpha1 will already be fulfilled before alpha2 gets the chance to fail. And if we run this code, that is exactly what we see in the program output. We are still getting fulfilled by alpha1. So with promise.race, the fate is completely dependent upon whichever promise settles first. If the first promise were to settle in a rejection, then the resulting promise will also result in a rejection, and that is exactly what we see in the program output. I understand that keeping the various promise utility methods in your head can be a bit challenging, so here's a quick recap and a reference that you can always revisit whenever in doubt. First up, we have the standard sequential flow. We simply await every single promise as soon as we get it, and this means that the program doesn't execute till that promise is resolved, and this is the simplest one to understand. The alternative are parallel flows, and the one thing that is common across all of them is that we do not await the promise after we start the task. There are various ways we can combine the parallel task results, and the simplest one is promise.all, which will simply wait for all of them to get fulfilled, and if they all fulfill, we get back an array of fulfilled values, otherwise we get the rejection from the first promise that gets rejected. If you want more low-level control and just want the fates of all of the promises into a simple array, then promise.all settled is your friend. It gives us back an array where each item contains the individual promise's status, a value if it got fulfilled, or a reason if it got rejected. If you are keeping your fingers crossed that some promise might get fulfilled, then promise.any is your friend. An example use case would be something like network redundancy. You know that some things might fail, but you hope that something will at least pass. And finally, if you just really care about the fastest promise to come back to you, then we have promise.race. If the fastest promise gets fulfilled, then the result gets fulfilled. If the fastest promise gets rejected, then the result gets rejected. An example use case would be duplicated work across different machines, so you don't have to do some upfront optimization to figure out which machine is likely to give you the answer faster. I hope you enjoyed this tutorial on how you can manage multiple promises effectively in JavaScript. As always, thank you for joining me, and I will see you in the next one. A critical fact worth knowing about JavaScript is its automatic memory management. Unlike low-level programming languages like C and C++, we are not directly responsible for managing memory in JavaScript, as it is done automatically by the built-in garbage collector. Browsers do not expose the underlying garbage collector, however, we can access it in a server environment like Node.js. As an example, we can determine how much memory is being used by the JavaScript heap by using process.memoryUsage. Additionally, we can even trigger a garbage collection manually if we wanted to. Let's just note the heap used before we trigger the garbage collection, then trigger a garbage collection using the node built-in global.gc function, and then note the heap used afterwards. Using the before and after values, we can actually determine how much memory was freed up by that call to global.gc. To demonstrate the garbage collector in action, we create a class heavy that creates a very large array consisting of 100,000 characters. Additionally, we create a function called consume that takes a character as an input and then creates a 2500 array of heavies. Note that we create an array within consume and then return it, so if we never store a reference to this array when we call this function, then it should be available for garbage collection, and the JavaScript GC should be able to free up that memory. With this heavy infrastructure and utilities created, let's just write all our code within a main function. First up, let's demonstrate the garbage collector in action by invoking the function consume with different characters, but not storing that resulting array in any variable. We note down the memory that is currently being used by the process, then consume a lot of memory for the trash emoji, and then note down the memory being used afterwards, and then invoke the garbage collector. The garbage collector should be able to free up all the memory that the consume occupies, and therefore we can do this as many times as we want, and it should all work perfectly fine. Let's consume the memory with a few different emojis, and every time we've made a consume call, we should see the memory consumption rise, and after the garbage collection, the memory consumption should decrease again. If, however, we store the resulting array from consume into a variable, that would mean that the array is still within scope and the garbage collector will not be able to collect it, and we should see our memory continue to rise after every single consume call where we are storing the results into different variables. As long as the variables uno, duo, and tre are pointing to those arrays, the arrays will need to stay in memory and the garbage collector can't do anything. And now for the moment of truth that you have been waiting for, let's just execute this code and demonstrate it in action. Within our fire and forget version, where we do not store the result of consume, you can see that every single time the garbage collection call has been made, we have managed to free up 1000 MB. However, when we keep the result into a variable, the memory consumption just keeps going up, and the garbage collector has not been able to free any memory. Now within JavaScript, we don't actually have to call the garbage collector ourselves, JavaScript would have jumped in and done that smartly depending upon how busy the code is and how much memory is available. But in Node.js, since it is a server environment, it does provide a hook to trigger it manually if we wanted to. If we keep allocating resources but do not free them up, eventually we will run out of memory, and in the browser, our tab will crash. Here we have the same utilities pasted into the browser console. We have a class that creates a heavy character array and a consume utility that creates a massive array consisting of heavy items. If we make 6 different calls to consume, it's going to be perfectly fine because every single time a consume call is made, we discard the result, which means that that memory that has been allocated can be deallocated by the built-in garbage collector. However, if we start to store these results into different variables, that will mean that all of this memory will still hang around, the garbage collector can't do anything about it, and we will eventually run out of memory, and the browser dev tools will actually even pause, pointing out that we are about to exhaust our resources. If we ignore this warning and push through with our code execution, we will eventually run out of memory and the browser tab has crashed, as you can see on the left-hand side. Of course, on a production site, the user is probably not going to have the DevTools open, so they will not get any warning. The website will just crash. The takeaway lesson is pretty simple. Whenever we are done with a value, we shouldn't keep a reference to it anymore. This will happen automatically if a variable goes out of scope, but if we still have the variable, we can do simple things like assigning it to null. So we start again by pasting in the utilities for heavy and consume, and we will still make consume calls and store the results in different variables. This means that we can use the results, for example, to look at the first character, but after we are done with it, we will assign that variable to null, and this will allow JavaScript to clear up that memory that was previously being occupied by that variable. So now if we run the code, even though the memory allocation might be high, we will not run out of memory because it will be available for the garbage collector to collect as soon as the value is no longer referenced from our code. JavaScript comes with an excellent garbage collector, and because of the browser wars, it's probably one of the best in the business, and you mostly don't need to think about memory management. As always, thank you for joining me, and I will see you in the next one. The word weak in JavaScript implies that a data structure will only hold a weak reference to an object, and this allows that reference object to be garbage collected even if we still have the data structure in scope. To understand the weak map, we need to understand one critical issue with the map class. We create a simple instance of the map, and for 2 variables x and y, we create 2 simple objects and use these objects as keys within a map to store 2 simple string values. Now ideally, when these objects go out of scope or we stop referencing them, for example by assigning x and y to null, they should be available for garbage collection. However, there is an issue that the map still holds a reference to the keys that we used, and we can actually get those original objects simply by iterating over the map.keys. So, since our code still has a path to get those original objects, they cannot be garbage collected, and the main thing preventing the garbage collection of those original objects is the fact that a map has a strong reference to its keys. This is the main difference between a map and a weak map. So let's create those x and y objects again, create a new weak map, and we can use it just like we were using the map. We can use these x and y objects to store values against them, and we can get those values back by using the weak map get method. However, the map itself doesn't hold a strong reference to the passed in keys. A strong reference is what we have when we assign an object to a variable using the equal sign. This is not what the weak map does internally. It uses something more low level. The only strong references to those original objects right now exist as the variables x and y. So if we actually assign x and y to null, there is nothing within our code or within weak map that is directly equal to those objects. What this means is that the garbage collector can jump in and free up the memory for x and y and any of the values that were associated with these keys. Obviously, weak map is a very specialized version of the map class, and therefore the weak map comes with significant limitations when compared to a map. The first limitation is that the keys for a weak map must be an object. It has to be something that a garbage collector can garbage collect. So let's create 2 simple objects assigned to variables alpha and omega to demonstrate the features of the weak map. We can actually pass an iterable of entries just like we can do with the map to the weak map constructor. Here the map has a single key, which is the alpha object, with the value which is the alpha string. We can set a value against an object as well if we wanted to. So for omega, we set the value to be the omega string. We can get a value back by passing in a correct object for the key. So we can get back that alpha string from the alpha object. And we can also delete keys. For example, we can delete the key for the alpha object, and the delete method will return true if the key existed. If we try to delete alpha again, it no longer exists, and therefore we get false. If we try to get the value for a key that no longer exists within the map, for example, alpha no longer exists, we get back undefined. And we can also check if a key exists within the map with the has method. So alpha no longer exists, however, omega still does. Beyond the restriction that the keys must be objects, all of these methods are exactly the same as they are within the map data structure. However, unlike the map, the weak map has no size property. It has no iteration methods to go through either the keys or the values or the entries, and it has no clear method because it is not holding any strong reference to the keys it contains. Since you cannot iterate over the keys or get the keys from the map yourself, there is no point in clearing it either. We've talked about it from a theoretical perspective, but let's do a practical demonstration of the fact that the standard map class blocks keys and therefore values from being garbage collected, whereas a weak map doesn't because it only holds a weak reference to its keys. We create a simple utility called fill that will take a map-like data structure and a given string character. Then it will iterate 2500 times and each time set a new key within the map-like data structure with the new object each time with an ID property which we will calculate using math.random. And for the value, we will allocate a massive array consisting of 100,000 items all filled with the same character. The objective of the fill method is to fill up a map with lots of new objects created using math.random with values pointing to giant arrays consisting of characters. Let's do a simple test to compare the memory performance of the map and the weak map classes, and for this we will utilize the memory used and the collect garbage utilities which we created in our previous lesson on JavaScript memory management and garbage collection. First up, let's put the standard map class to the test by creating an instance of the map, noting down the current memory that is being used, fill that map up with the chili character, note down the memory being used afterwards, and then try to collect the garbage. Those objects that we created within the fill function are not being referenced anywhere within the code over here, but they are still being referenced by the map. This means that the garbage collector will not be able to do anything, and in fact, if we just run it again with a different character, the memory consumption with the standard map will just go up and up because all of those objects exist as keys that we can get access to using the default map. Before we run this code, let's do the same thing with the weak map. We create an instance of the weak map and then note down the memory used, fill up the weak map with a different character, note down the memory used afterwards, collect the garbage, and we can do that as many times as we want. What will happen is that because those keys only existed within the fill function and they are not referenced from anywhere within our code, they only exist as weak references internally within the JavaScript built-in weak map. This means that they are available for garbage collection and the garbage collector will free up that memory for us because of the massive amount of content that we are creating. So now for the moment of truth, let's run this code and see it in action. With the map, you can see that we start off with a low amount of memory, but after we fill it up, the memory just spikes through the roof, and even though we try garbage collection, we cannot free any memory. That is because all of those objects we can still get access to using the map. And when we fill it up again, the memory spikes again and we still cannot collect any garbage. With the weak map, when we fill it up, the memory does go up. However, all of that memory can be garbage collected because nothing is holding a strong reference to those objects. Similarly, we fill it up again and the memory again goes up, but all of that memory can again be garbage collected. An obvious question you should have is, what are the main use cases for using a weak map? The answer is pretty simple. When you want to associate data to an object and tie that data into the object lifecycle from a memory perspective, so both the data and the object get garbage collected together, and you want to do this without polluting any of the object properties, you might want to use a weak map. As an example, consider this heavy computation that we need to do given an object that has a value member. The thing that makes it a heavy computation is the fact that we are looping 1,000,000 times. Let's create 100 simple objects with the value member initialized to the array index and measure the time that it takes to do this heavy computation for all of these objects 3 different times. And of course, this will all work perfectly fine, But wouldn't it be great if we could associate the result of the heavy computation with the object so that we don't have to calculate it again and again, but do it in a manner that doesn't hold on to a strong reference for the object, so if the objects ever go out of scope, they can be easily garbage collected along with any computation that we might have stored against them. And no surprise, that is exactly what the weak map is for. We create an instance of the weak map, create a function memoized heavy computation that takes an object, and if the object doesn't already exist within the weak map, we do the heavy computation and set the result against this object as a key and then return the result. Otherwise, we already have that computation within the map and we can simply get that result back by using weakmap.get. So let's run through the scenario again, but this time by using a memoized heavy computation. We loop through the objects 3 times and each time calculate the memoized heavy computation. The first time the computation will take place, but the second 2 times we will simply be getting them back from the weak map that we created. So if you run this code, you can see that the raw version takes around 1.2 seconds, whereas the weak map based memoized version is done in under half a second. Weak map is probably not something that you will be using unless you are building a framework, but if you ever run across it, you can be confident that this is now something that you already know. As always, thank you for joining me and I will see you in the next one. Modern JavaScript includes a built-in primitive type called BigInt, which, as the name suggests, can be used to represent arbitrarily large integers. We can create a BigInt by writing a number as you normally would and adding the suffix n to specify that this is not just a number, but instead it is a big int. It is a primitive type within JavaScript and the type of operator does work on it, and it gives us back the string BigInt. As the name also implies, fractions cannot be a part of integers and BigInts can only be integers. However, you can have negative or positive BigInts. And the key differentiator between a BigInt and a number is that a BigInt can be as big as you want. As an example, if you try to calculate 10 to the power 500 with just JavaScript numbers, that value would be too big for a number, and in fact it gives us that special value infinity that we looked at in our number lesson. However, no integer is too big for a big int, so 10 to the power 500 as big ints will happily calculate 1000 as many as you need. With numbers, it is actually not that hard to run out of the safe integer space. For example, this particular number as a number data type would actually translate poorly and you will actually see 1000 instead of 9999. However, the same value as a big int will be perfectly fine, as we mentioned, as big as you want. JavaScript also provides a BigInt constructor, which can be used to convert, as an example, strings of arbitrary integer size into big ints. Essentially, passing a string to the BigInt constructor is parsing, and of course, equality works with big ints as well. This parsed value is exactly equal to 100n. And this parsing logic also works with other number systems that we looked at in our number tutorial. So the hexadecimal 64 does still parse to 100n in decimal terms. You can convert between a BigInt and a number, and safeguards exist to prevent silly mistakes, but even then you should really consider moving between the two. As an example, we can convert a BigInt into a number by passing the BigInt to the number constructor, and as you can see, 100n converted to a number is equal to 100 in JavaScript. Similarly, we have already seen that we can convert a number into a BigInt by passing it to the BigInt constructor, so the BigInt version of 100 is equal to 100n. However, not all numbers can be converted to a BigInt. For example, if we have a number with a fractional part and we try to convert it into a BigInt, we will get an error in JavaScript, and the error message will be that it cannot be converted to a BigInt because it is not an integer. Similarly, if we have a very large BigInt that cannot be represented as a number, then we will get back infinity. And in the worst case, if it is still within a reasonable limit, we might even get the value wrong. For anything that is beyond max safe integer, you really shouldn't be converting a BigInt into a number. And for the same reason of possible loss of precision, JavaScript doesn't allow you to mix numbers and BigInts in standard mathematical operators. For example, in this particular case, it's going to throw an error that you cannot mix BigInts and other types. You should instead use explicit conversions. And the intent here is that if you explicitly convert using the number constructor or the BigInt constructor, you're sort of accepting the risk that you might lose some precision. So if we wrap the 20n into a number constructor, we can still do math between a number and a number. Begin supports all the standard mathematical operators that you are familiar with for numbers, but with the slight caveat that fractions are obviously going to get ignored. We know from our lesson on numbers that any math beyond the maxif integer is not okay to do with the built-in number data type. However, with the begins, it's completely fine to do as big a math as you want. In addition to the addition operator, feel free to use other operators as well, for example the multiplication star, the subtraction minus, the power star star, as well as the remainder % sign. However, the one operator that you need to be cautious with is of course the division operator, because begins don't represent fractions. All of the fractional part will actually get completely ignored in the output. Begins support the standard comparison operators, and if you are only comparing begins, then it's perfectly safe. But if you throw numbers into the mix, it's a different story. You can compare begins with other begins using the standard strict equality. You can check if one begin is less than the other, or if it is greater than the other, or even if it is greater than or equal to or less than or equal to, and they all work perfectly fine. However, you should be careful when comparing begins and numbers. You cannot use strict equality, as the strict equality cares about the types being the same. However, you can use those equality, but that doesn't mean that it is a good idea. And the other comparison operators seem to work reliably as well. However, be warned, since not all integers can be represented using the number data type, you might result in values that should be equal, yet they are not. The guidance here is that pick a data type that is more appropriate for your use case and then run with it. Don't mix begins and numbers unless you are really sure that the values they contain are safe. Begin is another one of those JavaScript built-ins that you will most likely never use directly, but having a built-in primitive integer that can be as large as you want is important for JavaScript. It allows libraries to use begins internally to do big computations and even provide nice reliable wrappers for mathematical things like big decimals. As always, thank you for joining me, and I will see you in the next one. The weak set, which is built into JavaScript, offers the same feature of weak referencing its members as we previously saw for the built-in weak map data structure. And for this specific use case of not blocking garbage collection, it's a drop-in replacement for the built-in set. Consider two simple objects contained within variables a and b. We can create a set within JavaScript using the set constructor and add these objects to that set. Having these objects within the set allows us to know very quickly if these objects are present within the set or not by using the set.has function. The set data structure holds a strong reference to the elements that it contains, just like the assignment operator, which means that as long as the set is within scope, those objects cannot be garbage collected. So even if we assign a and b to null, we would hope that the memory allocated for those objects is available for garbage collection. It will not be possible because the set has an internal strong reference. And we can actually prove that the set has that reference by simply iterating over the set, and there we go, we have those original objects. This is the main difference between the set and the weak set. The weak set does not hold a strong reference to its members. So let's just create two new variables x and y pointing to two different objects, and just like the set, we can create a weak set by using the weak set constructor, and this allows us to add these objects to the weak set. And the weak set does have the has method that tells us very quickly if an object does or doesn't exist within the weak set. However, unlike the strong reference assignment operator, weak set internally uses something more low level, which is called a weak reference, that allows the original object to be garbage collected. So if the original objects go out of scope, for example we assign x and y to null, because the weak set only has an internal weak reference to its members, it allows the garbage collection of those original x and y objects. And a simple proof of the fact that a weak set only has a weak reference is that it doesn't allow us in any shape or form to find out what items exist within it. Unlike the set, the weak set is not iterable. The weak set shares the same restrictions as the weak map, that is, its items must be objects, and the weak set itself is not iterable. Beyond that, the weak set has the same API as the set data structure. The restriction that members must be objects is there because the members of the weak set must be something that the garbage collector can collect. Here we have two simple objects to demonstrate the API of the weak set, and just like the set, the weak set also accepts an iterable in the constructor. So here we are creating a weak set that only has one item, which is the alpha object. Also, just like the set, we can add items using the add method. We can check if an item exists using the has method. We can remove an item from the set by using the delete method. And of course, once this item is removed, has will return false. Also, just like the set, the weak set delete will return true if the item did exist, and it will return false if the item that we tried to remove did not previously exist within the set. All of this API is actually shared between the weak set and the set classes. But that's where the similarities end. Unlike the set, the weak set is not iterable, and if we actually try to iterate over it, JavaScript will throw a type error. Similarly, it does not have the size property because it doesn't keep a strong track of the objects that it contains, and it doesn't have the clear method because there is nothing to clear. We cannot find out anything about the weak set unless we have the original objects. You can take my word for the fact that weak sets work, but if you are like me and feel that seeing is believing, then strap right in and let's demonstrate that a set blocks garbage collection and a weak set doesn't. We create a simple fill function that takes a set-like data structure and a character and then creates an array of objects 2500 strong, where each object has an ID property, which is an array filled with that character 100,000 times. Now all of these objects are only going to exist within the scope of this function, so when this function returns, they should all be available for garbage collection. However, before we return, we add all of these objects to the set-like data structure that gets passed in. Let's conduct a simple test to compare the memory characteristics of the set and the weak set classes, and for this, we will use the utilities we built in our lesson on JavaScript memory management and garbage collection. First up, let's see how the set performs. We create a set and start off by noting down the current amount of memory being used. We fill that set up with the crying emoji, and afterwards note down the memory used and then invoke the garbage collector to see if we can free up any memory. The expectation here is that all of those objects created within the fill function are still within scope because the set is holding on to a strong reference to those objects. And we can actually prove it even further by simply getting rid of the set. If we assign set to null and then try to collect the garbage, then hopefully we should be able to see that memory getting reclaimed. Now let's try the same process with the weak set. We create an instance of the weak set, we log out the current memory being used, fill that weak set up with the hugging emoji, and then log out the memory being used afterwards, and then try to collect the garbage to see if we can reclaim any of that memory. Hopefully, since the weak set doesn't have a strong reference to its members, all of those objects created within fill should get garbage collected. And now for the moment of truth. You can see that with the set we start off with 50 MB, but then it jumps up by 1000, and even though we try to run the garbage collector, we are not able to free up any of that memory. However, when we assign the set to null and run the garbage collector again, no surprise, all that memory gets freed up, so it was being blocked by the set. Next, with the weak set, all of those objects do get stored within it and the memory does jump up, but then when we collect the garbage, because those objects are no longer within scope, all of that memory gets freed up. An obvious question you should have is, what are the main use cases for using the weak set? The answer is pretty simple. Use a weak set whenever you want to track if you've seen an object before, but do so without holding a strong reference to the object so the object can be garbage collected if required. To demonstrate such a use case, we create a simple weak set called visited with nice utility methods called hasVisited, which takes an object and sees if it is present within the set, and a visit utility which takes an object and adds it to the visited weak set. The intent here is that these utilities can exist in a library or a framework that is going to be independent of the scope and the lifecycle of the objects that we are dealing with. Let's just create a few simple objects, John, Mary, and Jack, and then John comes to visit, and then Mary comes to visit, and at this point we can see that John came to visit, Mary came to visit, and Jack didn't come to visit. Now even though this information is coming from the weak set is not blocking the lifecycle of these objects. So if John, Mary, and Jack all get freed up, the objects previously referenced by these variables can now be garbage collected. Weak set is probably not something that you will be using often, as the objects you are dealing with will most likely live in the same scope as your set data structure. So you don't need to worry about holding a strong reference, as they will both get garbage collected together. That said, weak set can come in handy when you are building advanced frameworks, and if you ever run across the weak set in a codebase, you can now be confident that it is something that you already know. As always, thank you for joining me, and I will see you in the next one. There is a saying that when you see a problem and decide to use a regular expression to solve the problem, all of a sudden you now have two problems. Humor aside, the main objective of a regular expression, which is also called a regex, is to validate, search, and replace text. We can create an instance of a regular expression within JavaScript by using the built-in regex constructor. But this is really how people normally create regular expressions, because they are such a core part of JavaScript that JavaScript has special syntax for creating regular expressions. And as far as differences between the two is concerned, they are both equivalent. They are both instances of the built-in regex class. The string representation of the regex gives us the original special syntax that we would have used when we wanted to create the regex, and we can get just the source string which we would have passed to the constructor by using the source property. One of the simplest methods on the regex is the test method, which takes an input string and returns true if the regex finds a match within that string. Now this particular regex that we have created is searching for the characters A, B, C, D, E, F in that sequence, so of course it matches this particular string. However, by default it is case sensitive, so something like capital A, B, C, D, E, F will not match, and therefore test returns false. Now regex is actually searching for a match within that string, so if A, B, C, D, E, F exists anywhere within the string, test will return true. In addition to the source, the other portion of configuring a regular expression are the flags, which determine key behaviors of the regular expression. One common flag is I, which stands for case insensitivity, and G, which stands for global, which is required for functions that are designed to work for multiple matches. There are other flags as well, but they are rarely used, so we won't bother covering them in this particular tutorial. We can pass the flag to the regex constructor as a second argument, or alternatively, when we are using the special syntax, we can provide them after the ending slash. Here we are providing only one flag, which is I for case insensitivity. So this particular regex will match A, B, C, D, E, F lowercase, as well as any mixed case version or full case version of the same characters. Similarly, we can create a regular expressions for the characters F, O, O, and then we can create another version with the global flag. With the global flag, the guidance is pretty simple. If you are using a function that does not end with all, do not use the global flag, otherwise you will get some behavior that you should not care about in modern JavaScript. For our demo demonstrating the differences between the global and the non-global version of a regex, we will create a very simple string, table football, foosball, and you can see that foo appears twice within this string. With the match function, you should actually use the non-global version, and this will still give you back an array, but as you can see, it only contains one match, and that is because we are using the non-global version. If you want to get all the matches, we should use the more modern match all function, and if you actually try to pass it a regex that does not have the global flag, JavaScript will actually throw a runtime error that match all was called with a non-global regex. The fix, of course, is pretty simple. We should invoke the all style function with a regex that has the global flag, and in that particular case, it returns an iterator, and as you can see, it has two items inside of it, so it is matching both the football and the foosball foo. As you would expect, sometimes you might need to change the flags on a regex. For example, we have a simple regex with just one flag, which is I, and we can actually create a different one with both I and G by using the regex constructor, using the source property of the original regex, and then using the original flags and combining anything else that we want. For example, we want to make this one global. Methods exist on the regular expression object that take a string, but most commonly you will be using methods that are built into the string type and pass in the regular expression as the argument. We've already seen the regex method test, which takes an input string and returns true if the regex finds a match within that string. A method actually exists on a string called search that takes a regex as an input and then returns the index of the first match within that string. So here the match for ABC exists at index 0, and within underscore ABC, the match for ABC will exist at index 1. Of course, if no match is found, then the search function returns -1, which is similar to other index-based search functions we have looked at in this course. One of the most powerful functions for a regular expression within JavaScript is string match. If no match is found, then it returns null, so of course ABC does not contain any instances of foo. However, within the string, games football, foosball, foo exists twice, and match is something that you should use without the global flag. and it will give you back the first match at a property index 0. And another property this match will have is index, which will tell you where in the string this particular match was found. In this particular case, it was found at index 6. If you want to find all of the matches, you should use the match all function and then pass in a regex that contains the global flag. It always returns an iterator, which we can easily convert into an array by using the spread operator. And in this particular case, no match is found, so the array is going to be empty. However, when we repeat the same example, games football, foosball with match all and foo being case insensitive and with the global flag, we get back an iterator that should have 2 matches. And each of the items within the match are going to be exactly the same as the result for the single match. That is, at the 0 index, we will find the matched value, and at the index property, we will find the index for that match. Similar to the string match all duality, string also has replace and replace all functions, and you should use replace without the global flag, and you can replace the first instance. As an example, here we are using replace to replace the first instance of A with capital A, or alternatively, you can invoke replace all with the global flag, and here we are replacing all instances of A to be capital cased. And finally, the split method that exists on a string also accepts a regular expression, and this returns an array of the text surrounding the matches. So in this particular input, we get the strings that are surrounding the character A. Obviously, there is a lot of regular expressions, and as they get large, they get a bit hard to understand. So here are some excellent resources that will help us deep dive into regular expressions, and with these, you can just pop in your regular expression and it will explain in human language what the regular expression is trying to do. The first resource that I want to point out is regex 101, and this is what I tend to use when I'm working with languages beyond just JavaScript. On the left, you can select the language that you are working with, and right now we are working with JavaScript. On the right, you can provide your text, and in the top, you can provide the regular expression that you want to use to match with that text. So here we have the input string ABC, DEF, ABC, and when we pop in the regular expression ABC, you can see that it finds 2 matches, one from index 0 to 3 and the other from index 8 to 11. But the most important thing over here is that it is explaining what the regular expression is trying to do. In this simple case, it is simply trying to match ABC, literally the characters in that order. When I'm exclusively working with JavaScript, perhaps a better resource is regexer.com. Here again, you can provide your input text, and we will use the same text ABC, DEF, ABC, and on top we can provide a regular expression. So here we are using the regular expression ABC, and you can see that it again found 2 matches. And it is explaining what that regular expression is trying to do. In this simple case, it is looking for the character A followed by the character B followed by the character C. If all we are doing is searching and replacing simple exact strings, JavaScript built-in string find and replace would be sufficient. But what makes regular expressions really powerful are its support for special characters. So let's uncover the full-blown programming language in itself, that is regular expressions. The simplest special characters are the caret and the $sign, which are used to match the start and the end of a string. So given this input string, we know that we can find all instances of the characters ABC in that order by simply using the regular expression ABC. However, if we only want to match the ABC if it exists at the start of the string, we can use the caret character to specify that we only want to match ABC when it appears in the beginning of that text. And similarly, if we only want to match ABC if it appears at the end, we can use the $sign to specify that match me ABC only when it is followed by the end of the text. So now a question that you should have is, what if you want to match the caret character by itself? For that purpose, you can actually use the escape character, which is \. So \caret will match caret exactly. And similarly, $$ will match the $character, and actually \\/ will match the \ character itself. And in addition to these special characters, we can use the \ with any of the other special characters that we will look at as well. One of the most powerful features of JavaScript regular expressions is that they support look ahead and look behind, which are collectively called look around. So given this input string, we know that we can find all instances of the character B by just using B. However, what if we only want to find the B's if they are preceded by the character A? This is called a look behind, which we can do with parentheses question mark, less than to signify behind, equal to signify that it should exist, and anything that we want to match, which in our particular case is simply the character A. And now you can see that only the B's with the A before them have been matched. Instead of equals, we can use the not to specify that the sequence, which in our case is just A, should not exist. And now only those B's have been selected where the preceding character before B was not A. Similar to positive and negative look behind, we have the positive and negative look ahead. So if you want to make sure that we only select the B if an A appears in the forward, we can actually use parenthesis question mark equal followed by the pattern which is A. And now only those B's have been selected which are followed by A, and similar to the positive look ahead, there is a negative look ahead. We simply replace the equal sign with the not operator, and now it will search for B's such that the next character is not going to be A, and in our particular example, there is only one such B. Regular expressions also allow you to specify quantifiers, so you can choose to only match text if it appears a certain quantity of times. So consider the input text, which is a soup of B followed by O's followed by H's. We can select all instances of B's followed by O using BO, but as you can see, we have an O without a B, so we can actually make B optional by using the question mark quantifier. And then we can select 0 or more O's by using the star quantifier. And finally, we have the H at the end, and again, we will select 0 or more H by using H star. Unlike the star, which is 0 or more, we can actually use the plus quantifier, which is 1 or more. So in this particular case, B is optional, O must exist 1 or more times, and H can exist 0 or more times. In addition to the question mark, plus and star quantifiers, we can actually provide exact numbers as quantifiers as well. As an example, if you want O to appear exactly twice, we can provide that number between curly brackets to specify the quantity must be 2. We can even provide a minimum and a maximum quantity. So as an example, we can specify that O must appear a minimum of 1 and a maximum of 2 times, or even something more diverse like a minimum of 1 and a maximum of 10 times. And you can see that we are only matching strings if they have the required quantity of O. Regular expressions also support built-in character classes that allow you to easily match a set of predefined characters. The built-in character class word can be used with \w, and as you can see, it matches all alphanumerics along with underscore. Another character class is \d, which stands for digits, which are the characters 0 to 9. To match all of the white space, including spaces, tabs, and line breaks, we can use \s. We can actually negate all of these character classes by using capitalized versions of them. For example, \W matches anything that is not a word, which in our case is just the white space. \D matches anything that is not a digit, which is everything other than the digits. \S matches everything that is not a white space. A very special character class is actually dot, which matches anything except a line break. Its main use case is matching things that surround a particular pattern. For example, we can select any character followed by E, followed by whatever follows E by using .E dot, which in our example matches Meg. In addition to the built-in character classes, you can also define your own custom character sets. We know that we can match all instances of A using A and all instances of Z using Z, but we can actually match all instances of A or Z by creating a character set between square brackets that only include the characters A and Z. Additionally, we can include a dash between A and Z to include all of the characters that exist in the range A to Z, which is all of the alphabet. We can add numbers to this set as well by using 0 to 9, and we can even bring in complete character set, for example, all of the white space by using \s. Now, because dash is used to provide a range within character sets, if you want to match the dash, you must provide it either at the start or at the end of the character set. We can actually negate the character set as well, so if you only want to match things that are not a part of this character set, we can use the caret as the first character within the character set. So now in our example, it's only matching capital characters which are not a part of this particular character set. Another special character worth knowing is the pipe, which is used as the logical OR. We know that we can match the simple character sequence ABBA using ABBA or LOL using LOL, but what if you want to match ABBA or LOL? Well, the answer is pretty simple. Just put a pipe between the two character sequences, and now it's either going to match the first one or it's going to match the second one, and nothing else is going to get matched. When you want to take a portion of the match and add additional specifiers to that group, we can do that by creating what are called capture groups. As an example, let's say we want to match the characters ABBA when they appear twice in a sequence. We can try to use the quantifier 2 at the end, but it's actually only going to be quantifying the last A, so it is ABBAA. But what we really want is the whole group ABBA appearing twice. We can do that by adding a grouping before we use the quantifier, and now it's only going to match ABBA. The reason why groups in regular expressions are called capture groups is because they allow you to get access to what is matched for each group. The groups are essentially captured and handed over to you for further analysis. Consider the string from which we want to extract any multiplication of two numbers, which we assume are going to be the width and the height. We can match digits using \d, and we want these digits to appear one or more times, which we do with the plus quantifier. Then we want to follow it up with an x, and then another digit sequence one or more times with \d plus. And it does achieve our objective of matching this particular string, but wouldn't it be great if we could extract the width and the height portion of this particular match into their own groups? And that is why groups are called capture groups. We simply put parentheses around the first digit plus, and then parentheses around the second digit plus, and now if we hover over the match, you can see that it contains groups, the first one being 1920 and the second one being 1080. So let's take a look at how we can get access to these groups using the JavaScript match and match all functions that we looked at before. We create a simple string that contains a resolution value. Now if you were to use a regular expression without any capture groups, we will still get a match, but as you can see it has a length of 1 and the item at the 0th index is the full subportion that got matched. If however we invoke match with capture groups, with separate capture groups for the width and the height, the return result has a length of 3, the item at the 0th index is still the full resolution, but now it has an item at index 1 which is the width and an item at index 2 which is the height. And we can actually use array destructuring on the grouped result to get the value, the width and the height into their own variables. Now let's consider another example which has multiple resolutions embedded inside of it, and for this particular case we would want to use match all and then use the global flag within our regular expression. Match all returns an iterable, so we can simply loop over it using for off, and then each of these items is going to be the same as the result we saw for the match, so it will contain the value, the width and the height at index 0, 1 and 2. Now that you have completed this masterclass, you have no reason to be afraid of regular expressions, and if you ever come across them, you have access to resources to easily decode them. If you ever want to refresh your memory, you can always just watch this tutorial again. As always, thank you for joining me, and I will see you in the next one. We've already looked at the JavaScript built-in weak data structures, which are weak map and weak set, but if you want more low-level control of weak references to build your own data structures, or just want to gather a deeper understanding of how these data structures work underneath, then learning about the weakref class is exactly what you need. Normally, when we assign an object to a variable, this is what JavaScript calls a strong reference, and since this is what we use most commonly, feel free to call it just a reference. We can use this reference to access the object's members, for example the x and the y properties. Modern JavaScript comes with a built-in class called weakref that takes an object into its constructor and then wraps it up into something that does not hold it using an assignment operator. What it does internally is actually more low level, and we do not have any special syntax for it. This is actually baked into the JavaScript runtime. Now, if we want to get access to the original object that the weakref is wrapping, we actually have to use the deref method provided on the weak reference. So as long as that original object has not been reclaimed by the garbage collector, we can access the x and y, which should be 10 and 10. However, if the garbage collector runs, for example because of memory pressure, and it wants to clear up as much memory as it wants, it might get rid of that original object that we passed to the weakref. However, any object that is truly referenced from our code, for example by using the assignment operator, will still exist. So ref will still have an object that has x and y. However, weakref.deref might actually give us back undefined because the original object that we passed to weakref has been garbage collected. So unlike a reference where you can always use the properties that you want, with the weakref you should always check if the response from deref is undefined, for example by using optional chaining. And that's pretty much all that there is to the weakref. We have the weakref constructor, which takes an object, and the weakref deref method, which returns the object if it's still available, or undefined if it has been garbage collected. As always, you could take my word for the fact that weakrefs work, but seeing is believing, and demoing a weakref letting go of its memory, while a strong reference preventing garbage collection, will give you some insight into how memory management works in JavaScript. Unlike our previous memory management tutorials where we used special APIs within Node.js, let's do the demo of the weakref by using the Chrome developer tools, and this will actually give you some insight in how you can profile and manage the performance of your own JavaScript applications. On the top we have the performance tools with the memory checkbox selected, and at the bottom we have the developer console. Let's start recording to see what the memory profile of some code is going to look like. Within the console, we create this utility function called createHeavy, which creates an object which has a heavy property, which is going to be an array of 10 million items, all filled with the rose emoji. Next, we create 3 strong references to the objects that we create using this utility, stored in variables a, b, and c. This should see our memory consumption go up because we've created some pretty heavy objects, and this memory cannot be deallocated as long as a, b, c are pointing to those objects. Next, we create 3 more heavy objects, but this time we wrap them up with weak references. This means that while memory will be allocated, if there is ever memory pressure, then the garbage collector can jump in and free up the memory for these objects. The strong references ABC will always contain the objects that point to those rose emojis. However, the weak ref may or may not. Right now, it seems that the garbage collector hasn't run, so the weak references do point to objects that contain the rose emoji. Now let's push things in our favor a little bit by triggering the garbage collector manually by clicking the trash can within Chrome Developer Tools. Since these objects were pretty large, the garbage collector has most likely reclaimed the memory for anything that was a weak reference, and our assumption is proved to be true. You can see the strong references still contain the rose emojis, however the weak references have all been cleared and they are now undefined. The garbage collector will be able to garbage collect the strong referenced objects as well if you were to assign A, B, and C to anything else like null values. So now if you run the garbage collector again, we should be able to see a decrease in the memory consumption in the final profile that will be collected. And now for the moment of truth. The memory consumption actually looks exactly how we thought it would be. It starts off at a reasonable level, then it jumps up when we allocate those heavy objects and store them into strong references. Then it jumps up again when we allocate more heavy objects and store them in weak references. But when we run the garbage collection, all of those weak referenced objects can actually get garbage collected and the memory consumption jumps down again. And finally, when we assign those strong references to null values, all of those can be garbage collected as well, and the memory consumption jumps down even further. As we mentioned in our lessons on other weak data structures, you really need to worry about weak references, as objects and references that are used to hold that object normally live in the same scope and they get garbage collected together. But it's great that JavaScript provides such low-level control to its memory management while still keeping it high-level enough that we aren't directly responsible for allocating and deallocating our own memory. As always, thank you for joining me, and I will see you in the next one. A memory leak is a programming language term used when a program holds onto memory that it doesn't intend to use anymore. Just like a water leak wastes water, a memory leak wastes memory. A memory leak can slow down a program as it continues to request more and more system resources, and over time, it can lead to an out-of-memory error causing the program to crash. To demonstrate a memory leak, consider a simple function that allocates a lot of memory. It creates an array of 2500 items where each item is a heavy item, which itself is an array of 100,000 items filled with the bang emoji. Allocating memory by itself is not going to be a memory leak, but holding on to a value after you are done with it is a memory leak. For example, if all that we cared about was to read the length of the result, after we are done with that reading, we should get rid of the result as we no longer need that value anymore. If we don't do that and just keep creating more variables for more allocations and not getting rid of those variables, then we will eventually run out of memory. Let's demonstrate that by executing this code. You can see that we can allocate memory and we can read the length of the result. However, now you can see that the JavaScript runtime is struggling, and in fact, it will exit with an out-of-memory error. If we scroll up a bit, you can see the error that we crashed with. It is JavaScript heap out of memory. As we saw in our garbage collection tutorial, JavaScript manages memory for us. So fixing a memory leak is a simple matter of letting go of resources that you no longer intend to use. For example, scoping your variables only to functions where you use them, or even setting a variable to null when you are done with its value. In this simple example, as soon as we assign result to a different value, the previous value is available for garbage collection. So we can allocate as much memory as we want and store that into different results. And once we are done reading its length, we can reuse that variable for something else. And now if we execute this code, even though it is allocating a lot more memory than it was before, all that memory that we do not use anymore can be garbage collected, and the program runs to completion successfully. It can be argued that the key reason for the success of JavaScript is its support for closures, but sadly it's also the number one reason for a memory leak in JavaScript. This is because functions can have implicit strong references to variables outside of their scope, which prevents their garbage collection. Here's an example of a simple function that takes a value and then wants to keep a strong reference to it because it intends to use it in a local function. We return the getLength function from our closure, and as long as this getLength function is in scope, the original value is also going to stay in scope. So we invoke closure with some memory allocated for the value, and as long as the return function fn1 is going to be in scope, the original value is going to be in scope, and we can see that because we can use fn1 to read the length of the original value. So every single time we invoke the closure function with a value, the return function is going to hold on to that value, and if we do it a few too many times and execute this code, it will eventually run out of memory and the program will crash with an out of memory error. Now, of course, our particular functions are holding on to very big values, but I wanted to make clear the fact that a function can increase the lifetime of a value. So essentially, until we get rid of the function, that value is going to stay around in memory. The solution for values being held by closures is the same as any other memory leak. You need to think about which values you don't need anymore. For example, you can discard the function or discard the references to the data within the function. As an example, instead of keeping a reference to the value, what we could do is we could note down the length of the value by itself, and then within the function that we are returning, we only reference length, and there are no more references to value once this particular function returns. So now if we run this code again, even though we are holding on to the function getLength, it is not referencing value, it's referencing a simple number, and therefore the value itself can be garbage collected and our program executes without any issues. We've seen that functions hold on to memory for external variables they reference due to closures, but it will not make your program crash as long as you don't store too many functions. But we can end up in this silly situation by mistake when we are adding event listeners on some interaction, but not removing the event listeners that are no longer relevant. Consider the simple example of a Photoshop style application. When the user clicks on the Paint tool, we want to add an event listener that handles all cursor moves. If we add an event listener every single time the user clicks on the Paint tool, then we will end up with lots of event listeners, each with their own memory, preventing garbage collection. So the memory consumption of our application will continue to go up, and if we have enough event listeners referencing enough values, then our program will eventually run out of memory and crash. The solution to this problem is pretty simple. Whenever we are passing around functions for event handlers, we want to make sure that we unsubscribe that if it is no longer relevant. This particular add event listener gives us back a function which we can use to unsubscribe. So every single time we make a new subscription, we make sure if we already have a subscription present, we remove that using remove event listener. This will ensure that add event listener is not referencing functions that it no longer needs, and they can be garbage collected. And now if we run this code again, every single time a new subscription is added, the previous subscription is removed, which means that the previous function can be garbage collected and we don't have a memory leak in our code anymore. Here is a simple takeaway from this tutorial. Don't hold on to references to data or functions which you no longer need. This allows the garbage collector to jump in from time to time to clear up any unused resources, and this will keep your JavaScript programs snappy and efficient and your users happy. As always, thank you for joining me, and I will see you in the next one. As you work on JavaScript code bases with other engineers, there will definitely be some stylistic choices that you will all need to conform to. A lot of these are fairly universal across JavaScript projects, but a common one that can result in some friction amongst team members is semicolons versus no semicolons. You should use whatever your project already uses, and this means that as professional engineers, you should be familiar with the special patterns to follow for semicolon-free JavaScript programming. For much of JavaScript programming, it actually doesn't matter if we do use semicolons at the end of every line or if we do not. People that use semicolons argue that it conveys a clear intent of an end of a statement, whereas people that do not use semicolons argue that it just looks cleaner as there is less character noise. For this particular example, JavaScript doesn't care. The code will behave exactly the same with or without semicolons, because without semicolons, JavaScript will automatically insert those semicolons for us using a thing called automatic semicolon insertion, or ASI. However, let's consider another example with an additional statement. In this particular case, if we were to remove the semicolons, the code will actually error out with type error 2 is not a function. The reason why this is going to error out is that the JavaScript parser, in the absence of semicolons, will view this code as 2 statements and not 3. And now you can see why this code is erroring out, because yes, 2 is not a function. The solution is pretty simple. We can add a semicolon whenever we end up in such a situation. But this means that we actively need to care about the contents of the next line. The smart fix is to put the semicolon at the start of any line that initiates with a parenthesis to prevent any association with any code that might come before it. If we decide to go semicolon free in JavaScript, here is another scenario that we need to know about. This code would work fine if we had semicolons at the end of every line, however, it fails if we do not do so. The reason, of course, is that the JavaScript parser is parsing it as 2 statements instead of 3, resulting in an unexpected error cannot access B before initialization. The solution for this is the same as the solution that we have for parentheses. If a line starts with square brackets, prefix it with a semicolon. If all you've ever done is semicolon-based programming, as an example like myself, someone who programs in multiple programming languages, then this can look a bit weird, but if you want to go semicolon-free in JavaScript, then these simple tricks do become second nature. A very common code formatter that people use to bring style consistency to a codebase is Prettier, and most use it with the default options, which actually agree with my personal preference as well. If you look at the options that Prettier provides, one of them is regarding semicolons. There are 2 valid values, semicolons true and semicolons false. The default is semicolons true. If we set it to false, then Prettier will add semicolons at the starting of those lines that require it, which are lines that start with parentheses and square brackets. And we can see it in action if we jump into the Prettier playground, paste in some code that we know works perfectly fine if we always use semicolons, and right now the output is the same as the input. However, if you modify the options to use no semicolons, you can see in the output that Prettier has removed the semicolons and added them at the start of the lines that require it. This means that if you decide to use Prettier with semicolon-free programming, you are less likely to make any silly mistakes. Even though I personally use semicolons, if you are working on a codebase that doesn't use them, you can now be confident that it is a pattern that you are familiar with. As always, thank you for joining me, and I will see you in the next one. One of the greatest features of modern JavaScript is a standardized module system that works for both browsers and server environments. Modules allow you to keep your code organized and maintainable, and the key way you control how the module system works in a JavaScript project is by using the package.json file. Within an empty folder, we create a new package.json file, and we only need 2 fields in order to turn this folder into a package for JavaScript modules. The first field is type, which we need to set to module in order to let Node.js or any front-end build tool know about the fact that the files within this package will consist of ES modules. The next field is main, which must be a full relative path including a file extension to our main application or package entry point. Modern project templates for popular frameworks already come with these options configured, but it's good to know what these options are doing. Let's demonstrate this in action by creating our main application entry point, source index.js. Because we've specified that we have type module, it means that we can use ES module syntax like a simple export statement. Of course, in addition to exports, we can add any other JavaScript logic as well. For example, here's a simple console.log. Now, in order to execute this package, all that we need to do is to go into the folder that contains package.json and pass in dot for the current directory to Node.js. And because everything ran without issues, it means our configuration is complete and validated. With this simple setup out of the way, let's dig deeper into the core syntax for JavaScript ES modules, and at its heart, it consists of export and import statements. We create a simple file, example.js, and add a few simple JavaScript identifiers. We have a message pointing to a string, a simple sum function that adds two values, a simple sub function which subtracts two values, and now we want to export them for reuse across our code base. We can export the things that we intend to use elsewhere by using an export statement, and at its simplest, we specify the identifiers we want to export between two simple curly braces separated by commas. Now let's look at how we can use these exported identifiers in a different module. We can bring in all the exports of a module into a single identifier by using the import star syntax. So here the identifier example will contain everything that was exported from example.js. We can use the identifier example to read the message property, which will be the string hello modules. We can use the sum function to add numbers. We can use the sub function to subtract numbers. And this is the fundamental pattern of code export and code import using ES modules. In addition to exporting and importing things as a whole in bulk, we can also export items individually at the point of declaration and similarly import items individually by name. So let's get rid of the sum and the sub exports from our bulk export statement. Instead, we can prefix the function declarations or even the const if we wanted to with the export keyword, and this will automatically add them to the exports for this particular module. This code is functionally equivalent to the code that existed before we started this refactor. Similarly, on the import side, instead of bringing everything into the properties of a single identifier called example, we can bring in the different identifiers by name from the example module by using curly brackets in our import statement. So in addition to example.sum and example.sub, we have the sum and sub functions directly imported as well, which means that we can use them without the example prefix. And functionally, this code is going to be exactly the same as before. And if you were not using example.message, we could even get rid of the import star altogether. Now it is understandable that the identifiers exported from example.js might conflict with identifiers we have within our index.js. For example, if we had a local sum or sub function, we would run into name conflicts. With import star, you are free to call the identifier whatever you want. You don't have to call it example, but with named imports, you need to use the name that was exported from example.js. However, we can change the name that exists within index.js by using as followed by the identifier that we want to use. So now sum and sub are no longer identifiers within index.js, and if we want to use them, we must use the identifiers summation and subtraction. And now if you open up the terminal and execute this code again, you can see it still works, confirming our additional understanding of JavaScript modules. Quite commonly, you only have one main export from a file that you want people to import. And to make this pattern convenient, JavaScript comes with a special syntax for a default export and a default import. To specify that an export is a default export, we simply use export default. There can only be one default export within a module, and here we are saying that for the example module, message is the default export. Bringing in a default export is one of the simplest things within JavaScript. We simply import, followed by the identifier we want to use for the default within this module, followed by from, followed by the module. And now we can use this identifier message anywhere within index.js. For example, we can modify our first statement to simply log out the message. The static import statements which we have been using need to be defined upfront. This means they need to be at the root of the file, the import name cannot be a variable, and the import cannot be done conditionally. To demonstrate how these requirements can be a bit restrictive, let's create two simple JavaScript modules. First, we create a module circle.js, and within that, we simply log out circle.js loaded, and we provide a simple function called render, which logs to the console rendering circle. Then we create another module square.js which follows a similar pattern. It logs to the console square.js loaded and provides a simple function called render which logs a rendering square to the console. Within our main application entry point index.js, we have a shapes array which consists of a circle and a square, and for each shape of shapes, if the shape is a circle, we want to import circle from circle.js and then use its render method. And if the shape is a square, then we want to import square from square.js and use the squares render method. Unfortunately, this particular code is not going to execute and it will immediately error out because an import declaration can only be used at the top level of a module. The fix is pretty easy. We need to take these import statements and move them out of any condition or function or a for loop. And now if you were to execute this code, it would work without any issues. Circle.js will get loaded, square.js will get loaded, and we can use their methods to render circles or squares if we wanted to. To allow us to dynamically load modules based on a condition, JavaScript comes with a special promise-based dynamic import syntax that allows loading of modules using conditions and variables. Right now we are rendering a circle and a square using the circle and the square modules. But what if the shapes that the user wants to draw only consist of circles? You can see that we are only rendering circles over here, but we are still loading square.js even though this is not required for this particular input of shapes. Loading, parsing, and executing JavaScript that we do not need is a waste of resources that we should try to avoid. To allow us to conditionally and lazily import the modules that we need, JavaScript provides dynamic imports. A dynamic import within JavaScript consists of the import keyword followed by parentheses. This actually returns a promise for the module that we want to load, and we can simply wait for it to resolve by using the await keyword. And then, same as before, we use the returned module's render method to render a circle. We can repeat the process if we ever encounter a square. We await an import for square.js, store it into the square variable, and then use its render method. And now if we only have shapes that are circles, then only circle.js will be loaded, and we can verify that by executing this code. If you modify the shapes to include square as well and execute the code again, then of course square.js will also get loaded. With dynamic modules, in addition to loading them conditionally, we can actually even use variables for the path of the module that we want to load. And knowledge of this fact can actually simplify this particular piece of code significantly. We use the shape variable in each iteration to import the required module, and then from the returned object, we pick out the render method. And then all that we need to do is to invoke this render method, which will belong to that shape. Functionally, this code is exactly as what we had before, but as you can see, it is much more concise and cleaner in its purpose. One thing that is often overlooked about JavaScript modules is the fact that the module code is executed only once and on first request. After that, the exports get collected and cached, and the same exports are returned every time the module is requested. We create a simple module that starts off by logging to the console module loading started, then exports a simple message variable, and then at the end of the module, it logs out module loading completed. Now let's jump into our index.js and import this module using a standard static import. The first time within our program we request this module from the JavaScript runtime, it will look at its cache, and if this module has never been executed before, it will execute the module code and then collect all of the exports that that module provides and return them as a response to our request. And now anytime from anywhere within our program, if you request the same module using any syntax, for example import star or a dynamic import or anything else, we will always get that cached result back from the JavaScript runtime. And we can actually verify that if first is strictly equal to second, and indeed they will be references to the same value. In addition to first and second being equal because the result came back true, there are other things that you should notice in this console as well. Before the first was returned, the original module code started executing and then it completed. Then the first was returned, and then for the second case, the module code was not executed again, which once more points to the fact that we were returned the cached value. The beauty of JavaScript modules is that it allows people to freely publish and share reusable code using a central registry called npm. All that's needed in order to import these packages is a simple npm install. For this demonstration, we will be using a very simple but very popular npm package called Chalk, which has right now 251 million downloads every week. To get Chalk, all that we need to do is to open up the terminal in the folder that contains our package.json and execute npm I Chalk. Once this installation is complete, you can see that Chalk is installed and loaded into node_modules. To bring in a module which is installed as a package, for the path of our import, we actually use the package name. So here you can see that the import path is just Chalk, not chalk.js, and it is not a relative path like we have been using for our own modules. Now the Chalk module only has a default export, which is why we are using the default import syntax to bring that export into a Chalk identifier. And now we can start using Chalk to make our terminal logs prettier. For example, I love JavaScript in yellow and bold, and if we execute this code, that is exactly what we see in the terminal output. Once you understand JavaScript modules and start using them, it fundamentally changes the level of things that you can achieve. As always, thank you for joining me, and I will see you in the next one.